crypto-only venture fund operating out of Amsterdam. We've been active in the space since around 2016, 2017, and been co-hosting the Modular Summit for 3 times now, which is also why my co-worker gave me the honors of giving the opening statement here. Thank you for that, Balder. So I figured it would maybe be nice to explain a little bit how we got involved with Celestia, then how we have seen sort of the events change over the last 3 years, or 4 years maybe even, and then where I expect us to be heading. And then I'll wrap it up with some practical information around the event. So how did we get involved with Celestia? Well, I've been telling the story 1,000 times over the last year, so one more time won't hurt. We ran into Celestia when I got a research newsletter in 2019. This was around the summer. And the goal of this newsletter was to send all the academic research that had been published that week around to people interested in it. And one of the papers in there was called Lazy Ledger. It was written by Mustafa Al-Bassam. And I read it. I found it quite interesting because it featured like this data availability sampling feature, I would almost say, of the blockchain, where it allows you to hold the validators accountable by running a light node on a very lightweight device, such as the phone that Mats is holding right there. And so you could run a light node, and that was quite unique in the crypto space. So I started stalking the Lazy Ledger team back then on GitHub a little bit. I ran into John Adler, and I found his Telegram handle on his GitHub. I reached out to him, and as soon as he noticed that I was an investor, he told me to reach out to Mustafa, which already made it pretty clear that John Adler would not be doing the investor relations at Celestia. However, we did get in touch with Mustafa, and we started talking about the product and the project. And eventually, we, as Balder put it back then, we jumped on the Lazy Ledger train around end of 2019, start of 2020. And we've been working with the Celestia team since then. So then onto the sort of things we do with them. And one of them is event planning, right? Which at that point, we pivot from venture investor into event planners. The first event we did with Celestia was in Lisbon in 2021. This was, I think, sort of the fall. And it was an evening event. There were in total 4 talks and 1 panel with the people who gave the talks. Maybe as comparison, over the next 3 days, there will be 100 talks here. And I think over 20 panels. So you could say it has expanded a little bit since then. But we kind of liked it. And it was in general well received. So that's why we hosted Modular Summit 1 around DevConnect in Amsterdam. This was a 1-day event, was in April 2022, sort of for crypto timeline, just before Terra blew up. That's what people will remember. And it was, again, a very well event with sort of the right people. However, one thing that stuck with me, especially back then, was that it was all quite conceptually and academic, right? Like, hey, if we ever build this, then we could do that. And then users will benefit from this. At the same time, it was all on paper and not at all like in practice. I think that already started to shift a little bit with the second Modular Summit that we hosted in Paris last year. That was a 2-day event, featured a lot of tracks, and you could sort of, the first inklings of an ecosystem were starting to take shape. So there was a ZK track hosted by ZK Validator, there was an MEV track hosted by Flashbots, and a gaming track hosted by Argus. You could already see like, hey, there's something more happening here than just people thinking out ideas in the background. And that brings me sort of to the year that has happened, right? Obviously, the big thing was the Celestia mainnet launch in the past year. I think what that caused is also the theme for this conference, which is modular expansion. So what we have really seen is that a lot of use cases and actual applications have started to take off. Celestia is now live. There's some applications on it. There's traction on it. Things like Lyra, Evo in the DeFi ecosystem. Things like Ancient Ain't in the gaming ecosystem. And then Forma Chain for like NFTs, art, etc. I think what's going to be even more interesting in the year ahead, and what I think it also shows what you can do if you sort of build whatever and give developers and users a lot of freedom, is the Celestia native or ecosystem native projects. So the modular ecosystem is expanding, and things like Initia, Astria, Sovereign Rollups through Sovereign Labs, also mentioning a lot of portfolio companies here, but allow me please, are now being built and being deployed. And what I hope that what that leads to in the next few years is that we actually build better applications for users and developers. And therefore we bring more attention into crypto. And I think a lot of people at this conference have said, like, hey, we want to see more applications. Well, I think now the modular expansion is sort of happening. That's the time when we can start doing that. And I hope to see more of that over next year. So then onto the more practical stuff. This is obviously a 3-day event. There's buses going through and from the venue every morning. And in the evening, they take you back into the center of Brussels. Then there's a boat, which I highly recommend. It's a 30-minute boat ride. Not the quickest way to get here, but I do think it's very enjoyable, especially with this weather. On the website of Modular Summit, you can find the locations where you can be picked up and the entire schedule for it. There's lunch, snacks, and drinks on the rooftop there. So I think, all in all, you should have a good time here. And finally, I would also like to thank Yes and Nat from the Celestia team. They've been realistically the ones who put a lot of this together. We like to take credit, but they've been working very hard at it. So I think all credits to them, the rest of the Celestia team, and also all the amazing sponsors that happened to make this possible. I hope you have an amazing 3 days here, and I'm sure we will. Thank you very much.
All right, thank you, Matthijs. Next up is going to be Anurag, and he's going to talk a little bit about Avail Nexus. Please take the stage. Everybody give him a hand.
Thank you. So apparently I'm the one kicking off the summit with the first talk. Okay, quick introduction. My name is Anurag. I'm founder of Avail. Avail builds data availability scaling solution that that implements data availability sampling using validity proofs, slightly different from Celestia, which uses fraud proofs. Although I'm not going to talk too much on the data availability part today, what I'm going to cover today is solving the issue of L2 fragmentation with Avail Nexus, which is a component that we build on top of Avail DA. Some background of Avail before I get into the meat of the topic. So what is really Avail? So most people might have heard of Avail as I myself also said that the base layer is the Avail DA part, which is this state-of-the-art data availability layer, which implements data availability sampling with validity proofs. But we don't stop at that. Because we've built this base layer with validity proofs, we are also able to build something called Nexus on top. And what is Nexus? Nexus, you can think of Nexus as this permissionless verification hub, so that rollups that operate on top of Avail can also verify, proofs, for example, on top of Nexus. And that allows us to kind of unify these rollups and chains together to enable interoperability and async composability between these rollups and chains. How we do this, I'll get into the details of that, but we do it with this mixture of proof aggregation, ZK proof aggregation, and data availability sampling proofs. We also have a component called Fusion that I'll not get into too much detail. You can look up our website for more details, but I will cover some of it, right? Like from a Avail DA perspective, just to kind of start off the presentation, as I've already said, state-of-the-art data availability layer implements data availability sampling with validity proofs. So what we do slightly differently is we do not have fraud proofs. We use KZG polynomial commitments to implement this. This is similar to the primitives that Ethereum wants to implement on its dank sharding roadmap. And we've gone ahead and already built that, and it's the mainnet is coming out pretty soon. So that's what Avail DA stands for. Nexus is this permissionless verification hub that, as I said, employs this ZK proof aggregation technique. So imagine ZK sync proof, execution proof, and a ZK Polygon ZK EVM proof. We kind of aggregate these proofs together, combine them into a single aggregate proof, and then get them verified on the Avail DA layer itself, but also permissionlessly on the light clients. So we also embed Nexus proof verifiers on our data availability sampling light clients that can independently verify these proofs. Optionally, these proofs can also be sent to something like Ethereum for added verification guarantees. When we actually started to build out Avail, and this was during 2020, so just to give some background, Avail was actually started within Polygon. I actually previously founded Polygon, and Avail was started within Polygon back in late 2020. And that was a time when the rollup-centric roadmap was taking shape, and we realized that for the rollup-centric roadmap to come true, you really need this infrastructure that would support rollups at scale. And we looked at all the possible combinations. Of course, Celestia has been doing great work in general, but they started on this roadmap of the fraud-proof route, and we took a very alternative route. We went on the validity-proof route because we, at that time in 2020 when we began, efficient KZG polynomial commitments had already were possible. And so we went that route, and it has proved very beneficial for us. And that allows us to actually build out Avail Nexus on top, because we are able to now combine execution proofs on the rollup side with data availabilities checks. Just to complete the Avail product suite, we also have a component called Fusion Security. The problem with each new L1 blockchain bootstrapping is that there is limited cryptoeconomic security at the beginning. So, and that's the whole reason for the rollup-centric roadmap. We build, we have the rollup movement has grown so much because rollups inherit the security of the base layer. And so when you're building a base layer yourself, you need to be thinking about ways to increase the cryptoeconomic security. So of course, we rely on the native Avail token for cryptoeconomic security, but we want to go beyond. We want to kind of increase the cryptoeconomic security of the base layer sooner. And so we kind of leverage newer primitives in the space to kind of use alternative assets like ETH, BTC, and other tokens to complement or augment the cryptoeconomic security of the base layer. And so you can think of Fusion as additive cryptoeconomic security that essentially helps increase cryptoeconomic security or shared security for rollups in that sense. So, I mean, hopefully I've provided a brief overview of the entire Avail suite, but let me kind of dive into what Avail Nexus really is. And I'll just start off with the brief vision that we have in mind, like what principles are we building out from. So from a Web 2 perspective, if you kind of look at how applications work at scale, apps on the internet really work on microservices. Like there's a bunch of microservices that talk to each other and do a bunch of stuff. So for example, if you're buying a product on Amazon, and when you want to purchase it, it really makes a call to, let's say, PayPal or a Stripe, for example, and which in turn maybe also talks to a Visa microservice, for example. And so all of this is a very asynchronous sort of flow. It happens so fast with minimal latency that most users don't even know that there's a lot of complex backend engineering that is going on. And I think what we are able to now do with rollups, hopefully in the next few months and years, is that instead of this whole UX around individual chains and rollups, we are going to get into this phase where there will be more application-specific rollups, which will look more and more like microservices, where you kind of specialize in each service. For example, you specialize in payment, you specialize in payment coordination, for example, specialize in logistics, for example, and so on. And all of this is going to play out in a very asynchronous manner. And so that's the kind of end goal that we are kind of building all this infrastructure for at Avail. This is currently how most interop solutions work in practice today in Web3. So bridging assets specifically is like this sort of mint and burn mechanic. Essentially, there is some message passing mechanism that is implemented, and on top of which you implement things like asset bridging, for example, and so on. And generally, there is this, like mint and burn, lock and unlock sort of mechanic that is there. And how it plays out if we increase the number of chains is, like there is, you have to have a connection between each chain in the ecosystem. And as we know, because of the unbundling of, monolithic blockchains into this whole modular future that we are doing a 3-day summit for in general, the number of chains are increasing day by day, right? Like even today, if you see, there are probably 100 odd L2s that are in production, and that number keeps on increasing because the trend is that these roll-up stacks are commoditizing. It's now very easy to spin up these chains. The cost of spinning up a chain has become lower. And I'm just talking about general purpose chains like EVM and Stack Cairo-based VMs. The application-specific roll-ups are still to come into production, like Sovereign Labs, Stacker Labs, for example. And so the number of roll-ups is only going to increase. And so essentially, what this is going to look is akin to something like this, right? Like, I mean, it's going to be a very messy sort of a universe. And so essentially, what Nexus, if I want to simplify it down to the very basics, is this concept of Nexus where we kind of aggregate different sorts of proofs from different ecosystems, from different types of roll-ups, for example, and then aggregate it into this one single unified proof. And so this, of course, requires a bunch of tooling that is production ready today or will become more efficient in the coming months and years. But even right today, as of today, we have been able to do a prototype of taking a ZK sync proof and a ZK EVM, Polygon ZK EVM proof, and aggregate it into a single proof. And this is something that we will be releasing probably in the end of this quarter as the MVP. But the idea is generalizable. Like we build Nexus to be this generalized verification layer which can verify different proofs. Why we do this is because we kind of want to move away from this world where each chain has to verify each chain's state transition. And basically default to the possibility of each chain just verifying this one single proof, because that single proof has already verified the state of other chains in the ecosystem. We focus on ZK rollups for now because it's easier to do this orchestration on ZK rollups at the moment. But we are also working on plans to implement or integrate optimistic rollups. This we are doing with a combination of consensus ZK proofs and storage proofs, and we'll be releasing more details on this pretty soon. But essentially, like if you want to take away the idea of what Nexus is, this graphic is really what paints the picture. This is one more representation of what I want to say. So of course, there is the proof aggregation component, but there's a lot more components to it. There is a messaging layer on top of it, for example, and there's various abstractions on top, and so on. So Nexus is really this async messaging layer that we build on top of AvailDA. So this is like continuation of the initial end vision that we wanted to kind of convey, is that we are getting into this world of this multiple chains, and really where we want to go is move into this world where you can kind of do stuff on multiple chains with one single framing, for example. This is like initial graphic of what we do. We started with doing Groth 16 proof aggregation. But the current version that we are working on is based on RISC-0. We're also been looking at working with Succinct for using their SP1 prover, but the RISC-0 VM has become pretty performant, and so we are getting actually pretty good results from it. So in general, but you can look at the overall architecture as being that each rollup, for each rollup stack, we build like this adapter that kind of standardizes the information that comes from the rollup, and then inputs that into the proof aggregation system. And then that's how we arrive at the aggregated proof system. One great thing that is also enabled by the overall architecture of the Nexus is we are able to now do conditional execution. So as with real world Web 2 use cases, for example, when you're doing like this purchase on Amazon, and if the credit card payment fails, the e-commerce transaction gets rolled back and so on. And so we are also able to enable conditional execution and rollback based on timeouts because of the Nexus solution. And so this is like a high level overview of how we do this. In general, like please feel free to go to our blog, our docs for more details, or reach out to us. If you are interested in contributing to this. But this is something that I'm very bullish on. In general, enabling conditional execution across chains. Yeah, how it all fits into the Avail ecosystem in general is Avail Nexus is not an independent solution. It's not a separate layer. It's just a simple sovereign rollup built on top of Avail DA. It doesn't have any arbitrary execution. It's just for you can think of it as a coordination rollup on top of Avail DA, and it works with the Avail datability sampling guarantees. So this is a graphic of like how you can think Nexus will work out to be. So we work with all major rollup stacks to kind of build adapters into Nexus so that we can standardize the information to create this unified proof. Yeah, so I'll just quickly end by essentially see what is happening in the rollup landscape is that because Ethereum has kept their base layer pretty unopinionated, so there's been a lot of rollup stacks that have developed. It's there's a private market structure to Ethereum's ecosystem. In general, like you keep the base layer unopinionated, and so there's this bunch of L2 teams that have been working on various rollup stacks, and they're of course extremely competitive. They've come up with their own implementations, and also there's a reason also that these ecosystems are now becoming a little siloed. So each ecosystem is going and building their own interop solution. So if you think of this, Optimism has the super chain, ZK Sync has the hyperchain, Polygon has the AG layer, Starkware has its own L3 effort, Arbitrum has the Orbit effort, for example. And all of these are kind of developing in silos. And so it is really up to a neutral third party to kind of sit in between and connect all of these together. And that's what we really, what was that? I didn't see. Okay. So essentially, this is really what we are trying to do in general. So enabling the unification of Web3 by enabling modular execution layers to scale and interrupt in a secure and trust minimized way. Yeah, I think my time is up. Yep, thank you.
Any questions from the audience, maybe?
Okay, thank you very much.
Thank you, Anurag. Oh.
Yeah, I at least in some parts of the Ethereum ecosystem, there is a lot of focus on synchronous composability. Some other parts say it's overrated. You talked about microservices in the Web 2, how they are asynchronous, and also your solution will be asynchronous interoperability. So I wanted you to comment on what cannot be done without synchronous composability, or if your conditional execution solution is the way to give the users what they want, despite composability being asynchronous.
I think it's a good question. So essentially, how I think about it is trying for synchronous composability across the ecosystem is actually pretty hard, pretty expensive, and it's not required really. When you need synchronous composability, the best synchronous composability you can get is perhaps on a general purpose chain, for example. You will also have pockets of synchronicity among, let's say, with among ZK sync chains, for example, or between Starkware chains, or with Polygon chains, for example. And so you will have these pockets. You don't really need an application on each chain to talk to application on every other chain. That's not how even apps on the internet work, right? Like Amazon uses a very specific set of microservices to implement their use case. So they might need a payment use case, they might need a logistics use case, for example, and so on. So in general, how I think is there will be these pockets of synchronous composability, but largely it is it's a very asynchronous sort of universe. There will be solutions both on a synchronous and asynchronous level. When I mean asynchronous, synchronous, I also interchangeably mean high latency, low latency. It's not the same, but in general, there will also be solutions which work off, let's say, shared sequencer technology, for example, which will be based on cryptoeconomic security to do some stuff. So for example, if you want to transfer probably 100 million worth of value between two chains, it can be secured by something like EigenLayer, for example, with like some set level of cryptoeconomic security. And so we are already seeing solutions like that, for example. But like you will need to have eventual cryptographic finality. And so that's what we are optimizing for. So we work with sequencer players such as Radius, for example, and others to complement their synchronous efforts. But you can think of these as being more of, there is a fast synchronous way of doing things in a limited way, and then there's an eventual slow finality sort of way. Okay, yeah, thank you.
All right, thank you. That is all the time we have for questions, unfortunately. Next up is going to be Ismail from Celestia, going to talk about the Celestia technical roadmap. Ismail, where are you? There he is. Please give him a big hand.
Good morning. Thanks for coming so early. I have the, one second. I have the honor, I have the honor to present you the Celestia technical roadmap. And basically that's what the community has been working on in the past months or like almost years. I want to start and motivate the roadmap with 3 key problems that are still, I would say, the biggest challenges for crypto or like blockchains, at least on the base layer and in the infrastructure side. So first of all, blockchains still don't scale. If you think about it, like everyone's talking about mass adoption, if that was about to happen today, actually the current infrastructure wouldn't be ready. And the fragmentation problem that was mentioned before would even intensify and become a bigger issue. Also, these are old slides, okay. What I wanted to say is blockchains are still not verifiable by anyone. This means that a lot of teams like sacrifice some throughput for sacrifice the core principles of blockchains for some like throughput gains to quickly get some users. But like what we actually want is that everyone can like verify a chain. It's the whole purpose of why you use blockchains in the first place is you want to minimize trust assumptions. That has been discussed, I think, on ECC in length. Bridging sucks. It's like liquidity fragmentation, like is intensified through modularity even. All these rollups need to bridge between each other, and bridging sucks. It's turning into a bigger problem, both for end users as developers alike. So now I set the stage for like what I think are the key problems, or what the Celestia community thinks are the key problems that I want to attack with their technical roadmap. Damn, it's a really old slide. Okay. First of all, first goal of the Celestia community is abundant block space, and it should be verifiable by anyone. So the goal here is to have 1 gigabyte blocks. Here, the capacity that we aim for is actually like 1 gigabyte, which can host multiple Visa scale networks, right? And multiple Solana networks, many EVMs, and so on and so forth. Currently, where we stand is at 2 to 8 megabytes. If you assume the same compression numbers that Vitalik assumes in his blog post about rollups, with like 25 bytes per transaction, 2 to 8 megabytes already get you to Visa scale. It's like, I think, roughly 7,500 TPS to 30,000 TPS with 8 megabytes. And with 1 gigabyte, you get roughly 3.9 million TPS. So that's the goalpost. Another goal is trust minimization and 1 billion light nodes. We want actually everyone to be able to run a light node on their phone, in their browser, in their wallet, and so on. Our answer to the fragmentation problem that's been a hot topic is lazy bridging, or what we call lazy bridging. It's a technique that leverages ZK accounts to achieve the goal of like frictionless block space and 1 million rollups. So if you have 1 million rollups, think about the fragmentation that would exist, and we want to make it like remove that obstacle for developers and users alike and have like frictionless block space. So let's look a little bit more into what the community has been cooking. These are the 3 goals that I just mentioned. Abundant block space, 1 gigabyte blocks, trust minimization, or 1 billion light nodes, and frictionless block space, or 1 million rollups. So let's start with the frictionless block space as the fragmentation problem and developer experience is like a key issue. This consists of the following tracks. One that the community coined as modular money, which is about fragmentation issues and bridging, solving bridging, and fungibility of assets between rollups, and making the rollup experience as frictionless as possible. So, as I said, lazy bridging is leveraging so-called ZK or snark accounts on Celestia instead of enshrining a general purpose execution environment to have like a canonical bridge. It allows you to plug in any interop protocol or any proof aggregation protocol and any intents layer or intent solver where everyone wants to have like this, you have an intent on one rollup which executes in another rollup, for instance, to buy an NFT. So roughly the architecture looks like this, right? You have Celestia underneath with very minimal changes. We just add an account type, which is snark accounts or ZK accounts, some call them smart accounts. And then on top of that is a thin layer of interoperability solutions, bridging protocols, proof aggregation, interop. And it allows you to stream any asset in and out through Celestia just by connecting to Celestia. And yeah, basically have that frictionless experience that everyone wants, where you can like have an intent or anything on one rollup and it executes on the other rollup. If you want to learn more, there's a very big and very unique research community. There's a blog, not a blog post, a research forum post by Yuma from Succinct that like is the first approach on a specification for Celestia Snark accounts. There's a working group that meets regularly, is very active, I think monthly roughly. If you want to participate, this is the best place. And there's also Nashq from Celestia Labs is giving a talk about ZK accounts during Modular Summit. So what else is in the track Modular Money? The Celestia community doesn't want to wait for lazy bridging and has proposed what is called the packet forwarding middleware, which already allows you to bridge, not to bridge, but like to have IBC transactions from one chain and use Celestia as a hop. And then there's also interchain accounts, which allows you to basically manage your account from another chain. You can have another chain manage your assets on Celestia, which is important, for instance, for liquid staking protocols. Lazy bridging I already mentioned, and fee burning has been like under research since long before the Celestia mainnet actually launched. Then in the frictionless block space goal, there's another track called Blobstream. So far, it has been quite successfully deployed on Ethereum L2s and L3s, like on Arbitrum, Base, any big stack, any bigger community on Ethereum already uses it. Since it has been introduced, people realized that you can actually use this to scale any ecosystem. So for Blobstream, the goal or the work has been focused on using it to scale any ecosystem. And there have been proposals to use them for Mina ZK apps, for Bitcoin L2s and L3s, or there's a team doing research on Solana L2s as well. And I think there's a lot more coming there. There's a lot more cooking. Then there's another track called Rollup Developer Experience, or Rollup DevX. Here, two things I want to highlight is we're reworking the API currently to have like a canonical, stable V1 blob API, which allows Rollup developers to submit blobs, which will incorporate all the feedback and all the learnings we gained so far from deploying our first iteration of the blob API. If you remember, like when Celestia launched, there was no, like we were the only network that had blobs. And since then, a lot of networks emerged and a lot of users that want to submit blobs. So all the learnings will accumulate in the next API version. Another thing that's pretty cool is separating sampling from finality, also called fast blocks, slow squares, which is about achieving super fast finality without sacrificing data availability sampling. So how does that work without any pre-confirmations or anything? Like the idea is literally just produce the blocks as fast as you can. Let's say like have a block time of 2 seconds. That's what you see above. And then the erasure coding of the block, which enables data availability sampling, happens, for instance, every 10th block. And like all the blocks that were made before get erasure coded in the next step. So you get fast finality, like instant in Celestia's case, because it uses Tendermint or Commit BFT. And then you can have light nodes who sample without being slowed down by having to download all the headers in between. They just need to care about the square header and sample and get the guarantee that all the blocks that have been produced in the meantime are available. So then, additionally to that, there is, I don't think you can see it here, but there is namespace programmability, which allows developers to set predicates or conditions for the inclusion of blobs in a namespace. So it allows you to program the inclusion, but like very minimalistic. And then there's a dynamic base fee in the works, like proposed, and it's pretty straightforward. It means that the base fee matches the usage of the chain. And then let's go to the trust minimization and the 1 billion light nodes track. Here, there's basically two focus points. One is about light node security and light nodes on every device. So for light node security, the bar is already quite high because light nodes in Celestia already have similar security guarantees as full nodes in the sense that they get guarantees that the data route, the erasure-coded data route, has been encoded correctly by leveraging something called bad encoding fraud proofs. But that's not enough. We want to decrease the trust assumptions and increase the security for light nodes. One focus is block reconstruction, such that like light nodes in Celestia they already play a big role and they're like first-class citizens, but we want them to be even more important in the sense that they can be leveraged for reconstructing block data by sampling from them if there are enough of them on the network. And to know if there are enough of them on the network, we are working together with the Protocol Labs team called Probe Labs on light node observability. So to actually for the community to know how many light nodes there are on the network, that's also important if you want to increase the block size. And this will also enable, related to that, the reconstruction protocol has to be made more robust and more performant for like larger blocks. But there's more. I think that's actually even more exciting is that validity proofs are coming to light clients and partial nodes alike. So there will be validity proofs for the state, so Celestia state transition proofs. That's currently under research, probably also leveraging ZK. And there's a proposal to get rid of the data bad encoding fraud proofs to have data root validity proofs. With that, you get full, like light nodes are really on par security-wise and trust assumption-wise as full nodes, both when it comes to the blob space as well as the state on the layer 1. And to raise the bar even further, there's a technique called private sampling, which think about like a Tor network or something like this, where the sampling requests are unlinkable to a particular light node. And that's important for what's called a selective share disclosure attack, where full nodes would only give out shares to particular light nodes and wouldn't to others. So to fool the network in the sense that some think that the data is available and others actually don't get any guarantee and the data is actually withheld. Okay, and then light nodes in every device, that's the 1 billion light nodes particularly. There's a Rust light client or Rust light node already done, but that's obviously not enough. We want an in-browser and WASM light node. That's also already done. If you look around for QR codes on this Modular Summit, there you can actually run your light node in your browser. Another thing is that light nodes currently, you have to wait a bit for them to sync. And that is also in the works by the community to like mitigate that. And obviously the end goal is to have in-wallet light nodes that like everyone who's interacting with the chain in any form through a wallet doesn't have to use any centralized RPC, but can fully rely on the light node running in the browser or running in the wallet. And the last point I want to mention is the 1 gigabyte blocks, or the abundant block space. So there's two layers here. One is the consensus layer. The other is the data availability layer. On the consensus layer, we already have blobs, obviously. You can submit blobs and the erasure-coded data route. What is more interesting, as I said, for 2 to 8 megabytes, we're already there, but we have a plan, a very concrete plan to get to roughly 100 megabyte, which also already raises the bar significantly. So all these features on there, I don't want to go into detail there, but they are all about the peer-to-peer layer, the mempool, and making everything ready for like bigger blocks. So like block propagation and so on and so forth. So this is like very engineering. It's like not research heavy. Like that is, it's very clear how to get there. To get to 1 gigabyte blocks, we need to do what is called node sharding, and it's already also under research. Think about like nodes being sharded into workers internally, where they would only handle parts of the data. So that technique will get us to 1 gigabyte blocks. So on the data availability layer, we have data availability sampling. I think till today it's the only network that does this. But here the goal is about reducing resource requirements and improving efficiency. Reducing resource requirements through pruning of blob data, pruning of, or like header trimming, removing header data. And there's a more efficient data availability sampling protocol, which is essentially a rewrite of the data availability network layer. It's called SWAP, which is also will be ready for 1 gigabyte blocks. To further reduce the resource requirements for partial nodes, nodes, like storage nodes, we introduce partial nodes. There's namespace partial nodes, which allow you to download only a namespace that you care about, or that is relevant for your application or for your rollup. You can think of them as full nodes for a particular rollup. And then there's uniform partial nodes, which will allow you to uniformly shard the chain or like uniformly store data of the chain according to your resource needs. That's it. Thank you from my side. And if you want to check out the CIPs that the community has been working on for this, on the right, on the right, that's the research forum, and on the bottom here, that's the working groups. Thank you very much.
Unfortunately, no time for Q&A, but thank you, Ismail. Next up is going to be Vincenzo from L2B to talk about DA and its role for L2s. Give him a hand, please, everybody.
Hello. Coming? Okay, so today I'm going to be talking about data availability, and in particular data availability risks, and what we've been working on at L2Bit with the DA risk framework. So if you're familiar with L2Bit, you're familiar with the L2 risk rosette, made up of 5 categories, or 5 slices, if you see that as a pizza. And one of the slices is data availability. And so far, we have been marked green for layer 2s using Ethereum as data availability solutions. But we have lacked granularity on the risks and the different characteristics of other data availability layers. And so this data availability risk framework aims at expanding our previous efforts in assessing the security of different L2 architectures. And we aim to evaluate the specific security profiles of data availability providers. And so, a brief primer on data availability. You know, it's basically making block data accessible to all participants in the network, so to verify a blockchain block. And this generally applies also to layer 2s, where participants in the network needs to be able to access the data to verify the L2 state. But there's slightly difference in L2 types. When you have ZK constructions, you have validity proof. You know that the state transition is valid. But the users still need to be able to access the data to be able to reconstruct the state and maybe advance it for withdrawals. In optimistic rollups, you still need to reconstruct the state with the data, but most importantly, you need to be able to challenge an invalid state root proposal. And so what are the critical issues? They are different as well with the different types. For ZK rollups, users may be left unable to prove that ownership of the asset on the L2, and so this essentially would freeze their funds. While for optimistic constructions, this can be even worse, and you may have an invalid L2 state root being proposed, and without the transaction data necessary to recompute the state, users may be unable to prove its invalidity, and therefore user funds could be at risk of being stolen. And so looking at how these components play together with the availability layers and layer 2s, you have a sequencer, usually collecting transaction data and posting it to the DA layer. And this DA layer can be on-chain, in the case of Ethereum, called data on the execution layer, or blobs on the consensus layer, or it can be on an external DA provider, which can be of two main types. One type is a dedicated blockchain, public blockchain like Celestia or Avail, and with its own consensus mechanism, or can be on a data availability committee, which is basically a set of members getting together and preserving the data and making sure it's accessible to users upon demand. And if the data is on-chain, then Ethereum is aware that the data has been posted, a data commitment is posted together with the data. But if the rollup is using an external data availability layer, then you need a data attestation, and this data attestation needs to be posted to a DA bridge and act as an oracle on Ethereum for the DA layer. And so if you think about securing data availability, you have different guarantees that are needed, and here I group them into three categories. You have a data publishing guarantee. That basically, you need to make sure that the data was published and was accessible during the defined period. And this is different than a long-term storage of the data. But in this case, you just need the rollup to be aware of the data for the defined period on the DA layer. And then you need a data integrity guarantee, meaning that if any transformation is applied to the data, the users need to be able to recollect the original data that was posted to the DA layer. And then to complete, you need a data attestation. So you need a proof to Ethereum that at any point in time, the data was stored and all the data was included. And so a key takeaway of securing data availability is that for Ethereum, DA layer is secure only if there is also a DA bridge that provides this proof. So the DA layer and the DA bridge needs to work together to make sure that data availability is secured. So focusing on the DA layer, you have some issues in terms of what can go wrong with posting to the DA layer. And here I divided into two. You have the issue of unavailable data. So you can have the case that data cannot enter the ledger, and so data commitment cannot be produced. And this can be the case if a vast majority of nodes goes offline, or there is a censorship attack on the DA layer, and this is a liveness issue. Or you may have the data that enters the ledger, and then at some point in time it disappears. And this would be the case, for example, for a chain reorg. and the data being unavailable also on the non-canonical fork. And this would be a safety issue. And the other issue is the withheld data. So data is attested, but is not served. And this is known as a data withholding attack. And so we aimed at capturing these issues and addressing them through the economic security risk dimension of the DRX framework. So this is the first category of the framework. And it aims at measuring the level of trust that we can place in the majority consensus of the DA layer. And it's marked as green if the total slashable stake is quantifiable on chain and is more than the total value secured by the DA layer. It will be marked as yellow if this is not the case, so the total slashable funds are less than the total value secured. So for example, you may have 10 billion total value secured and only 1 billion in slashable assets, then the validators may be incentivized to be malicious or bribed to be malicious by someone else. And this will be marked as yellow. And in this dimension, we aim at capturing not only DA layers with their own consensus mechanism, but also data availability committees. And so in the yellow category, we also include committees that are publicly verifiable on chain, meaning like the members are known, that there is a reputational risk for the members, and they could lose their reputation if they behave maliciously. But if they are not known, and so this could be the case for an unknown committee with not known members, then this would be the worst case scenario, and we marked as red in this category. So we looked at liveness and safety issues, but what about protecting against a data withholding attack? And usually you have two ways. You can have every node download all the data, but this is, of course, not scalable, and you would need to increase node requirements. Or another approach is to use a data sampling algorithm, like data availability sampling, that offer a way to scale the data throughput while maintaining verifiability. And so just briefly, data availability sampling, you have erasure coding applied, which splits the data into smaller chunks and adds some redundancy, so that the original data can be recovered from a subset of the chunks. But here it's important that there needs to be enough verifiers, or light clients or light nodes, to sample enough chunks to reconstruct the original data blob. And so this fraud detection mechanism is the second category of the framework, and aims at measuring how effectively users can protect themselves against malicious majority of committee members. And it would be marked as green if invalid data can be detected on the DA layer through a sound data availability sampling construction. And it would be marked as yellow if, for example, there is a data availability sampling construction, but there aren't enough light nodes to sample enough chunks, so the blob cannot reconstruct it. And if there isn't any fraud detection mechanism at all, then it will be marked as red. And so we looked at the first part of securing the DA layer, and now we can look at securing the DA bridge. And here you can group the issues into two. You have attestation security. So basically, how robust is the bridge verification of data commitment? And does it introduce any additional trust assumption? And another issue that is very common to smart contracts and L2s as well is upgradability. So we need the criteria for an exit window and making sure that if there is any unwanted upgrade for the users, that they're able to exit the system. And so the third category is the attestation security. That basically verifies that the economic security on the DA layer is mapped to that attestation on the DA bridge. And this will include verifying signatures, verifying the threshold, and verifying the validator set that is tracked properly on chain. And in the case of the ZK proof would have to include these, all these checks, the correctness of the signatures, the threshold. And if the system wants to be marked as green, you would have, you wouldn't need to allow for signature equivocation. So you wouldn't, you cannot sign something on the layer and something else as an attestation to the DA bridge. If that happens, we marked as yellow. And this could also be the case for constructions where there's a different set of signers on the DA layer and the DA bridge. Usually it's a smaller set of signers. While if there is no bridge at all, then of course it will be red. And the fourth one is the exit window, which basically examines the possibility of users to exit the system in case of an unwanted upgrade. And this follows the criteria that we set in the stages framework for L2s. So you would have green for an immutable bridge or an upgrade delay of 30 days or more, and yellow for above 7 days, which you can bring to 0 if you have a security council in place, as defined in the stages framework as well. And red if the upgrade delay is below 7 days and there is no security council. And so we get to the last one, which is additional trust assumptions of external DA layers to enshrine solutions on Ethereum. And here, basically, Ethereum rollups need to trust only full nodes on Ethereum, while if you're using an external DA layer, you introduce additional trust assumptions which come from the need for a DA attestation on the DA bridge. And there is, this graph is actually from Luca Donno's scalability.guide website, which basically goes through an example of a rollup using Ethereum not from a point of view of enshrined with so-called data or blobs, but uses it as if it was external DA provider. And so you will post data to Ethereum and then data commitments to a DA bridge on Ethereum. And I think it's a good example to show how, even if you're, in this case, when you're using a DA bridge on Ethereum or basically the same DA layer in two different ways, if you're using Ethereum as an external layer, so you're using data attestation signed by validators, you would need to follow the data commitments on the DA bridge. And in case of data withholding attack, while the full nodes on Ethereum for our enshrined rollup would be able to discard the invalid data, and so make sure that the data is only available if it's present on the honest chain. In this case, you would need to trust the majority of validators to make it to sign an attestation and to make it available to you. So we aim at capturing this difference in the last category, which is accessibility. So it measures the ease with which data can be accessed directly from Ethereum. And so it will be marked as green for enshrined solutions in the Ethereum protocol and yellow for not enshrined. And so we're aiming to finalize this risk framework, and we have had some great suggestions in the L2Bit forum. So if you want to provide feedback or if you have some comments, some suggestions, you can go to the forum at gov.l2bit.com and post there. And that's it. If you have any questions, thank you.
Anybody has any questions?
Have you tried to
your solution? Sorry. Have you tried to evaluate existing frameworks with your evaluation method?
Yeah, so we aim at evaluating all the DA layers that are live right now. So Celestia will be one of them, Ethereum, of course, and also as well the data availability committees that are used by L2s these days.
Any other questions? I think in the back there.
Do the security assumptions change based off of a sovereign rollup or a smart contract rollup?
Yeah, so this framework is applied to Ethereum and L2s using Ethereum. So some of them would definitely change if you're looking from the point of view of a sovereign rollup. And we do specify in some of the dimensions that this will be the case. So if you're looking at the scoring in the system, it would be applied to L2s using Ethereum, so from the point of view of Ethereum only.
Anybody has any other questions? One question in the front.
Yeah. So do you need all greens to have a green slice? And for accessibility green, you need an enshrined DA bridge, like enshrined in the protocol, a bridge to an external DA solution. That's how it works.
So that category would be green for enshrined solutions into Ethereum. So in this case, it would be so far blobs on Ethereum or cold data on Ethereum, while external systems would be marked as yellow, which doesn't mean that are insecure, it just means that they add an additional trust assumption. So in the future, probably Ethereum would aim to have all green, but if you are using an external DA solution, you would have yellow in that dimension if it's not enshrined.
So it cannot be yellow, full yellow, the DA solution for DA.
Full yellow?
Full green.
It could be. Okay. Ethereum could be.
Ethereum itself, okay.
Yeah.
Maybe one final question, if there is one. If not, then thank you again, Vincenzo.
Great.
Give
Thank
another big hand. Next up is going to be a panel with Prabal from Avail and Mustafa from Celestia, moderated by Bartek from L2B.
Where's Nima? Do we have Nima? Do we have Nima? Nima can't make it, so all right, so I'm Matt. I can do it, yeah. Okay.
Testing.
Mind sitting here?
No, I don't mind at all.
If you move just one chair, it would be great. Matt, I'm gonna have you in the middle, if you don't mind.
I love how I'm a surprise appearance.
No, you just go. I think so.
Yeah.
Hello.
I do not.
No, he needs one mic.
Okay. Hello, everybody. I'm Bartek from L2Beat, and every year I have a pleasure of hosting this amazing panel on DA on this summit. So we met last year. We're gonna discuss DA this year. Hopefully next year, it's gonna be equally fun. So I kind of like did a bit of a reshuffling here. Maybe wasn't smart, but we're gonna see. So I put Toggle right next to me because he's supposed to represent Ethereum. I have no idea why, but there's like a tradition on this conference. Last year he did the same, and that's surprising because he's been sometimes I don't know. I mean, let's see what he's gonna say about Ethereum DA, right? But I'm like thinking that he might represent Ethereum here. And then on the other side, we've got two projects. We've got Mustafa from Celestia, and we've got Prabal from Avail. And again, from the Ethereum point of view, I kind of see these guys as being like an external DA provider trying to kill Ethereum's DA roadmap or whatever. So maybe, they like on the opposite side with Toggle. Again, we'll see. And in the middle, we've got Matt representing EigenDA. And I have no idea where EigenDA is, so I just put him in the middle. So we're going to find out, right? So this is a setup, and I put myself right next to Toggle because my background is Ethereum. So I'm really glad that the module people keep inviting me, even though I tend to like take Ethereum's point of view. But we're gonna see, right? So my first question, I guess, to the panel is that last year when we discussed DA. Like every single project was either a white paper or a PowerPoint or maybe a testnet. My main question from last year was like, where do you think the space is gonna be in a year time? And we got some interesting answers. Like, I do remember we're gonna see thousands of rollups being in the production or so, right? And I got really scared at that time because at that to beat, we are trying to evaluate all of them, but so far. Thankfully, we only have like less than 100. But anyway, I want to ask you guys, like, do you like, or how do you see the space 1 year after? I mean, is it where you hoped it to be, right? So maybe I'll start with, the left side of the panel.
Yeah, I think I still hope that your job gets tougher. Tougher because not only we see only Ethereum clones of EVM rollups, but also application-specific ones. So when I say thousands of rollups, some of the types of rollups are not, defined in the rollup as a rollup construct in the familiar world. We have seen, various numbers flowing around, and some of them you might also argue that they are not even a rollup, right? And so how you define a rollup also plays a role. But on the other hand, that's where we would like to be. We would like to be in a place where there is lots of application-specific rollups, and then that's where the scalability should appear.
And in terms of product, the Avail, I mean, last year you were at the testnet. Where are you today?
We are still at the testnet, and we are going to launch mainnet very soon. Yeah.
Mustafa?
We will see 1,000 rollups. We're going to see 10,000 rollups, even maybe 10,000 rollups. I don't think I ever said it's going to be happening in a year, but it will happen. For the next talk, the Modular State of the Union, I actually did a comparison to how many rollups we had last year to this year. And we have an insane amount more of application-specific rollups this year than last year. Last year was something like 10. This year we have something like 40. I did actually went on the archive Wayback Machine to look at the L2B website a year ago and now, and there are a lot more rollups. And the main difference is what's happened is that this year, there were 0 blockchains that supported data availability blobs, 0. This year, there's 3, EIP 4844, Celestia, EigenDA. And because now we have more blob space, we're seeing a huge influx of developers deploying rollups using rollup as a service providers like Conduit, Caldera, Gelato, and the likes. And there's literally hundreds of rollups in the pipeline with those rollup as a service providers because they make it so easy to deploy a rollup. So whether you like it or not, it will happen.
Matt, like I said, I mean, I put you in the middle because I don't know. I mean, are you guys building an external DA solutions? Are you aligned with Ethereum? Are you like part of the Ethereum roadmap? I mean, where are you with your solution? And are you live as a product?
We are live.
What are the rollups that are using EigenDA?
And we are currently doing 10 megabytes per second on mainnet.
For something.
So, appreciate it. All right, you can hear me now? Yes. To confirm, we are live. We launched live Q2 mainnet, and we're doing 10 megabytes per second. And EigenDA is a data availability layer. It's not a blockchain. The focus is for data availability. And yeah, current rollups that are using, whether they are at testnet, moving to mainnet soon, might be like layer N, a team like Celo. We've got a variety of rollups, but also non-rollup use cases that are of interest. Essentially, like data availability is useful for things that you want to make publicly verifiable. And we see that there's a massive space, obviously, in the rollup space and the abstractions that have led from like things like rollups as a service. And we expect the demand for rollups to increase and hopefully continue to accelerate on that front. So look forward to it. And
in terms of alignment, do you consider yourself to be like a competition to Avail, Celestia, or are you trying to like, find the middle ground between, I don't know, who is your primary user? Are you competing with Ethereum or you're aligned with Ethereum? I mean, how do you like position yourself?
I wouldn't say that, like, I think as far as on the alignment side of things, I mean, I guess, we're secured, inspired by dank sharding. So what that means is horizontally scaling. And so for us, decentralization means that we can get increased throughput and increased scaling. And on that front, we're secured by Ethereum, so over 3 million Ethereum today, as well as like Eigen token, right? So additional quorums. So I would view them as it's an option that applications that within the Ethereum space, it can make a lot of sense working within, but also non-Ethereum like rollups at use cases. If you have anything else, yeah.
Togrul, I see you're itching for, some hot take here.
So firstly, I would say Ethereum is actually secured by Ethereum, unlike everybody else here. And secondly, I think I hope that we don't get 10,000 rollups for your sake as well as for everybody else's sake. I think the meta of dying L1s becoming L2s is dying a bit, so they're going to become dying L2s soon. There are still going to be quite a few general purpose rollups, but I think the future is shifting more towards app-specific rollups. Again, I'm not sure how many you actually need, how many use cases need their own block space, but there are certain reasons why you would do that, and there are even L2s popping up on Solana now. So I think the future is more correlated to app-specific rollups rather than people just launching 27 other OP stack chains that have basically nothing different to every other OP stack chain.
So it seems to me that we are all betting on the future need in a way for abundant block space. At least some of us are. And today I've checked that the price of posting data to Ethereum is actually surprisingly cheaper than posting to Celestia. I'm not really sure, like it fluctuates a lot. Sometimes it can be quite high and sometimes it's just like next to zero. So I can definitely understand some people saying that, we need to focus more on apps and not the infrastructure, right? And you probably must have heard, these types of comments. we're building a lot of potential blob space. Are we like hoping that that's going to enable new use cases, or it's just too much at the moment, you know? And we should, like, as a community, say, hey, you know, with that much blob space, maybe we should like focus more on applications. I know that you, Mustafa, you kind of like, you know, had some take on that recently on Twitter. So what do you think? I mean, do we actually need that much blob space, considering, especially from the Ethereum point of view, that Ethereum very soon is gonna introduce peer DAS, right? That's gonna like increase quite substantially the amount of blob space available on Ethereum, and like Ethereum is moving really, really fast, you know, in this direction, right? And at the same time, you know, I've just seen that Celestia has promised, you know, amazing amount of blob space, same with EigenDA. So like it's a lot, right? And it seems like we're building for some future world, but you know, is that future world's gonna like come soon, or?
Yeah, so first of all, it's not true that Ethereum blob space is cheaper than Celestia right now. If you look at the data, it's the other way around. But in terms of block space, the way I look at it is that I look at it in terms of induced demand. Now, as I said on Twitter, I think what you're referring to, I asked the question is, why is it that 16 years later, since the creation of the Bitcoin white paper, the original use case of crypto, which is payments, we still haven't achieved wide-scale adoption of that. Like, Venmo is newer than Bitcoin, but Venmo has succeeded more than Bitcoin, at least in the US market, at payments. And I think a lot of that does have to do with the supply of block space, because if you look at what happened in the early 2010s in the Bitcoin ecosystem, for example, there was this whole movement where like Bitcoin never had this narrative about being a store of value. The original narrative was that everyone's going to be using Bitcoin to pay for coffees and for payments. And then what happened is that the Bitcoin community convinced a whole bunch of people to start accepting Bitcoin for payments. Even Microsoft accepted Bitcoin payments for things like Xbox games. And then what happened is around 2013, 2014, the transaction fee skyrocketed, and retailers actually stopped supporting Bitcoin for payments because there simply wasn't enough supply. So I think a lot of it does have to do with the fact that if we keep building infrastructure that simply falls over after 2 years when there's a bunch of demand, that does fundamentally limit how much adoption you're going to get. Like even Solana claimed to do 50k TPS, can actually do only 2k TPS, and since it's had a lot of demand, the user experience even for simple things like payments have been terrible.
So how does it that the fee market, you know, on Celestia compares with Ethereum? I said that, you know, right now Ethereum is cheaper because, you know, there's the data that I got in the morning, but, you know, again, it fluctuates, right? So it may be temporary, and like a few weeks ago it was super expensive because something happened, you know, and you know, like
ZK Sync airdrop.
What was that?
ZK Sync airdrop happened, so everyone was like spamming.
So we all know that, you know, the price can like fluctuates. How is price set up on Celestia compared to Ethereum? And same question for Matt. I'm not like familiar with how prices are actually set on EigenDA, and you know, who decides on the prices on EigenDA?
Yeah, so in Celestia, it's just a standard fee market, kind of similar to Ethereum. So like right now, both on Ethereum and Celestia, blob space is basically practically free. The only difference right now is that in Ethereum, there's a much higher overhead cost to kind of like having a blob carrying transaction. So that's kind of what makes it much more expensive right now than Celestia. But other than that, the per byte cost of the block space is free. It's just that the overhead costs of submitting a transaction is higher on Ethereum.
Yeah, and on Avail also, the transaction fee mechanism is such that there is, of course, a standard base fee. But on top of that, depending on the amount of data that you want to publish, as well as the congestion that is there over a period of time, the prices are going to fluctuate. So I think it's standard fee market practices.
Yeah, I guess, and a brief mention on the Ethereum blob space. We do expect that like the costs are going to go down, right? As this roadmap is continued to be implemented, we've seen that. We also have seen spikes of volatility, right? In fact, where blobs became more expensive than call data, right? So being able to have some predictable prices or expected costs is potentially useful on that front. So how EigenDA is structured is based off of the amount of data throughput that you need, right? So there are various use cases or various requirements, maybe for something that is posting proofs, might require a higher data throughput than a smaller, just like transaction sort of like commitment hash. So it's based on the amount of data you want to post, but also let's say like market conditions. And like some minimal exposure to that. But we also offer the ability for like reservation of bandwidth. So what I mean by that is being able to guarantee certain bandwidth for a set price for a certain duration of time over a certain period of time. So you can have more expected costs essentially on data availability.
Talking not just that you represent Ethereum, but you're also working for Scroll. Scroll is a rollup, right? Pays a lot of, I guess, for data on Ethereum. Like why?
When we initially set up to build it, we decided that we want to minimize dependencies as much as possible, third-party dependencies. So, and especially I think for a general purpose rollup, it's very important that you don't introduce any unnecessary dependencies, even if it comes at a trade-off of having a higher cost, because if it's an app-specific rollup, let's say, and it's doing gaming or something like that, the failure of that DA provider is not as much of a big deal as a rollup that hosts potentially billions of dollars. We currently have around $1 billion bridged into Scroll. So imagine if, for some reason, the DA provider, the third-party DA provider, stops working at some point. That'll be catastrophic. And so we made a conscious choice to trade off a bit of transaction costs, like make them higher, but make the protocol itself more secure from the perspective of like being as trust minimized as possible, both in terms of correctness assumptions and liveness assumptions.
So I wanted to touch, a little bit more on that point. There was a great question from the audience in the previous talk when we discussed enshrined versus non-enshrined DA, right? Like an external DA versus enshrined DA from the point of view of Ethereum. And just to set the context, my personal understanding of what would be the enshrined DA is if you are running a full node of Ethereum, then with enshrined DA, your full node would essentially be able to check if the data was made available, right? And if there was a data withholding attack, the data wasn't available, your full node would simply see that block as being invalid. So even if the majority of the Ethereum validators would confirm such a block, your full node would reject such a block, and that would likely result in some kind of a user-activated fork, and that is considered to be like super secure. On the other hand, as Sriram from EigenDA once said, the external DA looks like data availability committee to Ethereum in the sense that the Ethereum cannot do data availability sampling for external DA solutions, right? So you need some kind of an attestation, like for example, the Blobstream bridge from Celestia. So essentially, Celestia validators are attesting that the data was available, so you are not protected from the majority attack. You will be protected if you are a sovereign rollup. So, so my question now is, if there is enough blob space on Ethereum in the future, right, and you are an Ethereum rollup, then arguably using Ethereum DA is more secure. If you are a sovereign rollup, then arguably using Celestia or Avail or EigenDA, I'm not sure, is better because you can yourself detect the data wasn't available and that the network is under attack. Would that be a fair kind of like statement moving towards the future. Would it be fair, in other way, to say that if there is enough blob space for rollups on Ethereum, then it's maybe from the security point of view better for them to actually use Ethereum DA, or is there something compelling other than price to use external DA, given that the security is, like slightly is different, right? There's a different security assumption. How do you guys think about this problem?
So essentially, I think I would love to have the world that black and white as you painted, but to be honest, every one of the rollup implementations have nuances when it comes to using external DA or even Ethereum DA. For example, what can happen if the sequencer doesn't publish on an external DA? Is that a trusted sequencer, which means that you always trust that the sequencer has published it? Or are there validators inside that rollup system which attest to that fact? Irrespective of what the external DA committee or the validator said, they attest or not. That is not, what is the source of truth in the settlement contract? That has to be determined first. And this is a conversation that we have been having with various rollup teams right now. And each one of them has made different trade-offs. Some have made trade-offs that you optimistically accept that the transaction has been published, and you just move forward. You move forward because you just rely that it will do its job, and Ethereum doesn't matter for Ethereum. You just trust the external committee, right? And we have seen production-grade rollups with huge amounts of TVL doing that. On the other hand, there has been designs in which we have proposed, and we have been rejected, where we wanted to have not only verification by the attestation bridge, but also verification by the validator set, because the rollup cannot handle invalid batches. It always assumes, there are some rollup constructs which assumes that all published batches are correct, irrespective whether the execution attestation has been correct or not. And hence, depending on what kind of rollup you're talking about, what is the implementation there, what are the security assumptions, what are the participants that are there, who are the watchtowers, are there a need for watchtowers, is it a ZK verified, is it not, are we talking about liveness, are we talking about safety, is it centralized sequencer, is it multiple provers? It all depends on those kind of design choices. On the other hand, it's not just about the cost. The cost is, of course, one of the major factors, but it's also about what kind of orientation do you want for the application. For example, you want light client verifiability for that application. The application users want to verify the execution and the data availability. On Ethereum today, at least, you cannot do it because there is no data bridge sampling. With dank sharding, it will come. So there are also product requirements which guide this, and not just cost. So again, it's very nuanced, but happy to get more.
But just to add here, a light client that only does data availability sampling can still follow an invalid head, because if you don't verify the execution, then the execution can be invalid, and all the full nodes will drop that block, but your light client will just assume that block is correct. So even if Ethereum doesn't have DAS at the moment, no other chain that is live right now has a light client that verifies both DAS and execution, which means that you're, to a certain degree, still trusting the multi-sig of the consensus.
But you're now changing the premise. We are talking about data availability part only, and we are talking about blockchains which doesn't support too much execution, right?
But the thing is...
Hold on, I mean, your statement is also true when Ethereum supports DASing, until Ethereum supports ZK proofs of the execution environment.
Oh, but I'm not disagreeing with that. I'm not saying that Ethereum is going to have it. I'm just saying that no other chain has it either. Because even if you verify DAS right now on Celestia, for example, it can still be an invalid block. So verifying just data availability is not sufficient.
Yeah, but the point is that Celestia has minimal state, so you can run a partial node that does execute all the state, but does the sampling, which is lighter than a standard full node for Ethereum or Bitcoin, for example.
But Mustafa, I mean, in general, would you kind of agree with the statement that external DAs are more I don't know, useful, I guess, for sovereign rollups rather than the Ethereum rollups going forward in the future, assuming that there's an abundance of a cheap blob space on Ethereum?
Well, that's a loaded question. First of all, what do you mean by useful? And secondly, what do you mean by sovereign? Those are very controversial words in themselves, right? So,
like sovereign meaning that they define their own ordering,
sure.
or like they don't follow Ethereum. If Ethereum reorgs, they may like go their own way and whatnot, right? They don't like follow the Ethereum consensus.
Sure. I mean, look, the way I would put it is the following. I would say 2 points. First of all, the idea is that Celestia scales any ecosystem. So, yes, it can scale Ethereum L2s or Validiums or Optimium chains. It can also scale Bitcoin L2s, but it can also scale Mina L2s, and someone is even building a Celestia DA bridge to Solana so that you can verify DA proofs on Solana. So, and then, of course, you have sovereign rollups or native. Let's ignore the word sovereign now, because that's a very loaded word. I don't think anyone on this panel even agrees what it means. Or let's call them native Celestia rollups. Yes, you can use them for all of those things, and that's the first point I would say. And it does make sense for all those use cases. And the second point, I think, look, fundamentally, the fundamental fact is that yes, everyone on this panel agrees that if you're an Ethereum rollup or Ethereum L2, inheriting Ethereum security and posting a DA on Ethereum is the most secure solution if you need that level of security. But the fundamental reality is that Ethereum, for good reason, needs to be very conservative with its technological roadmap. It can't jump straight away to 16 megabyte blocks. Right now, it's got 375 kilobyte blob space per block. Even after PeerDAS, it's not going to jump to 16 megabytes. The current discussion is that it will jump to 1 megabyte, and that's still only a few hundred TPS. So the alternative DA layers, they provide a way to have like 10x, 100x, 1000x as data throughput, while still giving you the ability to settle to Ethereum. And yes, there is a security trade-off, and everyone acknowledges that.
Anything to add, Matt, from like your camp, or you kind of like agree mostly, with this characterization that we've just put forward?
Yeah, sure. I can maybe give it a little bit more color, and I agree. The use of data availability depends on your use case. So depending on what you need to prioritize, then it makes maybe a little bit more sense. If you need, depending on your needs, essentially, that is there are cost prohibitive, with DA maybe on the L1 itself. But we, again, expect that to decrease. So there's not just cost that maybe is boiled into decisions for rollups or other use cases. We expect that AVSs will be a consumer of DA in the future. You need to be able to publicly verify any of the data there. So the bottleneck isn't necessarily on even the execution of these state transition functions anymore, but it begins to also place a lot of pressure on the amount of data that you can post, the throughput that you have. And we've seen that as far as teams that are pushing extremely aggressive transactions per second, like a mega ETH, right? Where that is their focus of maximizing the amount of transactions. And then DA becomes their bottleneck. And high throughput is then a key requirement for them, right? Not just cost, but also high throughput, as well as underlying security. And that for EigenDA is inherited through Ethereum. So that, I would say that there are different designs require different trade-offs, and depending on your use case, I think that it's a complete evaluation. It's not like a one-size-fits-all.
Yeah, you wanted to add something?
No, I was just going to say that paradoxically, from our perspective, the biggest bottleneck on Ethereum right now is execution cost rather than DA or anything else.
At the moment, right?
Yes. So, for example, we are currently the fastest L2 in terms of finality, but the trade-off there is we pay a lot for settling quite frequently, and basically in our next upgrade we'll add batching of aggregation of proofs for a lot of batches, and basically delay the finality further than what it is now, purely because the execution of Ethereum is prohibitive, and it's going to become even more prohibitive once rollups becomes too decentralized, because there are certain things and certain overheads that you need to do on chain, and then to add to that, once you add multi-provers and multi-verifiers, computation actually becomes super expensive on Ethereum. And so unless you have like thousands of TPS of demand, there's no way to amortize it properly. And so I think what I'm trying to put pressure on Ethereum, and like a lot of other builders of L2s are trying to put pressure on Ethereum to actually increase the gas capacity, because at the moment, decentralizing and also improving the security of L2s is actually quite cost prohibitive.
Okay, now I kind of wanted to switch gears a little bit, you know, and maybe get more technical, so that certain concepts are more clear for the audience, for myself as well. Quite recently, a newish, I think, term has been thrown around in the discussions around DA. The old term was data availability sampling, DAS. You know, like people say DAS, you know, you should probably know what is data availability sampling and what is its role. The newer term is VID. I had to check it, you know, a few weeks ago. I think it stands for verifiable information dispersal. And I believe that this is a technique used by EigenDA to disperse data amongst, you know, different validators. Today I've heard that Celestia wants to do sharding to achieve, you know, a bigger block space. On the other hand, dunk sharding also in the future will not require full nodes to download the full blob, just a portion of it, which is, by the way, the case, I believe, in Celestia right now, and indeed the current Ethereum for 844. I'm not really sure about Avail, frankly. Can you, like, guys, sort of set the stage for these concepts? Are we talking about completely different things, or, you know, or these are like similar techniques in a way? And yeah, what is this, you know, like VID, the verifiable information dispersal? Maybe I'll start with Matt, and then let me hear from Mustafa if this sharding is the same thing or not.
Sure. That is, I mean, verifiable like information dispersal. Like, personally, I think that's less of maybe like that is an aspect of the architecture, but less of maybe directly related to like data availability sampling. Like that is more so on to give a little bit of context as far as how it works. And when I mentioned it's like inspired by dank sharding, essentially you have a blob, you have amount of data that's sent, it's chunked into blobs and dispersed amongst a network of operators. These operators are AVS operators in the case of EigenDA, and they secure like proportional amounts that they have staked. Essentially, you can only secure the amount of data that you could possibly safely and securely do so. So the dispersal is this sort of portion that goes from dispersing to those operators and ensuring that it is dispersed. But the data availability sampling is a separate aspect, and ensuring that once, you know, it's a different problem to have it dispersed than to make sure that it is available. And that's, so there's like two different sides, right? Is being able to ensure that that data is then made available after the fact and not necessarily just dispersed you know, forever. So if that distinguishes,
that sounds about right. I think, yes, I think you also talk about something called proof of retrievability, which is a very old concept from like the early 2000s that is very similar to data availability sampling. It's just that the main difference is that proof of retrievability and verifiable information dispersal proves to you that the information has been dispersed or to some servers, or can be retrieved from some servers, but it doesn't actually prove that's actually being published to the internet, such that anyone can actually download it. But to answer your question about the sharding, yeah, I mean, you brought up the point that, like with like, for example, like dank sharding roadmap, the idea is that consensus nodes or block builders or validators, they don't have to download the full block to verify it. So it is the case that in Celestia right now, you do have to download the full block if you're a consensus participating node to build on top of it. And the reason for that is because Celestia relies on bad encoding fraud proofs, whereas danksharding uses KZGs to prove the correctness of the erasure code. And because we use bad encoding fraud proofs, there's this like 5-minute or 10-minute fraud challenge period. So obviously validators cannot wait that long to build on the next block. They only have 10 seconds, right? So I would say two things to that. Like, first of all, I'm skeptical of the scalability advantages of making it that validators don't have to download the full block to build on top of it. And the reason for that is because that only makes sense if you assume a perfectly distributed staking setup where like they have 1,000 different validators and they all own 0.1% of the stake each, such that they're perfectly uniform. But what happens in practice, and if you look at Ethereum today, there's 3 validators or a small number of validators that control 2/3 of the stake or most of the stake. And so what happens in practice is that most validators that actually control most of the stake have to download all of the block data anyway. Where this is advantage, where this does have provide advantage is for like home stakers that have very little stake. The home stakers don't have to download the whole block. But I'm very skeptical in the first place of optimizing for thousands of home stakers instead of optimizing for a Nakamoto coefficient that makes sense. For example, like in Celestia, we have 100 validators, and then having fast, immediate finality, we have 10-second finality, for example, instead of optimizing for thousands of validators when Nakamoto coefficient is very small anyway, and having 5-minute, much lower finality. But the second point I would mention is that we do actually also, as you saw in Ismail's roadmap talk, we do actually also want to and have plans to ZK prove the correctness of the erasure code. But our current thinking is that we want to skip straight to seeing if we can Stark prove the erasure code rather than using KZGs to do so.
But would you be equally skeptical of the current EigenDA architecture?
Yeah, I'm also skeptical of that for the same reason. I know that EigenDA claims that you can scale the number of nodes, but again, that's only the case if you assume a perfectly uniform number of distribution of stake across 1,000 nodes, which we've never seen in practice.
Sure. EigenDA doesn't have consensus on top, so there is no like concept of consensus within EigenDA. It is a data availability layer, so in the fact of this data is dispersed to operators that is made available so that full nodes, if required, can retrieve the data to ensure that the state transitions are made. So I guess that's like one point just of clarification, that there's not additional consensus for full
we're talking about the data availability nodes. We're talking about like you're dispersing the data to 1,000 nodes, and the more nodes you have, the more data you have.
Yeah, and the operators of a data availability layer aren't also ensuring the correct state transition functions. Those are on the services that would require use, right? So, correct me if I'm wrong, but the rollups that are using this data availability layer would retrieve that data, and if required, would also download that to a full block, full node rather, and ensure those state transitions, let's say, were made correct. And there's different,
no, but the argument that I'm making, or that Bartek is asking, is that the scaling story for EigenDA is that you can scale with number of nodes, right? So the more nodes you add to the network, the more operators, the more like validators in this AVS, in this EigenDA AVS, the more data throughput you have. But what I'm saying is that that only is true if you assume, like if you're saying you have 10 megabytes per second with 100 validators, then you have a gigabyte per second with 1,000. I'm saying that's only true if you make the assumption that exactly. It's only true if you're making the assumption that the stake is equally distributed to the 1,000 validators. When in practice, what will happen is 10 validators. I think it is the case right now. 5 validators in the EigenDA AVS control most of 2/3 of the stake.
Plus, all of this, plus there are many more nuances which we are missing. Like the disburser right now is centralized and it is able to send 10 megabytes per second, as they claim. And with 1 Gbps connections and such, it's yet to be seen, like with thousands of operators, what is the requirements for this disburser first. Then there are other things also, like we are talking about two very different kinds of systems here. One is consensus-driven, and the other is committee-driven. And if you take a look at the protocol level guarantees that both of them provide, they are different. And not only from the protocol level, the protocol participants, but from the user level, the requirements are very different. For the data availability sampling, it's about the user level guarantees and not the protocol participant guarantees in that sense. Because the data availability sampling says is that I do not want to rely on whoever that is. But the verifiable information dispersal, that is about how does the information get dispersed within the protocol participants. And they are kind of different things. In terms of, like, I think a lot of different concepts were covered, but in terms of stake distribution, there is problems with that because the incentives are not aligned correctly. In my worldview, I think like the delegated proof of stake and the concentration of stake are kind of related, right? Because if the incentives are not there to delegate in the least staker, then it's there to be seen what is happening, right? And that's why at Avail we are trying to do nominated proof of stake. We are trying to do fragment in a bid to make things much more decentralized, the Nakamoto coefficient to be much higher. And yeah, I mean, that's why there are many different topics. Each one of them should be discussed separately, and only then we would be able to talk about the differences and the deltas.
So before we run out of time, there's just one more concept that I wanted to clarify, which I think is enormously misunderstood, and that is a proof of custody. It was like introduced a while ago by I don't know who, but Dankrat defined it as a technique to prevent what he called lazy validators. Validators that wouldn't download the full block because it costs time and money, but they would just attest, right? So that would be like a crypto economic or a cryptographic technique to make sure that we don't deal with lazy validators. But this is certainly not any type of like guarantee that the data is being stored or held by the validator or whatever, right? So it was just a technique that the data was actually downloaded by the validator before a testing. And then EigenDA kind of used this term, I think, for something else, if I'm not mistaken, at least a year ago. Now it seems like, this concept maybe is forgotten. I'm not really sure. I just wanted to sort of like, clarify, like, what is the current thinking in EigenDA team about this, concept of proof of custody, which was like heavily marketed a year ago, and now I'm not even sure if that's the thing. So have you guys like changed your mind about this, or like what's the story here?
Are you speaking to the fact of like operators being able to like attest to the fact that they have data, or what is?
Yeah, I mean, that was the concept that, like EigenDA was like pushing, and slashing condition was also like defined on that in one of the test nets, but I think it's not on the mainnet. So I'm kind of a little bit confused, and I just, wanted to get from the source, like, what's the story about the proof of custody here? And also the question to other guys, if this is this something actually like important in your opinion?
Sure. Yeah, I'd say, I mean, it might like still like be a piece of like the along from like dispersal to like data availability sampling, there's like still a requirement to be able to have attestations from those operators to ensure that it has the data. But I wouldn't say that it like the architectural like design as far as implementation on like slashing conditions for data availability. You have to be very cognizant of the fact that there are different things at play that a proper actor can still, like if you just solely say, hey, do you have the data? And you don't receive a response back, that does not necessarily mean they're acting maliciously. In fact, that's like possible that they could be getting like DOSed, essentially, that they have too many requests to respond to. Essentially, they don't have the ability. So more so speaking to the fact that there are other things that you have to be very careful about, like these slashing conditions, and custody is like an aspect of it, and like how you are able to ensure that you can retrieve data that has been dispersed.
Mustafa, a quick take, and we have to wrap up.
Yeah, I mean, I think it's pretty clear, like, proof of custody does not provide you with data availability guarantees. It's more like a nice to have, or like, if you can't do data availability, then custody gets you kind of like maybe something, but it's better than nothing.
I mean, again, we are talking about different kinds of guarantees within the protocol. If the guarantee that we want is on the dispersal, then that's one. It's about retrievability later, and you want to prove that within the protocol, then there are proofs of retrievability that are there. You can have to play challenge response mechanism there. If the end user wants guarantees, it has to do sampling because that's the efficient way to do it. And after 18 days, after 20 days, if you still would want to have guarantees, you have to play a fresh round of challenge response mechanism and not rely on original attestations.
Toggle, last chance for a controversial take, and we're wrapping it up.
Just use Ethereum.
All right, thank you guys. Thank you, the panelists. I hope that it was as entertaining as it was to me, and thank you so much, guys. I hope you see you next year.
Thanks.
All right, everybody. Next up is going to be Mustafa. He's going to remain on the stage for his State of the Modular Union.
Who's got the clicker? Thank you. Let's see. Okay. Okay, so this is a photo of a electronics marketplace in Shenzhen, China. And this is the way that I think about the modular ecosystem. So a lot of your hardware, including things like phones and laptops, are made in this place, in this city in China, Shenzhen. And it's kind of like a hub where all of these different hardware manufacturers can all kind of work together. And in Shenzhen, you can prototype a new phone in like 1 day or 2 days, whereas anywhere in the world, it would take you months or years. And you kind of have all of these different components of a hardware stack, and all of these different manufacturers all kind of like trading with each other and providing different pieces of the stack. Like your iPhone, for example, most of the components in there are not made by Apple. It's made by all of these different manufacturers, whether it's like your camera, your touchpad, your screen, so on and so forth. And so you can kind of think of the modular kind of like ecosystem in that way. You have all of these different layers, like execution, settlement, consensus, data availability, bridging, block explorers, roll-up as a service providers, and all of these projects are all kind of like collaborating with each other, interoperating with each other, connecting with each other. But what if we took some gasoline and lit this modular marketplace on fire because it sucks? And what if we try to imagine like what the ideal future would look like, or what the ideal synthesis of this like modular marketplace would look like? Because there's obviously still a lot of work to do. So first of all, let's start with the thesis. Like, why are we even here in the first place? I think a big part of why we're here in the first place is because since kind of like Bitcoin was created in 2008, we've been kind of stuck in this loop of new layer ones. Like every cycle, there's these new layer ones, right, that have incremental improvements over the previous layer ones, right? First you had Bitcoin and Ethereum, and then you have Cardano, Tron, all those kind of projects. Then last cycle you had Solana and Avalanche. This cycle you have Aptos and Sui. It's like, where does it end, right? It's like every cycle there's new layer ones that have incremental improvements over the previous layer ones. And all these layer ones try to create a whole new ecosystem that replicate the ecosystem of Ethereum by having some DEX somewhere, some NFT apps, some namespace, name service, and so on and so forth. And I think like if we want crypto to mature, then we have to kind of like break out of this loop that we've been stuck in by having a positive sum ecosystem, not a tribal ecosystem where it's like just a bunch of layer ones in tribes trying to create parallel ecosystems, reinventing the wheel, and so on and so forth. But with a modular ecosystem, you don't have to reinvent the wheel. Like if you want to make a better version of the EVM, you You don't have to create a whole new layer 1 just to do that. You can just do that in a minute by going to a roll-up as a service provider, create a fork of your EVM, add a new opcode, whatever you want to do, and in 1 minute you can spin up your own roll-up that inherits the security of Ethereum or Celestia or any other DA layer. And the first Modular Summit 1.0, 3 years ago, I think was very much about the theory of things like roll-ups and the modular stack. Like, a lot of it hadn't been implemented. Like, there wasn't even, I think, any general purpose, roll-up frameworks. Like, this was before we had the OP stack. Like, this was just one, like, OP was OP mainnet. This was before Arbitrum Nitro. It's like people were expected just to use specific roll-up networks, roll-up mainnets, but you couldn't really build your own application-specific roll-up. Then last Modular Summit, last year, we had the practice, right? We had these things actually being implemented, We had roll-up frameworks, we had bridges, we had all of this infrastructure. We had the first inklings of new roll-up as a service providers. But the big difference between last year and this year is that last year, there was zero blockchains live that supported data availability blobs. Like EIP 4844 wasn't live, Celestia wasn't live, nothing was live, right? You had very limited data availability throughput. Now we have 3. We have Celestia, we have EIP 4844, and EigenDA. And I think that's significantly changed the game, because now we're seeing an explosion of rollups, and that's why the theme of this summit is modular expansion. So this was, if you look at the modular ecosystem in 2022, it's pretty early. 2023, last year, we had an explosion of kind of like these infrastructure projects, bridges, sequencers, frameworks, roles as a service. This year, there's a little bit more infrastructure projects, right? But not as big as a jump from 2022 to 2023. There's some new execution environments, there's some new bridging providers, and so on and so forth. But where we see the biggest difference is in the actual number of developers or the actual number of rollups, right? And I think this is largely thanks to the emergence of rollup as a service providers. So these were the rollups that were deployed in 2023, and I kind of like sourced this data from L2Beat, Wayback Machine. These were the rollups, right? You had a bunch of general purpose rollups. These are what I call universal rollups, and these were like just general purpose EVM chains. Nothing strictly differentiated. And then you had application-specific rollups. You had a few of them. Now this year we have a huge explosion of new application-specific rollups and general-purpose rollups. And as I said, this is like largely thanks to the emergence of new rollup as a service providers. Because what we're seeing is that developers are choosing to actually deploy new applications, not using smart contracts, but by deploying new rollups. Because what we're seeing as part of the fat application thesis is that application developers want to own as much of the infrastructure as possible, because then they can actually, for example, either have more flexibility in making new use cases possible that weren't possible before, or capture more revenue that makes developing these kind of applications more sustainable. So who knows what we'll see next year at next year's Modular Summit 2025. I think 1,000 rollups. I mean, maybe that's ambitious, but I think we'll definitely see a lot more application-specific rollups for sure. But why does modularity actually suck? But like, what is the antithesis of modularity? So I'll read out this tweet to you, right? We fucking lost it. Nobody in their right mind wants over 550 rollups and endless layers that take days to bridge back. What the world wants is one goddamn chain that just works, and that should be Ethereum. No one with a shred of sanity wants to switch networks in MetaMask. No one wants the headache of adding a token manually on another chain because the contract address isn't the same. Bridging is a pain in the ass. What people want is to transact value simply and directly without all of this convoluted bullshit. And that's like, there's a lot of truth to that, right? It's like, it is kind of like, bridging does kind of suck, like MetaMask, this is what MetaMask would look like if you use all these L2s. Who would understand this? Like, doesn't make sense, The other problem is, there's this dream of sampling light nodes. So we do have sampling light nodes. We have these beams of sampling light nodes. And then it's pretty cool, right? But so far it's just a meme, right? Like, it's just people running light nodes on a laptop in cool places, and that's kind of cool. But that's not the point of light nodes. Like, the point of light nodes is not just to run them for fun. It's to actually embed them into wallets so that people don't have to trust centralized RPC providers like Infura and Alchemy, right? That should be the point of it. But we're not there yet. And finally, like, we're still deploying a lot of duplicate general purpose EVM chains. So, like, what is the point of modularity? Are we actually taking advantage of modularity, or are we just like copying and pasting a bunch of chains with the same applications, right? So what is the synthesis, and like what is the destination, and where are we actually going? Because I do think there is progress on all these problems, and I do think these are solvable problems, and we have to solve them because we do need to break out of this monolithic layer 1 loop. We can't just have endless layer 1s. So it's really important to solve this problem. In terms of the bridging, these are solvable problems. Like, there are good bridging experiences. Chain abstraction, that's become hyped, but there is some merit to chain abstraction, and things like cross-chain contract calls and intents, right? Those things do actually work, and there are good user experiences. Like Skip API is a pretty good user experience. For example, if you want to mint an NFT on Stargaze from the Cosmos Hub, you can do that in one transaction without even realizing you're interacting with a different chain. So, like, you can try out these products like the Skip API, for example, and Hyperlane, and see what a good bridging experience is like. So ideally, we live in a world where, just like if you use a web browser, you access lots of different websites, but you don't care what infrastructure they use. You don't care if they're AWS or DigitalOcean. So it is possible. Like, we know how to build it. We just need to build a world where, like, you don't have to. Like, if you're using a chain, and you're bridging between 2 different chains or multiple chains, you shouldn't even have to realize that they're different chains, right? It should feel all like one seamless experience, like you're using one single chain, and that is possible. Like, we've seen demos and actual live bridges that do that with things like cross-chain contract calls. Now we just need everyone to work together to actually make this possible, to make this widespread. So it's like, if you're building a new rollup, then how you think about interoperability should be the first thing you think about. Like, and then we need everyone to work together, including block explorers and wallets. People need to build wallets that support things like chain abstraction or cross contract calls, and things like chain specific addresses. If we had the address format that was actually specified the chain that address is on, that simple things like that would make the user experience way better. Finally, light nodes, right? As I mentioned, the whole point of light nodes is that we should be running them in wallets, not just as a meme. So, video. This is a demo. This is actually live. You can go on this right now. Lumina.rs. This is a first step of making this a reality. You can now run a Celestia data availability sampling light node on your computer, on your laptop, in a browser, or on your phone. So you can go on this website right now on your phone, and your phone will immediately start sampling from the browser. And this is a very important first step to actually making light nodes useful, because now that we have an in-browser implementation of a Celestia data availability sampling light node, what that means is that now it's way easier to embed that into wallets, right? So now, because this is a WebAssembly implementation, so now we can embed that into wallets like Kepler or MetaMask way more easily, because they're just browser extensions, right? And this is just a code that runs in the browser. So there's QR codes all around the venue. You can actually, I think if you scan one of the QR codes, you can actually mint an NFT for running one of these on your phone or on your desktop. So check it out. It's pretty cool. Finally, we are seeing an emergence of non-EVM rollups that aren't just duplicates of each other. I think the bottleneck has been a big bottleneck around that has been proving. Like a lot of the proving infrastructure right now exists for AVM, right? I mean, you do have stuff like Arbitrum Stylus, for example, which is a important direction, but we also have provable. There's been a huge amount of advancements in provable ZK VMs like SP1 and RISC-0. Now it's like it's possible to actually prove any arbitrary code using a ZK VM without having to write whole new circuits, and I think that will open kind of like a whole new era of alternative execution environments that you can actually ZK prove using rollups. And then yeah, we do have some early alternative VM rollup frameworks coming live. You have Rollkit, which supports Cosmos SDK. You have Move. Eclipse is building SVM rollups. Cartesi is pretty cool. You can basically Linux rollups. And now we're seeing Solana L2s. I mean, there's a lot of discussion about Solana L2s. Is ZK compression a rollup? That's a debate for another day. But we do see that now even Solana, which was always thought to be the end game of Solana, is one big monolithic chain. Now there's a demand for L2s there and rollups. So yeah, I mean, I think it's really important that we do make progress on these problems. And because, as I said, we need to, like, the crypto will always suck, and crypto will never actually mature into a useful space if we're going to be permanently stuck in this loop of just people building new layer ones to basically have incremental improvements, but are basically tribes in a negative sum ecosystem where people are competing with each other. It's important that we have a positive sum ecosystem where modularism thrives over maximalism, and all of these components can actually harmoniously work together, and that it's not a pain in the ass for users, and bridging is seamless, and it all feels like one L1 or one chain that everyone's using. Otherwise, we're going to be stuck in this loop of infrastructure. So that's why the theme of this year's summit is modular expansion. And so these are the things that I think we need to do to actually expand, to make rollups expand and actually useful for people. And I'm looking forward to more interesting conversations with you all at the summit. Thank you.
Any questions, maybe, from the audience? I think you get off for free,
okay.
Mustafa. Next up is going to be Sandeep, and he's going to talk about aggregation. We will start in 5 minutes, so we have a small intermission. Please stay seated if you want to see Sandeep, of course. All right. The next speaker is going to be Sandeep. Let's go to the stage. Give him a big hand, everybody.
Thank you. Thanks, guys, for having me. Yeah, so I think, like, it's a apt, slide after Mustafa just presented. Is that, this, what we are talking about is, I'm not sure how many of you guys have heard about the Polygon Ag layer, but this is basically, we believe, is the next step, or standing on the shoulders of modularity. The next stage is aggregation, and that is what Polygon has been working on, and I'll go through that. So this is like the mission of Polygon is this quest for this infinite network. because like in the blockchain space, we have, typically the infra has been a very investable asset class for the VCs, crypto VCs and all that, and the chains, L1 chains, if you can have the next Ethereum killer and all that, this has always been a theme for the VC investments and all that. And anytime a new chain comes up and they will be like, okay, we have this much TPS, we have 500. It started with like, Polygon POS itself, did like 200, 300, 400 TPS back in the day. Then you had like, okay, we will have 10,000 TPS. Somebody would say we would have 50,000 TPS, 100,000 TPS. Like now there are claims of 150,000 TPS on one single chain. The point is that no matter what constant number you talk about, that this big, chain, and you can crank up a particular state machine, no matter how much you crank it up, it still is not enough if we all expect the Web3 to go mainstream, right? Because I can tell you that because all these like Instagrams and Reddits and all these NFTs, they live on Polygon, like all of these stuff. And we used to talk about Instagram when they were going to mint NFTs, and they'd be like, even if we make it like free to use or open to use in the smallest geographies of Instagram worldwide, it will choke not only Polygon's chain, but all the chains that were existing at that point in time. So point is that these shared, fixed capacity chains are not the answer for this. The answer is like an infinitely growing network. Like how about 1 million TPS? How about 10 million TPS? Or I would even say, and you will see, in the coming 3-4 years, you would probably start seeing, not like 3, 4, 5 years, but maybe over time, like, probably 1 billion TPS on these chains, at least the capacity on the front. And, currently when we talk about this monolithic scalability, it is like always like some constant number, constant, and constantly we started with Bitcoin 7, 10. Today, these days, Solana is very popular, 3,500 TPS on some of the days they are able to clock. Polygon POS also consistently clocks like 170, 200 TPS and generates a large amount of fees, but it's still a constant number. So how do we prepare the Web3 infra for the internet scale adoption? And on the internet, like, just to give you a simple analogy is that, when you landed in Brussels, you are not looking for Brussels internet to connect into, right? You came in here, you brought some telecom package, and and boom, you are connected to the global internet. And this is not true for the blockchains today. Like, if you are on Polygon POS or Arbitrum or Optimism or Solana and all that, you are in some silo. And then if you want to use an application on some other blockchain, which you like, let's say you wanted to use Polymarket on Polygon, which is very popular these days because of the US elections, and you have your assets on Ethereum mainnet, you have to bridge. If you are on Arbitrum or Solana, you have to bridge using some third-party bridge, and then you can use those applications. The internet doesn't work that way. I just connect on my phone and I can connect to any application available to me anywhere in the world, whether it is built by a team in Iceland or Japan or wherever, right? So how do we prepare Web3 for the internet scale? And it needs to have these two things, like first, and that modular structure as Mustafa was presenting, that enables that, right? It's not like, fighting for the same set of users across all the blockchains. It achieves like practically infinite TPS. As many chains you can have, infinite TPS, especially some of the like modular designs using data availability. But let's say if you start using ZK also, then data availability for the ZK chain, Validium's data availability on something like what I'm going to talk about, like on Ag layer, data availability becomes also infinitely scalable. That means the chains can use any data availability layer that users or the developers want to use. So practically infinite TPS comes from this modular design, but then you run into the issues of fragmentation, which is, we were talking that users have to bridge the funds and all that. So how do we solve these two issues both? Because both are important to take the Web3 to the internet scale. And that's where what we are building, that is like we called Ag layer, the aggregation layer. And what Ag layer is this neutral, decentralized service which is a pay-as-you-go service. I'll talk more about that. That enables this safe interoperability between the connected chains and also unifies the liquidity, right? And when I say the safe interoperability, some people might, is it like a bridge? Like it's an infrastructure on top of which bridges are building. It's more of a, I think of Ag layer as more of a blockchain of blockchains, where there are multiple sovereign blockchains. You can think of it as a, in a very weird analogy, you can think of all these chains connected into the Ag layer in a way that is, they can be called shards, but they are actually not really shards, they are all sovereign chains. And that is one of the biggest unlocks of Ag layer, that any chain connected into the Ag layer, they can be completely sovereign. They can choose, and Mustafa was also mentioning like VMs, they can choose their own VM. Like they don't need to be EVM. They can be, we ourselves are building, for example, opt-in privacy plus high throughput VM, which is Maiden VM. Many of you guys would have heard about that. So it enables the developers to choose any kind of VM. You could choose Arbitrum Orbit, Optimism stack, any other stack, Sovereign's SDK, whatever stack you want to use, you can use that stack to still connect into the Ag layer and connect into this larger internet and or this Web3 internet. And the thing is that you can choose any decentralization profile. You can have a fully decentralized layer 1 like Near protocol, which is connecting into Ag layer. You can have a single sequencer. You can have like privacy enabled chain. Anything can connect into Ag layer, and then that makes it the users on that chain become like interconnected across all the chains. So the end goal for Ag layer is that all these chains combined feel like one single chain. And what is the offering of Ag layer is like, the most important thing is it offers a safety guarantee for all the chains that are connected into it. With obviously that once you have that safety guarantee, these chains can interoperate with each other natively. When I say interoperate, it's not about, and again, I want to go back to the internet analogy. In the internet, previously it used to be, and if you see, that's why it's called internet. It's a connection of multiple local networks like LANs, WANs, and so many other smaller networks. This is basically the interoperability. The current internet is the internet of information. The data can seamlessly flow from one place to another. The internet that we all are trying in the crypto industry to build is this internet of value, where the value can seamlessly flow across any of these chains easily. So that's where, I mean, although this meme is like very misused or abused in crypto, like this TCP/IP of this, but if you look at like Ag layer a little bit deeply, you would realize that this is something similar to like a fat TCP/IP, actually, that protocol that can be like a small part in the wheel. Still, these blockchains who are actually having distribution to the users, they will play a much larger role. But this is a small part of an essential part of the entire infrastructure. That's how we are trying to build Ag layer as that, the minimally value extractive. This is the part like I want to mention, that there are some architectures we are thinking about, like in the crypto industry there are multiple architectures being thought like that, where the interoperability can be achieved. But many of them are like currently in terms of their economic architecture, they are like rent seeking. That means you have to offer X percentage of your revenue of the sequencer to that chain. And for an app builder, it's super hard to kind of like think like, okay, especially if there's like the app is well funded and they feel that there's a big future for them in the future, it's very hard for them to commit X percentage of their chain's fees continuously to a platform and all that. Whereas like on Ag layer, we are completely agnostic to this. Like if a user, if a developer wants to use a very high quality VM and wants to pay for it, it's absolutely great. Like, for example, Arbitrum Orbit offers a very good, like, Mustafa was also mentioning like stylus and other features. It's a great software to run their chains. And for them, like we see developers are willing to pay fees. The thing is, for Ag layer, it does not matter which stack they are using and what is the revenue share on their sequencers. or other part of their ecosystem. Ag layer simply intends to provide them a simple, and straightforward interop, which is safe, and the value can move around, easily. And some of the other benefits of ag layer is like, obviously these tokens can have native tokens. They have like safe cross-chain transactions. And then, like some of the functionality, like, the bridge and call functionality that ag layer offers is like, which also allows, if you are like actually a chain builder and you connect into the ag layer like properly with the unified liquidity, then any of the chain, if any chain in the ecosystem, let's say OKX chain or Polygon POS, which is like, shortly will connect into the ag layer, any chain is connected to an exchange, then that means all the chains are connected. Because if users want to withdraw funds to that chain, you can simply use that bridge and call functionality and then move your funds from that exchange to the chain that you are on, right? So basically the Binance chain, let's say if it is connected to Polygon POS, you want to move your funds from chain XYZ, which is a gaming chain, you can simply move your funds with, like, assuming Binance adds that functionality, you can move your fund directly from Binance to your own chain natively. So those kind of functionalities, unified liquidity, I already talked about that, on all of these chains, the value can flow without any foundations of liquidity. Many of you guys who use these third-party bridges, they know that these bridges will have, the bridges have to maintain the liquidity on both the sides. And if you want to move the funds, if the bridge runs off the liquidity on the other side, you cannot move the funds. Whereas on ag layer, because if the chains are natively connected into ag layer, how we are building this is that the liquidity is free flowing. Like, you can move infinite number of tokens safely from one chain to another without the bridge or the shared bridge maintaining liquidity or needing additional liquidity provisioning on those chains. And if you want to dig more into that, like definitely discuss more about that. And then this is the high level architecture of ag layer. It is like right now the V0 is available on Ethereum, and there are like few chains, 4 or 5 chains are connected into it. But in future, once it docks out of the Ethereum main chain, then it's going to be a much lower cost, like the layer where all these chains can connect into the ag layer. They have like two kinds of proofs. We have like come up with this proof which we call pessimistic proof, which is more of a proof of that chains are not misbehaving with each other. And then if you want to secure as a user, if you want to be safe from the sequencer misbehavior, then you can add full execution proofs. And for that, you guys know, like, I mean, Polygon ZK is generally considered in terms of research and all is like one of the leading firms in the space. And this, like, with our type 1 provers on EVM, type 1, type 2, and other kind of provers like SP1, for example, which Mustafa is talking, is also built on Polygon technology called Plonky 3. So it's essentially like SP1 is a library which enables you, if you have a Rust code, you can take any Rust code and pass it through SP1, and it generates you a Plonky 3 proof on the other side, Plonky 3 prover on the other side. And so Plonky 2, Plonky 3 proving libraries from Polygon is like, generally it looks like the industry is converging towards that. We see already a lot of protocols who, even the ZK protocols itself, like slowly converging into that. So I mean, the proving system, anybody can use pessimistic proof as a baseline, and then if you want for the chain misbehavior across each other, and if you want to if you want to secure your users from even the sequencer misbehavior, then you can use the full execution proofs. So that is the rough architecture of ag layer. We can, if you want to look deeper into it, you could go into the documentation. So roughly, that's the whole idea here. Ag layer plus Polygon CDK. Polygon CDK here is a kind of descriptor term for like you using any chain. But in future, you would be able to use OP stack, hopefully Arbitrum Orbit, and any other interesting stack, or for that matter, any chain like you could fork like Polygon POS chain or Ethereum mainnet itself, launch your chain and connect into the ag layer. All of those functionalities should be easily possible with AgLayer. Currently, we offer like Polygon CDK only, but together they could achieve, as I said, the quest for infinite TPS, which we need if we want DeFi, gaming, all of these like mass use cases to grow. So unlimited scalability, unified liquidity, that's the mission of Polygon and that's the mission of AgLayer. I rest my case here. Thank you.
Maybe any questions from the audience?
This light went away. Now there's more light. There's more light on this slide. So AgLayer provides that functionality at the base layer. Like, there are multiple teams, middleware teams who are building that functionality, simple API calls that you can have. But essentially, what is happening is that with the bridge and call functionality that, the fund gets moved. So I don't know whether if you anybody used like sending funds to Ripple. It is like sending funds to a ACH account. You send to the main wallet and you have to define a code that, okay, this is my, this thing, right? So similarly, if an exchange is able to implement, you could define that, okay, I'm sending my money to this address, but as a chain ID code, right? So this will have a chain ID code. So when it comes to the bridge with that chain ID, it automatically gets routed to that chain. So you can directly withdraw to the other chain. That's how it works. But on top of that, middleware companies are working on simple API interface where developer just needs to call a simple function and that happens in the background. Yeah?
Like in here, on your left. So in the previous talk, we mentioned a bit chain abstraction. Yeah. Do you consider the AgLayer part of the chain abstraction stack or narrative, if you can say, or is it something you feel totally outside?
I think chain abstraction is actually one of the components of what we feel is aggregation. Like aggregation aggregates all of these individual elements. Like with this kind of thing, you need chain aggregation because the chain abstraction has a lot of things like wallet level aggregation, transaction level and the abstraction, intents and all that. All of those things are possible on top of AgLayer aggregation, right? But whereas when you talk only about chain abstraction, you are talking most of the times these transaction or wallet level abstractions and not talking about how the interoperability happens. So basically aggregation is, you can think about that aggregation is abstraction plus interoperability, right? But these are more like definitions, so yeah.
So the earlier question that Nick asked, was that relevant to natively moving the asset cross-chain? So is that the identifier that is being used, and how is that identifier secured? Like who is maintaining that ledger, that unique identifier for the natively moving of the assets?
Yes. So generally that ledger is being that all those let's say cross-chain token mappings, all this kind of chain IDs, they are all maintained on Ethereum. Because the AgLayer still connects on Ethereum, right? And uses the information from Ethereum to have all of these decision making.
I think that will be it for the questions.
Yeah.
Sandeep, thank you very much.
Hey.
Give him a big hand.
Yeah, welcome.
Next up is going to be Ed Felton from Arbitrum, speaking about Stylus.
Hey, everybody. Thanks for coming. I want to talk about Stylus. There's a lot of attention to all of the areas of building an L2 or L3 chain. Thank you. Whether it is sequencing or data availability or proving, there's, at least at this event, I haven't heard as much attention to execution, but the execution layer is actually quite important. And I want to talk about about Stylus and the multi-VM, which I think is the biggest breakthrough in blockchain execution I've seen in a long time. So, and I want to emphasize that everything I'm telling you about today exists and is available to you on testnet. And assuming that the Arbitrum DAO votes for it, will be on Arbitrum 1 and Nova mainnet. And if you have an Orbit chain, can be on your chain. Okay, so let's start with the EVM. Arbitrum has supported, like most of the Ethereum stack has supported EVM from the beginning. The EVM was designed for good reason, a design that made sense at the time and still does make sense for a lot of use cases. It was meant to be small and was meant to be easy to price. This was one of the, I think, the really amazing pieces of foresight in the design of EVM was to think about pricing as an inherent part of the mechanism. And so, right, Ethereum code or EVM code is written in Solidity kind of like this. It compiles down to this binary code. The code is translated into EVM bytecode. All right. But most developers on Ethereum, of course, tend to write in Solidity. Some write in Viper. But essentially, if you're learning to program in the Ethereum stack, you're probably learning Solidity programming. And unfortunately, bugs are reasonably common in code that's written in these languages. And it's partly because I think in the early days and when these things were first designed, there wasn't enough experience to understand what kinds of bugs might arise from it. Also, frankly, just the scale of the developer community meant that the amount of resource devoted to building really high-quality tooling, not only for things like compilation, but also testing and so on, was not there and still is not there compared to other programming paradigms and languages. So we saw, early on a lot of bugs. The community has gotten a lot better. Experienced Solidity programmers have a giant checklist in their head of things not to do. But obviously, it's better if it's not the programmer's constant attention and experience that prevents bugs, but something else. Okay, so how did we get here? Well, Solidity was designed to be easy. It's been compared to JavaScript in the sense that it's relatively easy to get on board, at least to some extent. And like JavaScript, ease of onboarding can be a pro or a con. But easy isn't always simple. If you're writing mission-critical code, if you need to avoid bugs, and smart contract programming is really all about avoiding bugs. It's important to have languages and tools and systems that are as bug-resistant, that make it as easy as possible for a competent programmer to avoid shooting themselves in the foot. Okay, so one approach that some projects have taken is to say, well, let's not do the EVM, let's not do Solidity, let's use a different virtual machine. Then we can perhaps write our programs in a different programming language. And you see some success here, things like Solana, obviously. But in the Ethereum space, we have this huge and vibrant community of programmers. We have a big installed base of applications that already exist. And so that's kind of the dilemma that you might see us as being in. You're either in the EVM world, some pros and cons, or you're in the non-EVM world and some pros and cons there. Right? And so one of the drawbacks of being in the EVM Solidity world is that it's a much smaller developer community. So this bar graph shows the number of active developers in each of these programming languages, systems, C and C++ being huge, Rust being pretty big, EVM Solidity being smaller. Now this means fewer programmers available, it means less existing code available, and it means tooling that is less secure and less robust. So we asked ourselves, well, do we have to choose? Why not have both? Right? Why not build a single system that lets you write your code in EVM, in Solidity and EVM, or write it in the language of your choice and run it all together on one big happy chain? So it's time to do that. Let's give Ethereum developers that power. So that's what Arbitrum Stylus is all about. It's the next generation programming environment for Arbitrum chains. Lets you write smart contracts in Rust, C, C++, Zig, and other languages. And it's fully EVM interoperable. So to give you an example of what it looks like for code, here's a Rust function that computes the Keccak hash of something, and it does that by calling the standard library, a standard library in Rust to do that. And the programmers just decorated it with this decorator at the top, hashtag Arbitrum. And this will cause, in Stylus, this will cause the compiler to compile this function so that it can run on an Arbitrum chain. And so porting this to Arbitrum is as easy as just writing that at the top. Okay. One of the disadvantages of EVM as it stands is that it's relatively slow and expensive. So for example, in the time that the EVM does 7 add instructions, you can do 1 hash round of Keccak in a state-of-the-art virtual machine. So alternative virtual machines such as Wasmer, which is the arguably the most popular WASM virtual machine, is able to run much faster, and for 2 reasons. One is WASM was very carefully designed for security, for performance, in a way that EVM was not. The virtual machine has much more engineering effort into it, but also EVM, in some respects, is unable to run quickly. So for example, the fact that the basic data structure is a 256-bit integer, rather than a 64-bit integer like you see in Rust, has a real impact on performance. These things really add up. All right? Okay. So Arbitrum, it turns out, already proves the results of computation by doing fraud proving over WASM execution. That's a decision that we made back in 2021, and we made it because we anticipated that we wanted to do this stylus move later. So Arbitrum state gets settled to Ethereum using fraud proofs over WASM already. And so the idea is that, so currently in the legacy Arbitrum, the fraud proofs are over WASM code that's compiled from the Arbitrum state transition function. So the idea is, well, why not extend this to user-provided WASM code? So what you need to do then is to have the ability to take in untrusted user code and to load it into that same execution environment that you're going to prove over, and of course do that in a way that is safe. WASM is a big deal, and I want to give a little bit of a sales pitch for WASM WebAssembly. Here we have the founder of Docker saying, well, if this stuff had existed in 2008, we would never have needed Docker. WASM is designed for the purpose of securely running untrusted code fast in an internet environment. It's used, for example, in browsers. It is designed based on a lot of really careful computer science work to design and prove and assure the semantics of the language. And also, there are very heavily engineered and battle-tested WASM virtual machines available. Okay, so that's what the multi-VM is. The multi-VM is this idea of having one chain, multiple languages, and fully composable. And this is a big deal, right? So what we're not doing is creating a silo for EVM code and a separate silo on the same chain for this WASM Rust code. What we are creating is something where any program, any contract can call any other contract, regardless of which language it's written in, regardless of how it was compiled. And users can interact with applications without knowing or needing to know in what language that application's contracts were written. In fact, it's even possible, if you're using a proxy upgrade pattern, to upgrade a legacy EVM contract into a Rust stylus contract without breaking anything or even changing your data representation. So this is not a new L2. This is designed to run on existing chains. Existing Arbitrum chains can upgrade into it. And indeed, the main Arbitrum testnet is already upgraded into stylus. Okay, so underneath the covers, the way this works from an engineering standpoint is that 2 composable virtual machines are built. Basically, we took an EVM implementation and a WASM implementation, Wasmer, which is the most popular and mature WASM VM, and integrated them together to give a single state transition. There's a single state try, which is exactly in the Ethereum format. which you're using regardless of which language you're in, one database. There's really nothing else like it in the ecosystem. So, and this has a bunch of really big advantages. First, faster runtime. Why faster runtime? Well, you have a faster VM. You also have better, more mature compilers. And if you write in a language like Rust, which is very good at telling the compiler what's going on so that the compiler can optimize more aggressively, you get a big performance advantage. So to give an example of one benchmark, if you're running Keccak hashing by using the native Rust library versus writing that code in Solidity, that is not using a precompile or something, then Stylus is 73x faster. So for compute-intensive workloads, you can get a lot more computation for the same gas. In fact, Stylus doesn't use gas to charge you for instructions. It uses milligas, called ink. So even memory access can be a lot cheaper because memory representation can be more efficient. So this allows a lot of new use cases. It allows more advanced cryptography because you can do more computation and you can import legacy Rust libraries for cryptography, or C or C++ libraries. It allows some AI-related applications to happen because not only, when you go faster, not only does it take less wall clock time, but also you can do a lot more within the same gas limit. It allows you to do L1 precompile research. That is, if you want to try out a precompile on, say, either in a testing environment or on your own chain, you can write that precompile, you can write that code in Rust, import it in Stylus, and get performance comparable to what you would get if it was a precompile that was handwritten to go with an existing chain. And so you can try out prospective precompiles by actually implementing them and running them at about the speed they would run. Also, you can do heavy computation of many different kinds. So for example, in finance, you could do a Black-Scholes computation quite feasibly. And one of our developers has done that. Okay, you can use tools you're comfortable with, right? You're not using a weird domain-specific language. It's not kind of sort of like Rust. It's not inspired by C++. You use the real compiler. And there's a really simple system call-like API to do the things that you would do in Solidity with sort of the magic things like block.number. And so you just have a library like this, block_number, just call that. So all of the affordances that EVM programs have to see chain state, to see the time, all of those things, those are all supported in simple Rust-style libraries. That's all part of the SDK. Most importantly, of course, the EVM compatible, fully interoperable. There is automated support in the SDK for the EVM binary calling convention. That means if you want to call some EVM code, you can just simply write an interface in, you can simply sort of declare a function signature and then just put a decorator above it saying to generate stub functions for calling it. So that means you can interact with call and be called by EVM contracts that are written in Solidity and Viper in a really natural way. So here's an example. Here's a Solidity program. We've got this contract foo, and it's calling some contract that satisfies this interface counter. Right? This is what you would write if you were in entirely EVM world and you wanted to have this counter contract. Right? Now, if in Stylus, if this counter contract were implemented in Rust, you wouldn't have to change anything. This code doesn't need to know what language the thing it's calling is written in. And it works the other way as well. If you're calling from Rust, you don't need to know. The end user doesn't need to worry. The user experience is just the same, except stuff is faster and cheaper. It just works. So one of the lessons here is that EVM compatibility is not the floor for performance, it's the ceiling. That is, oh, I'm sorry, it is the floor, not the ceiling. That is, EVM compatibility is table stakes, but we can do much more without taking away EVM compatibility. It's not an either or, you can really have both. The testnet's available. There's a lot of documentation and examples. You can go and look at it and try it out. A lot of people have. The SDKs actually are kind of amazing. I want to give a few examples to give you a flavor of how easy this is. So here we have, this is Rust code. And we import some stylus stuff, including some stuff from Alloy, a really great package that Stylus uses heavily. Kudos to the Alloy team. Here's an example where we're declaring a data structure that we can access in Rust, but we want it to use the same representation as Solidity. And so we use this sol storage macro. We write inside the data structure in Solidity. And then this will automatically generate the equivalent data structure in Rust, which you can access in your code. And it will ensure that it's represented in storage exactly as Solidity would represent it. So that means, for example, that you can upgrade from a Solidity implementation into a Rust implementation by just writing the data structures of the Solidity code that live in storage like this, wrapping this sol storage macro around it, and then just using the data naturally in Rust. So down here, we can say, we have a counter, we can say self.number.get. That is, we can just access this from Rust as if it were a Rust variable of equivalent type. And the macro does all of that stuff. I also took this implementation of the counter type and decorated it with this external tag. And this tells the compiler that I want this thing, this counter implementation, to be callable as a contract from outside. And so this will get compiled into a contract which can be deployed. And it's really that simple. I simply write the code of this thing. I put the external decorator on it, and now it will be compiled as a deployable contract. It's EVM ABI equivalent. For example, here's an implementation of an ERC20 token. We have this sol storage declaration here, which declares the data structure. This is the data structure that you'd expect for an ERC20. You have implementations of the code down here. By the way, down here, we've declared in Solidity syntax some events and error codes, and those also get automatically translated into Rust so that they're directly callable or invocable from the Rust code, just as you would want. I have to say, having used this, that this is one of those really rare programming tools where everything works at least as well as you hope it does. One other programming language is it's easy to add it. Most languages that don't have without a runtime that compile to WASM can be used with Stylus. One of our team members, Raul Jordan, one day got interested on a lark in getting Zig to run in Stylus, and it took 16 lines of code to do. So pretty easy to do. It's just a question of how of getting it to compile to WASM in a natural way. So you can do that if you like. You need something low level. Well, if you want to have really low level code, you can write like this. You can write user main, and you take call data in and give back a result, which is either the return value or the error value. So very simple. You can just work with the bytes if you want that of call data. So again, if you want to do precompile like stuff, if you don't want to have to pay for the automatic marshalling and unmarshalling into the Ethereum ABI, you don't have to. All right, lots of people have used it. They think it's awesome. Here's an example of verifying messages signed with Ethereum Validator BLS keys. Again, just a little bit of code to do. Lots of examples here. I won't run through all of them. If you want to try this out, and I encourage you to, if you're a developer, arbitrum.io/stylus. It's available today on testnet. It is available for Orbit chains that do want it. And if the Arbitrum DAO votes to adopt it, then it will be on Arbitrum mainnet very soon. Thanks very much. Do we have a moment for questions? Yes. Okay. Questions? I think that's Bartek, although it's hard to see. Oh, there. Okay. Yeah, that is Bartek.
Yeah. Hi. So, like, one of the main benefits of public blockchains is the transparency, and I can go to Etherscan. I can look at the source code of my Solidity smart contract. How do you see the tooling around that? You know, how do you make sure, like, what is the vision for you moving forward?
Yeah, the vision is the same kind of verifiability that you have for Solidity code, right? That is, with deterministic builds, that you can send the source code, that source code can be independently compiled, verified against the binary contract, and then that fact can be published. So, the vision is that it works just like it does with Solidity.
But will you work with scans and the
Yes.
likes to actually support that?
Yeah. There's no announcements there, but that is something that we're pursuing.
Hello? Oh, hi. I have a question here. Yeah, thanks for your talk. So if you have one machine that's responsible for executing these transactions, and it's got two, like a WASM virtual machine and an EVM, how do you determine the order of the transactions if both of these virtual environments access the same global state? Do you run all of the stylist transactions first and then the EVMs after? How does that work?
I'd say two things. First of all, transactions still run in serialized order, right? The semantics of Ethereum is one transaction at a time, and that remains. So the order of execution doesn't change, and if you cross the boundary from one VM to the other, that doesn't change anything about ordering. So it's not like you can be running an EVM transaction while simultaneously running a stylus transaction. The other thing I would say is within one transaction, the transaction may be directed to a stylus contract, which calls an EVM contract, which calls a stylus contract. So you can have a mix and calling back and forth within the same transaction. So it really is seamless in that sense. Things work the way you sort of expect. It's not, although the two VMs are integrated, they interact by calling back and forth to each other and not by sort of running in a fully independent way. And of course, that's what you would want, right? You want it to have the same semantics of atomic transactions and and any transaction being able to call any contract.
Cool. Yeah, thank you.
That all works as you would hope. Got one more over here. Why don't you just call it out? I'll repeat the question, if that's okay.
Sure, yeah. You mentioned that this stylus is available for Arbitrum chains. So what's the licensing around it?
So the licensing is the same as the rest of the Arbitrum Nitro code base. And what that means is that if you're using it in conjunction with one of the DAO's chains, then you're free to do whatever it is you like. You're free to do whatever it is you like for non-production use. If you want to launch a chain that does not settle to one of the DAO chains, then there's an additional license option available, which basically, in which you would give a revenue share, but then you're free to do what you want. So there is no license that constrains how you use it if you use it. So either you use it for an L3 that settles to a DAO chain, or you share a little slice of revenue, or you go to the DAO and make a deal.
I'm wondering how you reason about the correctness of programs, especially because you have now this very heterogeneous execution environment where you compose VMs, and so I mean, for me the trust assumptions are much higher, and so how can I be convinced about the correctness of programs?
Yeah, the question is, with the two integrated execution environments, how can you be convinced about the correctness of programs? Right. So one thing I would note is that WASM has more clearly specified and more thoroughly vetted defined semantics than EVM. And so if I had to choose one of those two VMs in which to do something like proving attributes of programs, I would choose the WASM one anyway. Now, so to me, it really comes down to the question of, are you adding complexity by integrating these VMs? Do you have a more complex execution environment? And of course you do. The stylus implementation has been through a lot of diligence, a lot of testing. It's been through independent security audits. And so, the development team has done everything they can to ensure correctness of the platform itself. The semantics of calling back and forth between these VMs are actually not all that complicated because it's kind of an arm's length call through the Ethereum ABI. So there's not deep entanglement sort of in the semantics of execution. It's in the implementation where there is more complexity, and that's just the usual problem, the usual difficult problem of how to ensure correct execution of complex blockchain infrastructure. And I'd say the answer there is the same as it is in any other blockchain infrastructure, which is that it just requires a huge amount of effort on assurance. And happy to talk offline about what has been done, and there is a record of the diligence as well that's available to the public. This is also being debated in the Arbitrum DAO, and you can go to those forums and participate in the debate about that issue as well. Thank you.
All right, thanks everybody. I think there's now going to be a lunch break upstairs, so feel free to head over there and be back in, I think, 30 minutes.
Hello, everyone. I'm Anthony from L2Bit, and I'll be your MC for the second part of the Modular Summit. I hope you are doing well after the lunch break. Maybe let's start with some warm-up game. Who is in Brussels for the first time? Please raise your hand. Okay, and who has been there before? I see some people didn't raise their hands at all. I see it's sometimes hard to raise their internal consensus. So yeah, our first speaker will be Umaroy from Succinct, and they are trying to make ZK proofs accessible to any developer, so please give a warm-up of applause for Umaroy.
Thank you. Hello, I'm Uma. I'm one of the co-founders of Succinct. And today I'm going to be talking about how ZK VMs will upgrade the modular stack. So let's look at the modular stack of today. We have a lot of different execution layers. We have a lot of different choices of DA layers. We have a lot of different choices for settlement, for bridging. The beauty of the modular thesis is that you can have this flexibility and freedom. But it also comes with trade-offs. And I think a lot of what's being discussed today is the UX implications of having all these heterogeneous environments. Today, users face really difficult interoperability between all these different ecosystems. It's difficult to bridge, liquidity can be fragmented, and overall, the UX of the modular ecosystem today needs some work. And I think that ZK is basically the only way that all of these problems will actually get solved. With ZK, I think in the fullness of time, every rollup will be a ZK rollup, every bridge will be a ZK bridge, and all parts of the modular stack that can use ZK will use ZK and solve a lot of these problems. And today, we have words for this that people are working on, things like chain abstraction, unified liquidity, aggregation, the integrated thesis, interoperability. And all of this terminology fundamentally has ZK underneath if ZK was actually to be used. So ZK seems really powerful. It is the fundamental base of how the modular ecosystem will be connected and talk to each other, and in the end, have a good UX for end users. But historically, the truth is that ZK adoption has kind of lagged behind. For example, if you look at Ethereum, the top two Ethereum rollups right now are Arbitrum and Base, and both of those are built on optimistic, fraud-proof technology, not ZK. So ZK has a ton of promise, but there isn't a lot of adoption. Why is that? Historically, one of the big reasons is that ZK is really slow and very expensive. So if you've built with ZK before or have friends who've done that, you've probably seen a picture like this where you have to generate ZK proofs on a very big, very expensive AWS server with many cores and a lot of memory. And that takes up a lot of money. And then also proof generation, even with a really big computer, is still very slow. But I think what's even worse, more than the slowness and the cost, is actually that the ZK developer experience is really, really bad. Today, if you want to build with ZK, whether it be a ZK rollup or a ZK bridge or any other application, you have to have a team of 30 math PhDs or cryptography PhDs and a bunch of really smart engineers who know weird arcane languages like CIRCOM or Plonky2 or Cairo. And then they have to code in these languages that basically look like assembly with no print statements and really horrible developer tooling. And they have to understand all these math papers behind the scenes. And this slide looks chaotic and really horrible because that is the ZK developer experience of today. And because of these things, today, if you want to build with ZK, the time to production takes months, if not years. And you can actually see this in many ecosystems, where the optimistic rollups went to prod a couple years ago, but then the ZK rollups took a few more years after that to fully launch. And why is this the case? Well, it's a lot of what I was talking about before. Right now, you have to have a very specialized team, and there's probably less than 1,000 people in the world who can write all this ZK stuff. And then even if you have an expert, the developer velocity is extremely slow. You have to learn these custom languages, SDKs, the developer tooling is super primitive, and it is very similar to writing a very low-level language. Once you've done all of that, the end result is unmaintainable. For example, in Ethereum, Ethereum goes through a hard fork or upgrade every 6 months to every 1 year. And so if you want to be an Ethereum compatible rollup, you also have to upgrade your logic. With the current ZK tooling, this requires a huge engineering lift every single time. Furthermore, if other teams want to use your product and customize it, it's very difficult. Today, you have a lot of teams taking the OP stack and building their own rollup, and they often add their own precompiles, which they can simply do by writing an op-geth and writing some Go code. But if you have a ZK rollup and you want to customize it, good luck. It's going to be very difficult and not really something that's possible for an external team to do. And then finally, once you've done all of this stuff, you also really care about security. Now, unfortunately, today, the ZK code bases are often hundreds of thousands of lines of code. The audit surface is extremely large. There's very few firms that can actually understand it. And so it's very expensive and time-consuming to audit all this stuff and make sure it's actually secure and be ready to use in prod. So it's succinct. We've been building with ZK for a long time. We really love ZK. I think we've seen that it has tremendous potential. It seems super foundational. And especially with the modular thesis, I think it becomes even more important to connect all of these ecosystems together as we are getting thousands of rollups. And so we really wanted to accelerate ZK. We saw that the ZK experience of today was really bad, and that's why we built SP1. So what is SP1? SP1 is an open source, general purpose, performant ZK VM. There's a lot going on there, so let's break it down. So what is a general purpose ZK VM? What it allows developers to do is developers can just write normal Rust code and then get a ZK proof. So before, there was this kind of nightmarish world of circuits and specialized languages. None of that anymore. You just write normal code, and then it just works. It's kind of magical. The technical architecture underneath SP1 and most ZK VMs is that you have Rust, and it compiles to a normal ISA called RISC-V. It's a reduced instruction set. It's a standard target of the Rust compiler. And then our ZK VM SP1 proves the correct execution of the RISC-V ISA. And then underneath the hood, we use Starks and small field, baby bear, fry, and log derivative lookup arguments, and a bunch of other stuff. I could probably spend hours talking about that. But kind of the whole point of a ZK VM is you guys don't have to worry about that stuff. Only we do. SP1 is also really performant, which is very important. General purpose is obviously super great, right? Like write Rust, get proof, it sounds awesome. But if it's not practical, no one's actually going to use it. And so performance is extremely important. And we've actually found that with SP1, the proving time and the proving cost can often be better than the customized circuits that people have written in the past. And there's been many algorithmic innovations that our team came up with for our state-of-the-art performance that I'll go into in a little bit. And then finally, SP1 is also fully open source. So all the constraints are open source, and you can check them out yourselves, which is really critical for security and auditability to understand exactly what's being proven. It's also modifiable and customizable by external teams, which is really important. And we've already had several teams customize it and make different parameter choices or add their own precompiles, which I'll talk about in a little bit. So, OK, I've told you about what SP1 is, but let me show you how easy it finally makes ZK. Here's an example of a very simple Fibonacci program written with SP1. As you can see, it looks like normal Rust code, and that's kind of the entire point. With SP1, you can use the Rust standard library, so you can use Vex and all that nice stuff. You use Rust totally normally. You can use existing crates and libraries, so you can use Serde, you can use JSON, you can use Rust crypto and all the cryptographic libraries. You can use things like Revim and Ref. And I've personally found that developing with SP1 leads to 100x developer velocity and productivity. You have things like print statements and for loops and if statements, which sounds very normal, but if you've ever tried to use ZK before, actually is kind of a breakthrough. And you can just have all your Rust tooling, and you use all these existing libraries, and it feels very much like a normal programming paradigm. It's super easily maintainable and customizable, right? External teams can just take existing implementations and then modify them when they need to. And then I think one really cool aspect is that the audit surface area is much smaller because we can reuse all these existing crates and libraries that have already been audited. For example, Ref, which is a Rust Ethereum implementation, recently had their 1.0 release, and they were audited. And now you can just take Ref, import it into SP1, And then there's those thousands of lines of code don't need to be audited by your team because they've already been audited and used in production, and you're just good to go. So by making maximal use of existing Node software and audited libraries, your life as a developer and time to production gets a lot easier. And so I like to say, with SP1, using ZK goes from taking months and years to just being a weekend project. As I mentioned previously, another really important aspect of SP1 and general ZK VMs is performance. So being really easy doesn't mean anything if it takes several days or several hours to generate a proof. So at SP1, or at Succinct, we came up with several algorithmic innovations to make SP1 very performant. I could, again, spend hours talking about this stuff, but a little preview. We have novel memory checking arguments. We make heavy usage of lookups to really minimize the amount of proving overhead. But our main innovation that I want to touch on here is our precompile-centric architecture. So one of our key insights while building SP1 is that most cryptographic use cases that people care about for ZK, like blockchains or roll-up state transition functions or bridges, most of the prover overhead is spent in repetitive computations like hash functions and signature verification. So that takes up a lot of RISC-V cycles, and that leads to really long prover times. We thought, what if we could replace that with kind of a ZK native assembly, where we have a specialized circuit for things like Ketchak or SHA or ED25519 verification that talk to our main CPU and save time and prover overhead. And we found that when you do have these specialized circuits, and it's hard to kind of get all the engineering right to make this work, well, once it does work, it's actually really effective. You have programs that used to take billions of cycles go down by a factor of 5 or 6, and in some cases, even by a factor of 10 or 20. SP1 currently has state-of-the-art performance, often by an order of magnitude, and our precompile-centric architecture is really key to that. If you reduce the number of cycles by 5x or 10x, that's an automatic decrease in prover time by the exact same amount. And then more recently, we've been working on SP1 GPU, which is a GPU implementation of our prover. In general, the proof systems that we use, it's a very embarrassingly parallel workload. There's a lot of hashing that can be done in parallel, and other parts of the prover are also very similarly parallelizable. And our GPU implementation improves things quite significantly as well. So in all, SP1 lets developers write normal code without sacrificing performance. So it's pretty awesome. But I don't want you to just take my word for it. I also want to show you with an example that we had at Succinct. So at Succinct, we have been working with the Celestia team for quite a while on making a Tendermint-like client to bridge from Celestia to Ethereum. And originally, we were working on this Tendermint-like client implemented in Circuit World using a custom library called Plonky2. And this is what our circuit code looks like. It looks pretty ugly. You can tell it doesn't look like normal Rust. We're using this DSL. And it's pretty complicated. It's convoluted. And by the way, this is just one small snippet of one file. There's actually many, many files like this that we wrote. In total, I think it took us 3 months of time and thousands of lines of code in this really weird DSL that we had to write a whole Tendermint-like client in. It was very painful, and I can personally attest to that because I worked on this. Okay, now, recently, after SP1, we built the exact same thing. And the code that I'm showing on the screen is the entirety of the Tendermint-like client, and it shows up in one file on the screen, which is pretty awesome. And so I'm going to walk through kind of the various pieces. So first, to make a Tendermint-like client in SP1, what do? You import the Tendermint library, which is pretty awesome. The Tendermint library, by the way, was not made by our team. It's maintained by another team in the Cosmos ecosystem, and we can just import it, and it just works. And then we import another library, Alloy, that's maintained, actually, I think, in part by the next speaker, James, and some of the Paradigm team, and it's also really awesome, and it just works. Okay, then, our main body of our function is exceedingly simple. We just read in 2 blocks, we CERD-A deserialize them, we instantiate a verifier from the Tendermint library, we call this function verify update header that does all the checks. The library's already been audited, so we can know that the code is good, and then we make sure that the verification passes. And in all, I think this ends up being looks like 30 lines of code. And then finally, we take the blocks, we hash them, and then we use the alloy types to basically get a solidity struct. We ABI encode it, and then we expose it as a public output of our proof that we want to use on chain. So let's look at the numbers. Okay, on the left-hand side, we have our old system, Tendermint-like client with circuits. As I mentioned, it took 3 engineers on our team, 5 months end-to-end. It was very painful. It was thousands of lines of code. And the audit costs were actually pretty high. We spent a couple $100K all in for the whole system. And it also took a really long time to audit it. So once we got it done, we couldn't use it in prod right away. We had to wait another month and a half. And it's very complex. There's many teams that wanted to fork it and use it because a lot of teams use Tendermint, and they were kind of unable to really do that because it was very difficult. With SP1 Tendermint, it was a magical developer experience. We just imported this library. It's 50 lines of code. It took 1 engineer on our team 3 hours. I actually think is maybe our intern. And the audit cost, I mean, there's barely anything to audit. It maybe takes 1 day. And it's extremely simple. It's super forkable and customizable. And actually, recently, we hosted a workshop on SP1 Tendermint, and we had 50 people show up, and now dozens of teams are taking it and forking it and experimenting it for their own use case or their own chain, which is super awesome. And I think this customizability is really important for the modular ecosystem, especially when you have this world where people are customizing things and really taking advantage of the flexibility of the modular paradigm. They really need this ease of use to customize things to their own use case, and that's very powerful with SP1. Now, you might say, okay, well, the developer experience on this side seems like 100x better, so surely that comes with some trade-offs. Like maybe the proving time is really horrible. But that actually wasn't the case. And this was even surprising to someone like myself. So on the left-hand side, in our old circuit world, we spent months and months getting the proof times down to 10 minutes and the proof cost down to several dollars. And we were actually really proud of that. We'd worked really hard to get to that point. Now with SP1, we thought we could maybe never achieve those numbers. We were hoping to be within a factor of 2 or 3. But actually, to my surprise, with SP1 and all the optimizations in SP1 GPU, actually the proof latency ends up being 2 minutes. So it's actually an improvement. And the proof cost actually ends up being significantly cheaper as well. So you might ask, why is that? And the reason is because SP1 is so general and can support so many different use cases by so many different teams because it's so flexible and customizable, on our end, we can spend all this time and effort making a really optimized system and really making it as performant as possible because the ROI is so high. For example, in our old system, it would have never made sense to put our Plonky 2 Tendermint-like client on GPU. It would have just been way too much engineering effort for only one use case and one project. But with SP1, we know that every time we improve it by 10%, all the teams building on top of us also benefit. And then I also want to talk about something that's very, very relevant to the modular ecosystem, which is rollups. I think the biggest use case of ZK in the next year is going to be ZK rollups, and I think all of them are going to be built with ZK VMs, hopefully on SP1. So for example, we ran ref within SP1, and we benchmarked the proving time and the proving cost. And we found that the proving cost per transaction currently, and this is without the GPU stuff, which makes things better by a factor of 5, is around 1 cent per transaction. Already, that's getting pretty cheap, especially when you look at how much Ethereum rollups are paying to Ethereum for DA today. And so I think in the future, all modular rollups, all rollups in the modular ecosystem will be built on top of these ZK VMs, and they can customize their execution environment to whatever they want, which is really powerful. And to wrap up, I want to say that with SP1, ZK is going to go mainstream finally. It's easy, it's very fast, it's cheap, and it's really flexible. And I think with that, we'll finally have accessible ZK, and that will allow the modular stack to have good UX, because ZK will be easy enough to use in all the contexts that it needs to be used, and then that will lead to great interoperability, all rollups being ZK rollups. They will all be connected and talk to each other, and the liquidity will be unified, the ecosystems will be united, and finally, users will have the good experiences that will, be really good for the entirety of the space. That's all. Thank you.
Thank you. Wait, Uma, we have some time for questions, so maybe there is some. Yeah, we have one question. Can you wait for the microphone?
That's fine.
Yeah.
What part of the modular stack do you think is, I guess, most important, or which part of the stack will ZK, in your view, play the most important role, or which part is needed by the presence of ZK the most, and kind of why?
Yeah, I think the rollup, it's rollups all the way down. Like, I think today you have all these different rollups in the modular stack. I mean, even in Ethereum, and they just can't talk to each other. Like, liquidity is so fragmented, and it's, you know, you need this complex infrastructure and ecosystem of like fast bridging layers and liquidity layers and relayers and this and that. And it's all just very complex, and it all just doesn't work that well. And I think fundamentally the problem is it doesn't scale. Like, maybe this would work if we had 5 rollups, but in a world of 1,000 rollups, or I know Ishmael was talking about like 1,000,000 rollups, that just having all this complicated middleware is just not going to scale. And I think the only thing that really will scale is verifiable compute, which is ZK. And so I imagine a vision where every rollup has a ZK proof being generated very fast alongside the chain. And then if 2 rollups want to talk to each other, you want to do bridging or interop between them, you just verify the ZK proof of rollup A on rollup B and vice versa. And it all just kind of works without need for much more complicated infrastructure. Like, the ZK just hides, just makes everything verifiable and be able to talk to each other.
So like generally like interoperability and kind of like message passing between rollups as like the most important part. When it comes to the current paradigm, I think like it's pretty intent-based dominated. I would say is like the ideal interoperability structure, at least for asset passing. How long do you think this intent-based paradigm will reign, I guess, supreme until this ZK-based interoperability concept becomes a far better option?
Well, I think the intent-based paradigm and ZK is actually super synergistic. So like, the intent-based paradigm means that like the user specifies their intention, and then all the bridging and asset movement is abstracted below them. But at some point, the assets actually do have to settle. Like, you actually have to execute the bridge transaction. You do actually have to move stuff around. And today, like, the people fulfilling the intents really feel the pain of optimistic systems. They have to wait 7 days. Their liquidity is locked up. There's a huge cost of capital. With ZK, it goes from 7 days to like a few minutes. And so I think basically the ZK paradigm will make the intent-based paradigm a lot more efficient and a lot more practical.
Thank you. We don't have time for much questions. So once again, big round of applause for Uma. And right now, there is our next speaker, James Presswich from Init4. This is the research collective building next generation of Ethereum. They are, for example, co-architected the execution extensions to Ref, and he'll tell you a bit more about client monogamy. Big round of applause.
All right. So I kind of lied a little bit to the organizers and told them this was a talk about client diversity, which is a common Ethereum concept. So first off, let's introduce me. I'm James. I work on Ethereum things for the last, I don't know, like close to 10 years or something. I worked on Bitcoin stuff before Ethereum was around, and now I spend most of my time doing roll-ups, bridges, cross-chain things, and mechanism design, writing, and being really annoying on Twitter. So why do I care about this? There's been this idea since the beginning of Ethereum that you should have a lot of clients. You should have Aleph and Parity client, and maybe like whatever Gavin was working on back in the day, and Geth and Reth and Nethermind and Aragon and Akula, and client diversity. So this is from yesterday. Like, client diversity is a measurement of how many pieces of software did we build to do the exact same thing, and how many people run each individual piece. And what are the philosophical implications of me forgetting to finish the slide? I don't know. So you might notice a few things about this. It makes you feel a little anxious, a little scared, a little irresponsible. Like, it's got this, wait, do I have a laser pointer here? Don't think so. Damn. It's got this like, uh-oh emoji, and it's got like this big red bar here. And it does like this weird thing where it just assumes everything is what you don't want, which is a very normal statistical methodology, just assume the bad case. Oops. There we go. The same page like has this big danger warning, like we're above 50%, we're in danger. And then I clicked on this like link here, view staking pool diversity, because I was interested in that. Like I want to know who's got money and what the money's doing and who's in charge of it. And yeah, that's an ad. It just goes to someone's website. They're trying to sell you data analytics. And they fucking got me. So the way I found this was just Googling client diversity, because I have no idea what I'm saying up here. This is the Google results for client diversity. You may notice something like, this is the official Ethereum website, and this is some random guy's ad. And one of them shows up on top when you search client diversity. So I don't know why they have the same logo or what's going on here, but the important part is that client diversity is scary. Like, it's a political goal that there should be more Ethereum nodes, that people should write geth and reth and whatever. And it's also the assertion that you, as the user running software, should make a different choice based on what's politically good for the network. And I think that's a bit weird, that they're telling you that you should just stop running geth because there's too many geth nodes, and that's your fault. But this isn't to talk about client diversity. Like I said, I lied to the organizers. So this is a talk about client monogamy. You got to just settle down and marry one. And I'm James Prestwich, and I've been working on Ethereum stuff for close to 10 years now. Before that, I worked on Bitcoin stuff for a bit. And why do I care about this? I have to ship code. I worked on this thing called Alloy. Alloy gets used by Foundry and by Reth and by a bunch of other people. I worked on a bunch of different bridges. I've shipped a lot of code over the years. And all of the code does one thing. Like, it does what an app does. It talks to the node. Like, this is what an app does. The client sends requests to the node sends responses back. The general format is the app is going to wait for a block, do something with the block, and then repeat that forever and never stop. If your app stops, that means something's gone very wrong and you're very unhappy and you have to do a bunch of ops things and no one likes that. So the problem is that while the app is talking to the node is talking to the network, and things are happening. And the client talking to the node is this nice, consistent JSON RPC that usually works, but sometimes doesn't. But the node talking to the network is an absolute mess. And the node talking to the network is going to get new blocks. And maybe it's going to get a new block, like right here, between these two client requests. And then, something different is going to happen. And the client doesn't know the node got a new block unless it specifically asks if it got a new block. So because these are separated by time, if you ask about the block over there and then you get it back over here, you got a different block, and you don't know. So here's an app, like when you try to actually make one, you're going to ask the node what the block is. You're going to see if you have missing blocks, like if the node knows of blocks you don't. You might go, oh, fuck, and have to try to get all of those missing blocks, and then you want to process them. And then, wait, sorry, the node has a new block now, and you have to undo all of the stuff you just did and go back to the beginning and repeat this forever. It's not a good pattern to write. This is what every weird JavaScript UI does behind the scenes. It's asking MetaMask what blocks it's got. It's trying to keep consistent. It's trying to see what the chain is doing. It's trying to process stuff, and it's just failing, and it's all a mess. So the problem, like I said earlier, is that anything can change on the node at any time. So when you're writing your app has to account for the idea that the node has reorged 20 blocks while your app was running, which means your app has to then internally reorg 20 blocks, and that kind of sucks. That's incredibly complicated code to write. Any hands for people who've written reorg logic in chat? Yes. What's up, dude? Nobody likes it. Nobody does it. And as a result, apps are very unreliable. And the root cause is the JSON RPC. So the third time you make an app, you're going to make something like this. You're going to have two separate tasks, one of which is polling for new blocks, is making an organized model of the chain locally in your app, and then is externalizing blocks. And then another task that's your working loop that's waiting for work from the polling task, and does the work, sees if it's still valid, and then commits it. And both of those tasks are going to repeat forever. And if they crash, something's wrong and you're having a bad day. So why not use the notifications? I know some of you have written stuff with Infura and you know about the streaming API. Well, I have bad news. You expect them to work kind of like this, where you're learning about transactions or blocks from the network, and the client receives them right after the node does. But they actually work kind of like this, where sometimes blocks will just disappear somewhere between the network, the node, and the client. No client reliably notifies you of all information you've subscribed to. Any subscription may be missing random events from the middle. Nodes just don't work sometimes, especially over JSON RPC. And we discovered this with a lot of trauma. So like I said earlier, I maintained this thing called Alloy. Alloy came out of Ethers RS. And in Ethers RS, we had this like pending transaction system. The idea was you should be able to broadcast a transaction, and you should be able to wait till it confirms. It's really simple, right? Well, you think it's really simple until you actually try to do it. And then you find out that none of the nodes work. And Infura will take your transaction, but then tell you it doesn't have it. And everything's just kind of terrible all the time. And so as the pending transaction loop got bigger and bigger, we eventually decided to just not fix it and do a complete rewrite of Ethers from the ground up. And the new one's somewhat better, but it still uses JSON RPC, and it still has to account for the idea that sometimes the node just lies to you. And different nodes lie in different ways. So for example, Aragon has had a long-standing bug where it just returns incorrect results on some RPC calls for no reason. You ask for a receipt, you might get a different receipt. That's great. So the 15th time you make an app, you just fork Geth. You just fork it. You build your app into Geth. But why? So a node is a piece of software that is specifically written to wait for blocks and then do something with the block, and to repeat that forever, which is the exact same loop that you want your app to do. And the node has like people who have specialized in writing this reorg logic for you, because it has to, because it's a full node, it has to track the chain, so it has to handle reorgs. And so why don't you just make your app into a component of a node? The node is doing the hard parts, the complicated stuff. Your app should not have to track reorgs. There is a piece of software dedicated to doing that. So eventually, as you get better or bigger or more professional, you start forking nodes in order to write your applications. It is the only way to get reliable infrastructure. You cannot make something reliable over JSON RPC. It just doesn't work. The nodes themselves, the JSON RPC servers, aren't reliable. And you have all of these timing issues we talked about earlier. So the only way to like go for high reliability is to build into the node. You see this from Etherscan, from essentially every like significant block explorer. You see this from things like Infura or Alchemy. They modify their node software. Infura and Alchemy go steps further and add like balancing layers and other like infrastructure things around the node software. They don't try to use the JSON RPC. It's not good, it's not reliable. So apps are just better when they're running as a component of the node. It's, you know, at this point, like it's unavoidable, it's a well-established fact. Once you get professional enough, you fork Geth, or you fork Breath, or Nethermind, or whatever other flavor you like. And then there's no inconsistent state ever, because there's never a time lag between when the node learns about something and when the app learns about it. You avoid this entire class of problems. You never have to reorg because the node is reorging for you, and the node gives you a nice little piece of memory that says, hey, we reorged, and you can just handle it. You don't have to ask the node if it is reorged. You don't have to backfill any blocks. The node just gives you that. So when you're writing your app, you can just cut out the whole pulling loop, all of the chain state tracking, all of the reorg monitoring, and just go to workers. You can put all of your engineers on working on your app instead of half of them, because you no longer have to maintain half a full node in JavaScript. And that's pretty great. So this brings us to client monogamy. I'm James Prestwich. I've worked on Ethereum for a few years now. And unfortunately, I have to run a company sometimes. I have to pay people. Some of the people write software. I write software. I have to pay me sometimes. Software engineers need to eat and need health insurance if you're in the US, so that's kind of expensive too. And I can't spend my money rebuilding my app to be part of Geth, and then wait, the network's not diverse enough. I can't just spend the same amount of money again, fire all my Go engineers, hire a bunch of Rust engineers, and rebuild it to work with Reth, because the network's not diverse enough. Client diversity is only for end users. Like, it's only for the hobbyists at home. Real businesses cannot support client diversity because we have to pay people. We have to build our application. We have to marry a node. So if an app is a node component, you'd have to rewrite that app for each node if you want to be able to switch. So, like, things I will not be doing is rewriting my entire app to switch nodes. Once I have built an application, once I've built the validator service, once I've built the rollup, I will not be spending the same amount of money again to rewrite it for a new node. I am now married to the node that I chose. And diversity, like, doesn't even come into it. Even if I want client diversity, I no longer have that option as a business. Every significant business in the space chooses a node and sticks with it. Client diversity is for people who are not being paid to work on this. So 95% of companies are not going to rewrite their entire app. They are married to their node. And if you want to professionalize your company, if you want to professionalize your application, if you want high uptime and high availability, you have to do this too. You have to settle down, marry a node. So these systems exist. There are interfaces in both Geth and Reth for modular extensions. I helped design the Reth one and did a little bit of implementation on it. But you know, there aren't any takeaways here. You have tension between the network's goals to be diverse and your goals as an individual who has to spend time and money building something. Any questions?
So a lot of this conversation was about applications, but I think most people view client diversity as a way of reducing risk on the network from a validator perspective. So when you talk about needing to marry a client, how do you reconcile that? Are you talking on the application layer specifically, or do you include that with validators somehow?
A validator is a specific application, right? Like, the validator is waiting for a block, doing something with the block, attesting it maybe, and then waiting for the next one. A validator is running this exact same loop. And a validator has to make the exact same choice here. Do I go over JSON RPC and potentially miss blocks and have impacts on my revenue because of lower availability? Or do I build my validation logic into a full node as a component? Client diversity is not necessarily about the validator set per se. It's about mitigating the impact of consensus issues on the network. Consensus issues are unavoidable. Ethereum has had at least 3. Bitcoin's had at least 1 major one between 07 and 08. Last year we had one that was not a consensus issue but did prevent finalization. That was when one CL client accidentally DOS'd all the other CL clients. Diversity is about mitigating that specific impact of these events we know will happen infrequently on the network. Diversity also happens to increase the frequency at which these events happen And the goal is that if you are sufficiently diverse, the impact will be lower at each event, even though there are more events, and that will pay for itself. Whether you believe that or not is a separate question that this talk isn't about.
Thank you very much, James. Once again, big round of applause. And our next speaker is Mark Tanaway, the co-founder of Optimism. He'll tell you a bit more about the superchain and OP stack interoperability. Big round of applause.
Hello, hello, hello. So my name is Mark, and I'm a contributor to the Optimism Collective. And today we're going to talk about putting super in the superchain, right? So what does this mean, right? So my claim is that we're not going to make it unless we overhaul the way that users interact with blockchains, right? So here we are as Ethereum, as the community, right? Vitalik is talking about all of the historical things that, all the historical problems that we've solved, right? And this is where we are now, right? Cross L2 UX is too fragmented. So that's what I mean by, talking about putting the super in the superchain. So here's Peter. He's talking about how, he's having UX horrors of crossing between L2s. He currently has Ether on OP mainnet, and he needs base ETH to, and then he needs to go over to Zora to mint an NFT. So he's asking, can the devs do something, right? This is right here. This is our attempt to do something. So our goal is to make the superchain feel like one chain. Cool. So let's put on our archaeology hat, because they say that, a lot of computer science is just archaeology. Like all of these problems, these hard problems have just been solved. We kind of have to just go look at the past, kind of dig up some old secrets, apply them to the new problems. So, okay, we're in this mysterious old ancient ruins, and let's explore a little bit. Okay, we found a treasure chest. Okay, so wonder what's inside. Okay, okay, designing data-intensive applications. This is some great wisdom from, the Web 2 world that, we kind of forgot about here in crypto. So, I'd like to ask the question, maybe we should be thinking of chains as horizontally scalable microservices in a wider microservice architecture. So, I'm going to be talking about interoperability today. And the first thing I'd like to talk about is, the product. Because one thing that this industry likes to do is we like to focus on crazy technology, right? We like to talk about the solutions, the infrastructure, but really we got to focus on the users, right? We got to solve problems for users, because otherwise our really interesting technology is never going to get used and we won't be able to continue working on it. So, secure, portable, fungible ERC20 tokens. So, we are making yet another token standard called Superchain ERC20, and it's a small extension to the ERC20 standard, but the idea is that any of the assets you've deposited to OP mainnet, Base, or any of the other chains will be able to seamlessly migrate to a new ERC20 token standard that will allow them to be fungible across all the chains that are interoperable, right? Without cross-chain liquidity constraints. So you're asking, why are these people creating yet another standard? There's already a million standards, right? Why? So, you can use XERC20. It's a free standard. It's very flexible to work with many bridges. You can easily build this right on top of the low-level abstractions that we're providing if you prefer this. Cool. So after talking about, the kind of product side of things, right? We want to allow cross-chain portable ERC20 tokens. Now let's talk about the secure message passing, right? This is where it gets fun. It's more protocol stuff. So let's talk about our design philosophy first, right? So one big thing that we always think about when working on the OP stack is the minimal diff, right? And George Hotz gave us this advice. He said, focus on the minimal diff because there's always bugs in your code. And the more lines of code that you write, the higher chance that there's going to be bugs in it. So write less lines of code, right? And whether you love George or not, he's an interesting and controversial person. He's out there, he's doing cool things. There should be more people doing like epic things like him. So also we want it to be flexible, right? What does this mean? It means that we want it to be able to be used in many different ways. We don't want to enshrine too many opinions about the design, right? And we want it to just work with existing applications. What does that mean? That means that if you've already deployed applications to OP mainnet base or the other chains, you should be able to instantly start exporting your data to other chains. In importing data, you don't need to necessarily plug into, say, a new system to be interoperable. And we also want it to be simple to reason about. So one good thing to focus on is if you're designing a protocol, you want the design to be very small so that you can fit it all on your head, right? Because as soon as something becomes too complicated to fit in your head, then that's where problems arise and you can introduce bugs. So we're focusing on simplicity here. And I'm going to start with some vocabulary so that we can all kind of align our mental models and think about this. So the first thing that we want to talk about is this idea of a dependency set, right? The dependency set, as a chain operator, you get to manage your dependency set. You get to basically say, these are the sets of chains that I would like to accept inbound messages from. And any chain has the right to define this. Then we have this initiating message, right? So an initiating message, and then there's an executing message that goes along with it, right? These two together make the full cross-chain, message. So an initiating message is simply a log, right? Very simple. There's like nothing more to it. It's just a log, right? Like Ethereum, like in Solidity, you can like emit events, right? That's like, those are creating logs within the protocol. And then we have this idea of an executing message, right? So the executing message is represented as a log on the remote chain, right? We have this source chain and a remote chain, right? The initiating message is created on the source chain. The executing message is created on the destination chain. And the idea is that the executing message includes the initiating message as well as a unique identifier for that initiating message. So getting into the user experience, right? There's a total of 2 transactions that are sent, right? We have this log, which is the initiating message. It's created on the source chain. And then that initiating message is sent into the destination chain, right? So this, you can kind of think of it as like you're able to teleport an event that your smart contract has emitted into another chain. So you can introspect on the events of other chains. And we believe that in practice, what will likely happen is a relayer system will exist and send the second transaction on behalf of users. So the ideal user experience is the user really just sends one transaction, and then some sort of solver network exists and ends up sending the executing message. And the user can kind of get this feel of just sending a single transaction, and it feels just like how L1 feels. So the dependency set. I mentioned this before. Each chain can define their own dependency set. And this is all managed on-chain. And this relationship is unidirectional. So what that means is it's permissionless for anyone to accept inbound messages from your chain. You don't need to convince the other chain to also accept inbound messages from you. You can just, turn on your chain and then, define the chains that you want to, depend on as part of your dependency set, and then start accepting inbound messages from them. So the initiating message, right? we spoke about this a little bit before. Literally any log can be an initiating message. So this is very simple, very simple. You don't need to do any extra integrations. All the applications today already emit logs. Now we have the executing message. So I'll start off by talking about the invariant that makes this all work. So, because it's like really useful to think about, if you're designing a protocol, thinking in terms of invariants. Everything is just invariants in state machines. And if you define all your invariants up front, then you can be sure that your system is secure. So we're gonna think about the invariant here, right? The invariant is that all executing messages must have an initiating message that matches its identifier. So what does that mean, right? So the executing message is this tuple of the initiating message and its identifier, and this is the definition of an identifier. So the identifier is able to uniquely identify a log. So what information do you need to do this? You need a block number, you need a chain ID, and you need a log index, right? The chain ID tells you what chain out of all of the chains emitted this log. And then the block number tells you like in what block was this log emitted. And then the log index tells you, because the logs are all ordered, it tells you like which specific log that is like corresponding to, the initiating message, right? So given this identifier, you can look up any log across any chain. So we have this special pre-deploy smart contract, right? The OP stack loves pre-deploys because they're EVM bytecode, right? Instead of like adding new pre-compiles, we add new pre-deploys. And the purpose for this is to like make it seamless to integrate with tools like Foundry, right? You don't need to go and add extra code to Foundry, maintain a Foundry fork, all this stuff just to have your pre-compile work, right? It'll just work. So yeah, basically, the node will observe all of the executing messages and enforce this invariant. So now I'm going to go through these key properties. All right, the shared proof system. Okay, so the shared proof system, right? This is going to be kind of, bundling all the security of the interoperable chains into a single fault proof, right? And why is this important? This is important to reduce platform risk and governance risk, right? When you have different chains that are all operating under different consensus models or have different proof systems, then there's always a risk that that chain, the governance of that chain, will kind of change its rules. And under a shared proof, you kind of enforce that the chains that you're operating with will be working under the same security properties as you. So this gives the property of like fungibility of Ether or ERC20s across all of these chains, right? And just helpful reminder, proofs are useful for withdrawals from the bridge, and the bridge is not the rollup, right? A lot of people have this misconception that if the fault proof removes a claim, because people make claims when they want to withdraw. They say, hey, this is the state of the L2 at this block. And, a ZK rollup will be like, all right, here's my validity proof. And then the bridge is like, okay, I accept that this claim is correct. An optimistic rollup is like, truth comes from lack of disproof, right? So when somebody makes a claim, right, they're like, all right, I claimed this is the state of the L2 at this block height. And if no one is able to disprove that within a time period, then it becomes finalized, right? So if the fault proof, removes a claim from the bridge, it does not cause an L2 reorg. This is like a big misconception because the chain is not, or the bridge is not the rollup. Cool, so let's talk about message integrity, right? Because it seems kind of like, maybe the sequencer can like spoof, these cross-chain transactions. Well, that is not true because we define this in an invariant first way where all of these executing messages events, must be validated as part of the fork choice rule, right? So any block that produces these executing message events, if any of the tuples, the identifier and initiating message pair that's like emitted from this event, if that executing message, if the values in it don't match, then the entire block is considered invalid and reorged out, right? So that means that the sequencers or the block builders are going to always want to only include valid cross-chain transactions. And ultimately, it's like the full node software that protects users here. Also, another feature is like we don't have this idea of like force inclusion for these transactions. There's no idea of sending a L2 to L2 transaction where it's automatically force included into the remote chain, right? You can kind of think of it as it's like kind of like a broadcast UDP sort of system, right? Because if we had force inclusion, it would add a lot of complexity. So you would either need one of two things. You would need to have an awareness of the gas market on the remote chain, or you would need to have an inbound message queue. Both of those are very complex, and simplicity is key. We always use simplicity to drive decision making. So it also reduces this like tight synchrony assumption between all the chains. And it's also backwards compatible, right? So all of the existing applications today already use events. So as soon as this goes live, your application that's already emitting events, all of that information can be consumed on different chains. And an interesting property of this is that as the builders become more sophisticated, or the sequencers, kind of the same thing, but it improves the scalability of this, right? And this very simple low-level protocol could, in theory, be used to build a shared sequencer on top if people want that. So, yeah, we can build kind of like atomic cross-chain transactions on top of this with sequencer confirmation levels of trust, right? So usually, for an L2 builds a block, then the L2 has this idea of like a pre-confirmation or a sequencer confirmation, which is kind of like a pinky promise saying like, this is the data that I'll ultimately submit to the data availability layer, right? So the latency can be extremely low if you trust those sequencer confirmations. But this protocol can be completely trustless as soon as that data is published to the DA layer. So if you're consuming data from a remote chain, as soon as they, batch submit, the inputs, the transactions that, produced the outputs, the logs, as soon as that remote chain batched their data, then you can start consuming it trustlessly, and you don't need to, really trust anything. Cool, so cross-chain messaging, right? So I've been talking about low-level abstractions here. The lowest level abstraction is like broadcast UDP, right? You just like emit an event, and then it kind of just goes out there, and any chain can just choose to like consume it if they want, right? And then we can build higher level abstractions on top of this really simple thing. So we've built a higher level abstraction that gives both replay protection and domain binding. So basically that says like, you can only send this message to a particular chain once. And this is very useful for sending Ether or ERC20s between chains. Cool, so now I'll talk a little bit about contributing, how to build on top or contribute. So at OP Labs, we are committed to working in the public. I think it's very important. All of our specs, open source, free software, all of our project management, all happening on GitHub. You can go right to our GitHub repo and go and look at all of our tickets. And we also have a contributor Discord. So we're kind of looking at how L1 operates. And we think that, by opening up development, it'll help to make it easier for people to contribute and understand what's going on. So if you're interested in joining, come, chat on our GitHub, show that you're adding a little value, and then would love to invite you. And we're currently working on a public DevNet for this, so this is coming soon. And basically, my claim is that we need to enter the world of modular applications, right? So these are horizontally scalable smart contract systems. Like modular has been like the biggest buzzword for the longest time. Everyone's talking about modular data availability, modular execution. Well, now it's time to add another thing to the buzzword. It's modular applications. And when I say application, I mean like, DApp, smart contract. I like calling it app because like what's a DApp? It's an app. But okay, so horizontally scalable smart contract systems. This is I call this like the bring your own gas model, right? So like right now, if you turn on extra servers, you cannot, you can't bring gas to the network. You can't speed up the network by turning on new servers. It's a replicated state machine, right? This is unlike the Web 2 world where you can just turn on more servers and, process, more usage of your application, right? So we want to enter a post-gas scarcity world, right? This is like the broadband moment for crypto, right? So the idea is just to start thinking about blockchains as CPU cores or threads or microservices, right? So in the world of modular apps, what we want to do is we want to look at our smart contracts, see where the gas bottlenecks are, and then we want to redesign our architecture to kind of try to shard the most expensive parts of our applications across multiple chains so that we can easily horizontally scale our applications, right? And this is exactly how Web 2 is able to build for actual global scale. And in the future, we're looking at using, ZK proofs to relax this dependency set constraint. And this will be, realistic once the costs are low enough and we have, proof generation time fast enough. Cool, that's it. Thank you very much.
We have some time for questions, so maybe someone from the audience. So if there is no question, I have a question to you. So you have started with a problem from Peter, that basically you have Ether on multiple chains. How it will be solved?
Totally. So that's a great question. So there will be a very easy way to just send your Ether between, say, OP mainnet and base and other, OP stack chains where it's all secured by the fault proof.
But still, if he wants to use he wanted to use base, I believe. He wanted to use base, I believe, so he'll still need to send between the networks to use it, right?
Totally, totally. But the idea is to work towards a user experience where you say never need to change your network RPC on MetaMask again, right? Because there's no reason why, if you're not using something like a smart contract wallet, you can, you can send a transaction to one chain and basically, call another smart contract on a different chain that does all the things that you want, right? And if we have this relayer system that is able to handle the second transaction in this cross-chain transaction, then really it'll feel much more similar to L1, and you'll be able to take actions on remote chains.
Yeah, now I see. Thank you. Once again, big round of applause for Mark. We don't have much time so we don't have more time for questions. Sorry. So our next speaker will, thank you, Mark. Thank you. So our next speaker, Alex, is a little bit late, so we'll need to wait a few seconds or a few minutes for him. So to give a little introduction, he's a founder of Matter Labs. They have created ZK Sync Lite and ZK Sync Era, which is a ZK EVM rollup. And basically, he'll talk today about elastic chains.
where they claim that they will create ZK chains providing native interoperability. And right now we need to wait a few minutes for Alex because he's lost somewhere in the venue. So please stay with us for a few minutes and Alex will be there.
Okay, so let's welcome Alex on stage.
Hello, everyone. Sorry for the delay. We got messed up the presentation, so I'm just going to start without it. I'm Alex Gluchovsky from Meta Labs, founder CEO of Meta Labs, and one of the creators of ZK Sync. And you probably know ZK Sync. It's arguably the most mature ZK rollup stack in Ethereum today, with by far the most number of transactions in production. There was a recent airdrop, and after the airdrop, we still remain very high on the number of active users. So, okay, I can now move. Yeah. So, and ZK Sync is most production-ready ZK tag also from the platform perspective, like from the ability to actually handle the high load. But what I want to talk about now is why we're here. I just want to remind everyone why we're here in this space. Crypto can be distracting with all the meme coins and speculation and all these things, and then there's bear market, bull market cycles. Can be a bit depressing, but like the war values that this industry is built on, they were fundamental to Bitcoin, to Ethereum, to sovereign rollups, and to ZK Sync. So ZK Sync is based on the belief that freedom drives progress, unlocks creativity, and which in turn drives prosperity. And our mission has been from the beginning, from 5 years ago, to increase advanced individual freedom by mass adoption of crypto, of blockchain tech. And mass adoption means that first of all, we have some properties that we want to preserve at a huge scale. We have spoken about them in the ZK Credo last year, try to articulate them in precision. I'm really happy to report that a lot of progress have been made specifically on ZK Sync on many of them. Ethereum probably scores higher on most by far, except for hyperscalability, by this ability to actually reach the population of the world. Like we have 5 billion active internet users, and to reach them, just like the internet cannot scale on a single server, the world of blockchains cannot be one blockchain. Like it's inevitable. We all agree that there must be many chains. And this is basically what ZK Sync 3.0, what the Elastic Chain is about. It's a transition from initially the simple payment, application-specific payment ZK rollup to the ZK EVM, the first ZK EVM we launched last year, to now a network of chains, which is very similar to the idea of Cosmos and Polkadot and the sovereign rollup ecosystem, but with a very important distinction. I want to talk about it in technical terms. So that's the Elastic Chain. There are many chains that are connected together at the protocol level natively under a single, uniform intuitive UI. So you have basically the metaphor is elasticity means that the capacity of the system can increase proportional to the demand. And if the demand increases arbitrarily high, the capacity can go basically infinite. You don't need to buy additional drives and attach to your laptop. You can just go to Google Cloud or whatever and have as many documents and as much storage capacity as you need. That's the metaphor. That's what we need to get in order to get to mass adoption of cryptography, of blockchains. And seamless UX means that you have one wallet, one account. You as a user, if we're speaking about the billions of users, normal users, mainstream user, the audience, they should not bother about technological complexities of seed phrases, paying gas, understanding, bridging between chains. Should be like the internet. You have your account, you interact, you just sign. You have your smart wallets, which are natively implemented at ZK Sync, non-natively implemented in Ethereum, and you use biometric keys, full self-custodiality, but very easy to use. And you pay gas in any token you transact with, right? All of that should work cross-chain, but the huge problem of today's cross-chain is that it's fundamentally limited. And I really want us to understand this, but we have very little time, so I don't know how we're going to make it. Distinct blockchains that are not connected together look like a state with a consensus of validators that come to agreement on what the state is. Right? And we have some accounts with some state, And let's imagine we have a separate blockchain and we want to transact. You want to send some native assets from Ethereum to Solana. You can't really do this because there is no native ETH on Solana. So you need to create an asset which is going to be like virtual counterfactual representation of your Ether account. And you need to lock this amount of the token you're going to be sending in the original chain. And then you need somehow to be able to pass messages to unlock it back, to ensure that this is authentic, that this ETH is valid. And this is something we cannot do between separate, disconnected blockchains. Because if you take IBC paradigm, for example, from Cosmos, which says like, okay, we have consensus there, consensus here, fault Byzantine, fault tolerance, we can just send messages that attest that we have a majority of the validators signing this, right? And then the other blockchain will accept that, will verify signatures and unlock the funds. The problem is it's not the full picture. You don't see all the full nodes of all of both chains that have subjective view on what consensus really means. Like, they are far more important than your validators because they enforce the security, the validity of the system, even if the validators are malicious. And that is very, very important. That is what gives you sovereignty, not the economic security of, oh, we have so much stake in the validators. And this, like, those guys all would have to trust the other blockchain from where the bridging is coming, or like between the two blockchains, the bridging is working. But that does not scale for 5 billion people, because if you have thousands of permissionless blockchains, like sovereign rollups, separate blockchains, whatever, like non-sovereign rollup, you cannot subjectively convince all of the full nodes that they can trust completely unknown entities that operate those chains. Like, that just doesn't scale. Like, you cannot pass a message from the upper left corner to this, to this, to this, because you don't know what's in between. It's like sending an internet message from your laptop to your bank without SSL, without cryptographic authenticity of the message. Like, you don't know who's in between, who's going to do something malicious and replace your message with something invalid. And with rollups that settle on a single layer 1, the problem is slightly different. You can pass messages, and you need, like, it's very important. You can pass messages by making a commitment to the layer 1, and in reading this commitment from another layer 2. It requires to have ZK proofs. Like, you can only do it like efficiently between ZK rollups. You cannot do it with optimistic rollups because you have to wait 7 days for finality. It doesn't matter if you do it on layer 1 to layer 3s, settling on layer 2s. You will still have the 7 days finality for objective machine-to-machine verifiability of what's the correct state. But let's assume we have 2 ZK rollups. That still is not sufficient because you have all of the balances of native assets from one rollup and another rollup stored in separate smart contracts on your layer 1. And so if you want to send the assets, you would need to update those balances. And that means transactions on layer 1. And that completely defeats the purpose of the layer 2s, where we have 1 cent per transaction, whereas on Ethereum it's like $10. And now you will have to propagate this $10, and you break the UX, you break the composability, you break the seamlessness of the system, not to mention the costs, which will go exponentially because you have this bottleneck of layer 1. So what do? You need a shared smart contract for those chains. They would need to opt into something shared, which only stores the root hash. Now you can make the changes in the state and only update the root hash, but the assets that are pulled together are remaining in this single contract. And this is what the Elastic chain is about. Like, it's having this, we call it ZK router. It's the single contract that contains all the state. We have ZK gateway, the aggregator that composes the proofs from the chains together, verifies them cryptographically, and then settles on Ethereum. It also does a bunch of things like state recompression, for example, that makes it a lot cheaper for these chains to produce like 1 second blocks, but then settle on Ethereum in bigger batches. But it gives you the ability to transact between any number of these chains seamlessly with full trustlessness, with those chains being completely autonomous. They are operated by separate sequencers, by separate validators, whatever. But from a user perspective, you just have one account. You can access applications on any of those chains, no matter where you are. You don't have to maintain multiple accounts, don't have to bother about gas and so on. And I hope that one day we will have this something like a ZK router Ethereum-wide, where we all agree on some standard. We have some isolation ZK proofs that like guarantee with multi-proofs. We guarantee that the rollups are like not harming each other, and this thing is enshrined in Ethereum. And then we can do it cross rollups, and like all of the entire rollup centric world can interop natively this way. But this is probably much further down the line. I think this it will be like 2-3 years from now. For now, we'll experiment on ZK Sync, and I think we will be the first ecosystem to actually have this native interop live very soon, because now ZK router is live, ZK Sync era is plugged into it, and we have a few dozen ZK chains ready to be deployed this year. They're being built right now. A lot of them, those guys are on the testnet. More are in the building. They will be plugged into the system, and at least they will be connected in the Elastic chain ecosystem that is seamless, trustless, and goes towards the preservation of the cypherpunk values we care about at a global level with billions of users. And it was really cool. Like as a developer, you have a really interesting way to deploy your application on one of these rollups, like on ZK Sync Era, for example, find product market fit, build your community, bootstrap in an easy way. And then once you're big, you need a lot more throughput, you can graduate to becoming your own ZK chain in the Elastic world and have your own token, your own sequencer, your own validators, everything. And that is why ZK is the end game. Thank you.
Thank you, Alex. Yeah, unfortunately, we don't have time for questions, so yeah.
I can wait outside and take questions.
Yeah, you can ask Alex in the venue, for sure. And right now, coming up is the shilling session for Astria by Josh Bowen. Josh, is Josh here? Yeah, Josh is here. So let's give him the round of applause.
Hello, everyone. I'm Josh. I'm the co-founder and CEO at Astria. And so previous talk I gave that's gotten quite popular was titled, We're All Building the Same Thing. That is not what I'm going to talk. Can you guys reset the clock, maybe, just so I know where I'm at from a timing? Talk about, we're all building the same thing. That is not what I'm talking about today. Today, I'm just going to be blatantly shilling Astria, and I think generally I have this shtick of being very forward and very honest, and quite frankly, what I'm here to do today is I'm going to sell Astria to you, and I'm going to talk about what we've done and why we think you should use it or you should be interested in it. So, oh, come on. So what is Astria, right? Astria is a shared sequencer network. We call it the shared sequencer network. This is going to be the bottom of every single slide here. But what does it mean that it's the shared sequencer network? Well, I'll argue that the important part of that is the network bit. So, when we say it's a network, what do we mean? Well, really we mean that this is a network like other blockchains. There's been a lot of talk about I want to decentralize a rollup. Isn't that just making another blockchain? And yes. Making a decentralized sequencer is making another blockchain network. But it's also accurate to say that Astria is a shared sequencing layer. And what do we mean when we say it's a layer here, right? That's somewhat of an overloaded term, right? Is it an L1? Is it an L2? Is it an L3? Is it a layer 0? We use this diagram here. I think this is the simplest way to put it, is that we assume Astria is the sequencing layer which is going to sit in between rollups and in between Celestia as a data availability layer. But it's important to note that Astria is a L1, right? And I think that's something that, if I want people to take anything away from here, fundamentally, Astria is an L1. And that's why we think it's important to call it a shared sequencer network, right? We have a network of nodes. Astria itself is not a roll-up of another chain. It is its own L1. And what are the important parts of being an L1? What does this actually enable us, And we've seen a lot of chatter around base rollups, right? We've seen a lot of discussion about pre-cons for base rollups. And fundamentally, myself and kind of the project downstream from that is opposed to pre-cons. And you've seen a lot of discussion generally from the Paradigm crowd about how we wouldn't need pre-cons for our base rollups if the L1 block time was just faster. And that's exactly what we've been building for the past 18 months. We've been building an L1, explicitly to sequence rollups. And those rollups are fundamentally based rollups of the Astria L1 shared sequencer. And that's what we've done. We're running with around 2-second block times. There's a bit of variance in Comet BFT. And we're running, using Comet BFT, we get single slot finality. And we think that is the optimal architecture to give you decentralized liveness guarantees with a rollup and a high quality user experience. Astria is also kind of a settlement layer, right? And this is a word that's been overused a bunch and it's somewhat confusing, but generally when we say settlement layer, we mean bridging. And what do we mean when we say Astria also supports bridging? Well, again, it's an L1. It has its own consensus set. It has its own state machine in it. And so what bridging on Astria looks like is you can have rollup number 1 and you can have rollup number 2, and they're going to have these bridge accounts inside of the Astria shared sequencer state machine. And structurally, this is very, very similar to what you would have on an Optimism or an Arbitrum, where you're going to have a smart contract, and that smart contract is going to be looked at. It's going to be watched by the rollup node, and that rollup node is going to derive information out of that contract. And what this enables people to do is to have multiple rollups using the same shared sequencer as based rollups, and they can do a withdrawal from their rollup. It will result in funds appearing on the shared sequencer, like their base layer, right? They can then transfer those funds to a different bridge account, and those funds will immediately be derived into the other rollup, right? And so this is, the set of things that we are providing with Astria that we think makes it a great platform to build rollups on top of. So why did we build Astria, though? And when people say, why Astria, why that really what they're often asking is why not X? Why not some other thing that is not Astria? And generally, a lot of times this is going to be why not Ethereum, right? We're at the Modular Summit. Thank you, Maven 11. Thank you, Celestia. And a lot of times in this kind of modular space, in this Celestia native space, we get the question of why are you doing a new thing? Why are you not doing 4844? Why are you not working on danksharding? Why did you make a new thing? And fundamentally, I joined Celestia as a relatively early employee in 2021 when Celestia was not that well known. And so a lot of people say, well, look, Celestia is still kind of new. Celestia has a relatively low FDV, a relatively low TVL. It's a relatively new token. Why would you not just use Ethereum? And from my perspective, as someone who was a very early kind of person to make a commitment to Celestia, Celestia looks really, really good today relative to when I made a kind of large commitment to work on Celestia. And the reason I picked Celestia is fundamentally the people at Celestia invented this concept of data availability sampling. And I think it's important that we look to what the people who invent these concepts are going to do with them and have brought data availability sampling to market as like the first blockchain to support that. And fundamentally, I think there's value in building on an upstart project and being willing to make the commitment to a new project and not completely depending on the incumbent perpetually, because that's going to constrain innovation. Now, why not centralized sequencers? Why do we think it's important to have decentralized sequencers? Fundamentally, this is an ideological perspective. You can run a rollup with a centralized sequencer. You can get some decentralization guarantees, mostly in like the safety space, right? To get forced transaction inclusion, whether it's a 12-hour delay, a 24-hour delay, with various kind of safety properties. But from my perspective, and again, my project is generally downstream of that, right? So when I say something, you should generally assume Astria is going to kind of follow that perspective right now. It is not a decentralized project right now. So why don't we do centralized sequencers? Because I think it's important to fundamentally be ideological in this space. The point of working in cryptocurrency is that decentralization is important to us. Decentralization is the point of working in this space. If you want to do centralized things, there's a robust TradFi industry that, quite frankly, has a lot more assets in it, even than the incumbent Ethereums or Solanas of the crypto industry. But we think it's important to be decentralized, and we're willing to be upstarts who are willing to pay a high cost from development, from acquiring new assets, because we think decentralization is important. And from my perspective, I think that extends to liveness guarantees and to exposing it to users. Fundamentally, if you give users a centralized kind of point of interaction with the chain, they will get used to that. And you have abstracted away the reality that decentralization is not free. decentralization has a cost. We're running more nodes. And if you give users a centralized intermediary there, they will think that is what is kind of to be expected. And it's, there's this saying, right? It's hard to convince a man of something if his salary depends on him not being convinced of it, right? I was probably misquoting that, right? But fundamentally, when we have these roles with centralized sequencers, when they think about decentralizing, they've had it on their roadmap for years, they have a revenue stream that they have to come to they have to get comfortable with giving up part of that revenue stream to decentralize. That's not a likely outcome. So we think decentralization is a point. We think it's important. We think it's important for liveness and safety. And we think if you don't do it first, if you aren't decentralized by default, the incentives are such that you're not going to want to do it later. So what have we built at Astria, right? We've built Forma, right? Or we've helped build Forma. We've helped incubate Forma. Forma's a cultural hub of the modular ecosystem. It's been live on its mainnet for a couple of weeks now. It's done several NFT collection mints. It's minted a bunch of NFTs. In general, it's been successful. And Forma is very useful as a demonstration of what I keep saying, these Celestia native rollups, right? That's one of the things we're really focused on, is saying, if you're going to use a new ecosystem, you can't use it halfway and only use Celestia to be alternative DA for an Ethereum-based thing. You are still making significant concessions to the incumbent Ethereum system. And so we think it's important to explore and provide these Celestia native rollups. And so Forma is our kind of first step there, and it's been running on its mainnet for a while. And we're very, very happy with kind of how it's done. We've also made the Astria stack, which fundamentally is what powers Forma. And what do we mean by the Astria stack? We mean fundamentally things like the execution API. And this is a API we've made. It's a gRPC. It's a protobuf API. And it is what rollups use to integrate with Astria. And we made this as an alternative to something like ABCI or something like Ethereum's Engine API. And the reason we did that is fundamentally we think when you're going to be a startup, an upstart against an incumbent, there are lessons to be learned from the incumbents. It's not that their APIs are bad, it's not that they're terrible, but it's that we've seen how they work in practice. And if you're going to bite the bullet and do a new thing, there are things to learn, and you don't have to pay the same cost they have to maintain it. Then we made our own execution API. More importantly, we've made a lot of open source software. And when people talk about decentralization, it's fundamentally my view that the most important part of being decentralized is that your software is open source. And I want to be clear, I mean open source and not source available, right? It's important that if you are making a decentralized project, anyone can come in and use the software you make to innovate on that project, to modify that project, to make an alternative to it. If we're worried about reg risk in this industry, and you are running a BSL license, it's like a business source license, and your entity, whether it's a Delaware C Corp or something else, and your entity is attacked and you're under BSL, you may not be able to open source that license, and people may wait a 2-year clock. So we think the most important thing is that the software is open source. That is the core pillar of decentralization to us. We've also made a lot of developer tooling because we think that's important. And fundamentally, when I joined crypto 3.5 years ago, the state of developer tooling was not good. It's still not great, and it can be better. And again, we're trying to do something from scratch. We're willing to kind of commit a lot of effort to that. And so we think it's important to try to provide a better developer tooling system from the start, right? So one of the big things we've made is the CLI. I think the Astria Go CLI is like the repo name, right? But fundamentally what we've made for the CLI is we've accepted we're in a modular ecosystem, right? And what modular code means for those that may have worked in a space where they worked with like a monolithic code base, they moved to a microservice code base, fundamentally, you need to get comfortable maintaining multiple components. And the way you do this well is you bring your development environment dramatically closer to what your production environment looks like. And so we've built a tool that allows you to run all of the components in the Astria stack locally in like a very easy to use way. If you have the prerequisites like Just and like Go and like Rust and whatever, you can git clone this repo, you can run Astria Go and init, and it will go pull all of the binaries you need, and you can run Astria dev run, and it will run all of the components in our stack. And what this will run is this will run our sequencer app state machine, this will run a Comet BFT instance, this will run Composer, which is functionally the write path relayer between a rollup and Astria, and it will run Conductor, which is the kind of consensus node of the rollup. And we think it's important that this provides a very easy hot pass, something similar to what a lot of web developers and like Web 2 are used to, where you can run a local tool and you go edit your code and it takes you 30 seconds, maybe a minute, to modify your code, save your file, rebuild your code, and redeploy the instance. So we've created a tool that enables you to do that, but in a blockchain modular development environment. And again, this is open source. This is MIT and Apache 2 dual license. If this is useful to your project, it's a relatively generic framework. Our team would be more than happy to talk to you and see how this might be helpful to your team to use a different state machine or to use a different set of componentry, right? We've also built Astria Guess because the state of crypto is what it is. We run EVMs, right? That is the environment that has the most broad kind of developer community, like the best kind of the depths of liquidity in like developer talent. So we've built Astria Guess, which is something that works with the rest of the Astria stack. It is fundamentally our first kind of like audited, committed, like execution environment that integrates with the execution API and the rest of the Astria stack. What about the RAS, right? Back in December, we had a RAS for a moment here, right? This was what the UI looked like. We provided it for free. It was on our DevNet. We ran a large Kubernetes cluster, and we allowed people to enter a name, a rollup ID, and launch a rollup on the shared sequencer. Turns out if you give people a button, you don't charge them any money. You don't make them like log in or anything. You put it on Twitter. A lot of people click the button. We got something like 700 or so attempted deployments on this. About 530 of those kind of half deployed, and about 350 of them total worked. We ran out of IPs in a lot of places. And so why do we not still have the RAS? And fundamentally, that's because we don't think that this one-click deployment is all that valuable because it doesn't allow you to have a differentiated rollup. It says you can easily deploy the same guest node as everyone else. And so that's why we focused a lot more of our developer resources on local development environments like our CLI that more easily allows you to modify your rollup state machine and test that flow very quickly so that you can go deploy it. But I do want to note, we run infrastructure for Forma. We're happy to run infrastructure for you, but we're not going to give you a one-click interface. We're happy to run the infrastructure, but we don't think this long-tail one-click interface of undifferentiated rollups is fundamentally a valuable space to explore. And for the first time here, I'm going to talk about Flame, right? What is Flame? Flame is fundamentally kind of harkening back to like how Astria started. And it started as the Sevmos project when I was at Celestia, right? And the goal here was to get an EVM rollup running on Celestia as a Celestia native rollup. And that's what Flame is. Flame is our in-house rollup that is focused on Celestia native DeFi. And what do I mean by Celestia native DeFi? I mean, this is a rollup that runs on Astria Geth. It runs on the Astria shared sequencer. It writes its data to Celestia. And it uses TIA as its native gas asset. And it's primarily focused on doing DeFi around TIA as the kind of core asset of that ecosystem. Again, a lot of people would say, why would we do that? Why would we not use ETH? Why would we not use Ethereum? There's significantly more assets. And fundamentally, it's because I think it's worthwhile to commit ourselves to contributing to an early ecosystem and being a first mover and seeing what kind of legs Celestia can have. So what's next? We've built a bunch of stuff here, right? Well, we're actively working towards the testnet. We are going towards our kind of final audit in the next couple of days. And when that comes back, we're hoping we're able to move into a kind of testnet phase with a small number of validators. If you are a validator, please do not come talk to me right now. We have picked the testnet validators. We have a very long list of your interests that you have provided, and we have picked the ones we are working with at this moment. We will reach back out to all of you when we are at a second phase. I appreciate the interest, but we're not taking inbound on that right now. And then we're going to move to a mainnet. And that's going to be a more appropriate time for all the validators to come and ping me on Telegram, and we will chat with you then about how we want to pick our mainnet, right? But right now, we just want to get the testnet, we want to make sure it works, and we want to kind of get to market as soon as possible. And then after we get a mainnet out, we're going to work on a Forma migration, because right now, Forma fundamentally runs on its own Astria cluster. Fundamentally, it uses the Astria stack as a centralized sequencer, right? But it does post all of its data to Celestia mainnet. If you want to go to the Selenium block explorer and you go under rollups, Forma is going to be listed there. You can look at all of the blocks it posted since its Genesis block. But we do want to migrate it to the Astria shared sequencer main. And why do we want to migrate it there? Fundamentally, it's so that we can actually explore a lot of the theoretical topics we've talked about when we discuss shared sequencers. Do we want to have interoperability? Can we have interoperability between the rollups? And in our view, the easiest way to actually explore this thesis is to have these two rollups that are built through like partnerships with us or in-house like Flame that allow us to have Forma and Flame living on the same shared sequencer network that both have native bridges through the shared sequencer network, and to kind of explore the actual practical design space of providing a better user experience for interoperability between rollups. And then we're also going to start working on Astria Rest. We've been talking to the Rest team for almost 2 years now. They've gotten to a v1.0, right? We have gotten close to a mainnet, and we think now is the time where it's worthwhile and we have enough kind of bandwidth on an engineering side that we're going to start working on an integration there, and we're very excited for that because we are primarily a Rust-based team, and really our CLI and Geth are kind of the remaining bits of Go code in our stack. So we're very excited to start working on like an Astria Rest as a like replacement for Astria Geth, and then we do intend to migrate both Forma and Flame over to Reth, when the time comes. And then the last bit, we're going to start working on validity proofs, because I'm going to be honest with you, the native bridge that we have in our shared sequencer, it's a multi-sig, or fundamentally it's a threshold signature. We're not going to have fraud proofs. We're going to work towards validity proofs because we think the ZK VMs, most notably Succinct and RISC-0, are at a point where they're getting production ready. RISC-0 is already on a V1, and we're going to start working, again, as we go to mainnet, as we free up bandwidth on engineering, to start building validity proofs and try to get both of these rollups running on mainnet on a shared sequencer with validity proofs. That's my talk.
Yeah, thank you very much. We have time for one more question. Is there anything? Anyone from the audience? So maybe I have a question.
Yep.
Because you state that it will be easy to deploy new rollups. So do you have any goal in mind? How many rollups would you like to see deployed via Astria in, let's say 5 years from now?
I think predicting anything in 5 years in crypto is an insane prospect. I think we want to think more in like 18 months, maybe chunks. And I also don't think optimizing for number of rollups is truly ideal, because the fundamental limitation to our system is going to be the underlying data availability bandwidth. And right now we're constrained by Celestia running 2 megabyte blocks at 11-second block times. That's how much bandwidth we have. Do we want one rollup to take that up? I'm sure Mega East has a perspective on that. Do we want 2 rollups to take that up? Do we want 100 rollups to take that up? I don't really have a strong opinion on that. Fundamentally, we want to saturate all of the high-quality data availability that we have. Whether that is best done through one large rollup, through several rollups, through application-specific rollups, or through general-purpose rollups, we're quite frankly agnostic to that perspective.
Thank you, Josh. One more round of applause. And right now, the next speaker is Namik from MegaEth, and he'll try to answer this question that we are all asking ourselves lately. What is a real-time blockchain? Big round of applause.
Hello. Yo, how's everyone doing? I think it's pretty awesome that you have me talking right after Austria. We have different opinions on sequencers, so that'll be exciting. Big picture, there's just one thing I want you to take away from this presentation. It's that we are taking an extreme approach towards what it means to have a very, very performant environment. We want to scale blockchains, and we're not going to take anything else as a result. A bit about us. We are a team with a pretty strong domain expertise in low latency compute, high performance networking, and just a general spirit, vibes, and technology of blockchains. Why are we actually here? Elong studied low latency compute at Stanford for his PhD. Lei did high throughput networking at MIT for his PhD. Some of you may also know him as one of the co-authors of the famous data availability white paper of Shuyao from Eigenlayer. Shuyao led global business development at Consensus for 6 years. MetaMask, Linea, and Fura. I myself am just like the local degen, right? Did a little bit of venture, investing in infrastructure, ran a prop book in New York trading, and have been an operator in DAOs and companies like Consensus. I think we have a thesis, which you've heard 1 billion times now, which is that L1 blockchains fundamentally cannot scale proportional to the world compute, right? And that's because traditionally, L1s are heterogeneous, right? Nodes are heterogeneous, meaning that ultimately, if you want to be really, really performant, you need to have a beefy node, right? And the beefier a node is, surprise, surprise, the harder it is to decentralize, right? And have many, many participants. There we go. So, I think it's interesting when you look at the actual tasks which a blockchain has to do, and what are the ideal configurations for those tasks to be completed. So we basically have sequencing, execution, dissemination, finalization, as well as validation, right? And in an ideal world, they have different trade-offs. Like for sequencing and execution, you really want to make sure that's a very powerful node, so you have extremely performant block production. For validation, you want that to be as decentralized as humanly possible. What you have is, in traditional heterogeneous architectures, people making decisions on this trade-off curve, right? So here's a very lightweight bunny. It's pretending to be a node that does all of these things. Validation, fantastic. Really, really low cost of entry, very decentralized. Finalization, okay. Okay, sequencing sucks. Execution sucks. It's not very performant. That's Ethereum, right? They made an extreme trade-off. Now you have a substantially beefier bunny, right? Beefy node. Fantastic for execution. Not so good for validation, right? That's Solana. So a lot of people are like, hey, you know, Solana's great, really, really performant, not as decentralized, right? So we take very different approaches, and this is actually because we're in L2. We can actually optimize something called node specialization. The thesis is that instead of having a node be heterogeneous, doing everything, all of those different tasks, why not have particular software and hardware configurations for that particular task, right? And that's effectively what we do. So, you know, imagine a world where each node is specialized and optimized for this task. For sequencing and execution, you have a very, very beefy node, right? And that is not very decentralized. But for validation, you have an extremely lightweight node and many, many, many prover nodes, right? Which are very, very decentralized. What if you could actually optimize the blockchain on a task basis, which is possible for layer 2, and I will explain that momentarily. So this is kind of what we do, right? We have one sequencer, very, very beefy, not at all decentralized, which is able to hit 100K transactions per second. And because it's one centralized node that's been optimized, like 1 millisecond latency, right? We have effectively a wide range of nodes. The long story short is that our provers are actually more decentralized than Ethereum when it comes to the cost of actually being able to participate in the network. So here are the three basic configurations of our sequencer prover, which is currently an optimistic model, and our full node. As you can see, block production, i.e. sequencer, is way beefier than a Solana node, right? But when you look at our basic block validation, it's way, way, way more decentralized and lighter than an Ethereum node. It's kind of doing the best of all worlds, right? Oh, anybody want to see that? I'm seeing some pictures are being taken. There we go. Love fuel. So this is kind of similar to anyone who likes to read Vitalik blog posts, as I'm sure everyone here pretends to do. Back in 2021, he kind of showed this outcome. Hey, what if we just have an optimized model where block production is still centralized, quite honestly pragmatic about it, but you basically have maximizing the block validation in a decentralized manner. And then you obviously, because you're layer 2, you have the intrinsic censorship resistance guarantees that are associated. That's basically what Mega ETH is. What we have to do now, though, is you have a very, very, very optimized piece of the puzzle, i.e. fantastic block production. But it's just one piece of the puzzle, right? And if you don't optimize the rest of the EVM, you end up just having the bottleneck somewhere else. That's not why we're here. We're here to build a real-time blockchain. So here you're going to see a very basic schematic of the Mega ETH architecture. The sequencer is extremely beefy, and that allows us to do additional optimizations. We're able to do JIT compiling and memory computing, as well as parallelization, which is a very popular buzzword these days. Past that, however, we also optimize the prover network, right? We're able to effectively decouple the individual nodes to do a subset of the sequencer's transactions. That means that we don't have to scale the hardware requirements of the prover nodes with that of the sequencer. This is similar to stateless validation. From there, we have our full nodes. Our full node network has a couple of additional optimizations, right? We have our state deltas compressed, as well as the fact that we've rewritten the data state trie. The end result is 100,000 transactions per second, sub-millisecond latency, and 1 millisecond block times. Pretty exciting, and there's a reason why we're able to do this, right? It's because we've taken this idea of node specialization, having every single node do a very particular task, and taken it to the absolute extreme. We can only do this by being a layer 2. We have a couple things that allow us to inherit the security and decentralization of Ethereum, as we ourselves have centralized block production. We have proofs to ensure the sequencer is following the rules. Right? That's initially going to be optimistic because ZK is expensive, but we're very, very excited to be able to switch when the time comes. We have the guaranteed rights of a force exit. Right? If you think the sequencer is being malicious or it's censoring transactions, you can still exit to the L1. And then finally, you have the ability to rotate the sequencer. Right? There is a big difference between decentralizing a sequencer, i.e. multiple sequences running, and you lose all of the performance and latency benefits, and actually rotating who is running the sequencer in some sort of block interval. So I just gave a bunch of fun facts about like MegaETH, how we work, how exciting it is. But at the end of the day, we are way more obsessed with applications than we are boring infrastructure. At least I am. I think MegaETH has become the unlock to be able to build real-time apps. It's the reason why everyone in crypto actually got in here, right? The ability to create peer-to-peer applications that have a permissionless base layer, right? Anyone, anywhere can come and play and learn and grow. So in that regard, we have quite an opinionated approach towards ecosystem development. We think that if you have a real-time blockchain, we need to find people to build real-time applications. And this is an open call. Please reach out. I would love to work with you very, very closely on building real-time apps. You might be a DeFi fan, there's great HFT use cases. You might be way more interested in consumer. Imagine a streaming blockchain where you can basically stream information in 1 millisecond intervals. That's crazy. You can put everything on chain, and there are no trade-offs anymore. Also, like autonomous worlds, allegedly have insane product market fit, even though autonomous worlds themselves do not yet have product market fit. So if anyone here is an AW, do reach out. I'm a very big fan. I think it could be a lot of fun. Here's some use cases, right? So I love the idea of a real-time prediction market. It's a bit silly, but imagine being able to bet on events as they're happening. It could be some sort of reality TV show as opposed to like a long-term presidential election. My personal opinion is people care way more about betting on fun things than they do about betting on like dark, depressing, state of the world things. You can build different kinds of betting products, decentralized racing games. Those are ones I mentioned. But you can build real-time money markets, right? You can finally build a fully on-chain club. You can build a fully on-chain perp dex. These things are actually now possible. You can build a fully on-chain Minecraft. I have a friend who's building that. You can build literally anything your mind has to propose. I'm particularly interested in consumer applications. In the realm of attention monetization, right? I personally think that times of putting $1 in to take $1 out are done. You need to enable people to be able to participate with the blockchain and peer-to-peer networks with things other than capital. So if anyone's ideating about this, doesn't look like it, do let me know. So yeah, I mean, that's me. That's MegaETH. We are on a mission to make Ethereum great again. And yeah, this is a pretty cool Megadev logo / poster that I like.
Thank you very much, Namik. We now have time for some questions. Here, can you wait for the mic, or I can give you mine? Okay.
Hello. And the question will be how it will be compatible, what's the place on Ethereum itself with MegaETH? So how it will be bridging compatible, built around this, around Ethereum, how it will work from your point of view?
Sure. So I think I understand your question. We're fully VM compatible, and we're layer 2. So when you look at bridge flows, it's pretty standard, right? There's a lot of products that are available in the market. I think when it comes to stuff like liquidity, it's also a really strong bonus to be a layer 2, right? An EVM layer 2 is a lot stronger value proposition for liquidity providers and all kinds of players to kind of come and bridge up. Is that what you meant?
So it will be like L2 infrastructure above, on the Ethereum?
Yep.
Okay, thank you.
Cool.
Do we have any other questions?
Yeah, right here.
Yeah, wait for the microphone.
Could you touch again on you mentioned the proving component of the system has some form of, it sounded like kind of like sharded proving or something like that. I was hoping you could just kind of go into a little more depth on how that works and what are does that change the security assumptions at all if you have different pieces of the network being proved separately?
Sure, so, hello? Hello? Can you, there we go. So effectively what we have is one really, really powerful sequencer, right? And it's streaming blocks at lightning speeds. Now, in a traditional architecture, you would have to have these provers who are able to kind of match that level of frequency, which means that you now have really, really beefy prover nodes too, not decentralized whatsoever. So we take a sharding-like approach where each prover node within the prover network does a subset of the transactions of the sequencer in a sharding-like manner.
Is this on? When you talk about proving, because you mentioned that you're going to be doing kind of optimistic security at first, in the optimistic mode, what are those nodes doing? Because I assume they're not generating like ZK proofs.
Yeah, so they're very, very light at this moment, right? That's kind of the situation of how fraud proofs on optimistic architectures work. But very much the case that when effectively the prover costs for ZK architectures go down, we'll be switching literally as soon as possible.
Thank you.
We have time for, wait for the microphone.
Yeah, thanks for your talk. You mentioned you're having one like beefy centralized sequencer. Can you briefly speak on the security element of that? Like, for instance, aren't you able to censor transactions? So what are the security guarantees by having a single sequencer like this?
Yeah, so that's the traditional concern around having a centralized sequencer, right? What we do to mitigate this is a couple things. We'll have a rotational sequencer architecture where not one person is always running the sequencer. The second implication is that in some ways with layer 2, you need to trust the operator a lot more. So you have the ability to force exit back to the L1 via an escape hatch, but there is the risk of like the sequencer behaving maliciously.
Okay, so when you say inherit the security of Ethereum, you mean the ability to exit?
Yes.
Okay.
Any other question? So maybe I have one question from L2Bit perspective. So is your goal to be on top of L2Bit and beat all the other rollups?
I mean, you know, I think that that's a very PvP way of looking at things. Our main focus here is on letting every single person in the world be able to interact with like blockchain properties with no, like when they traditionally couldn't do it, right? Like I grew up in an emerging country. Everyone I know uses Solana because Ethereum is just way too expensive. Also pretty confusing, right? So yeah, I mean, would love to, you know, be on L2Bit, right? And you can learn about all the trade-offs we make, but definitely don't look at it from a we need to be #1 perspective.
Thank you, Namik. One big round of applause. And right now we'll have the panel. The host will be Steffi Dunbar from Fluent. And the talk will be somehow similar to what Namik has been talking about. So whether there should be one big rollup or 1 million rollups. And let's just wait a little bit until we set the stage and we'll briefly start. You are the host?
No.
You are the host, right?
Yeah.
Yeah, so I think you can sit on the left.
On the left? I think everyone will sit on the side of the picture. Okay. Should we start now, or are we starting in a few minutes?
Can start.
Okay.
If everyone is there, you can start. Yeah.
All right. Are you guys everybody ready? All right. Let's do it.
Yeah. Okay. Are we okay? I assume you don't want to be a tiger.
How do you know?
Oh, no one wants to be a paper tiger.
All right, it's on. Hey everyone, thank you so much for being here today. We're going to unpack 1 mega rollup or 1 million rollups. Today we have Shuyo from MegaETH, Azim from Morph, Ben from Starkware, and Marine from Optimism. I'm just going to get us started off like, I guess a little bit of background. Since the rollup-centric roadmap came out in 2020, we've seen hundreds, if not thousands, of rollups just proliferating across the space. Some EVM, just additional execution points for EVM-specific apps, additional rollups that are more so like alt VM or next gen VM, in addition to a bunch of app-specific rollups. We haven't really quite found what the winner is, if there's going to be one, if there's going to be many. And I'm just going to get us started off with like a really straight-to-the-point question. What do we think? 1 rollup or a bunch of rollups? If there is 1 rollup, do we think it's technically feasible to bring all of the world's users on chain in one state machine? Shuyao, let's get started with you.
Oh, it works. Yeah, I mean, I don't think you can have like one roll-up that houses the world's transaction, but I think we need to make that one roll-up, whatever it is, to be as powerful as possible to enable compute-intense application to co-locate. So, I mean, to answer your question, obviously not one roll-up, but we need lots of really powerful blockchains.
So yeah, I'm going to start this by saying I'm the least technical person on my founding team.
Actually, I think I'm the least technical.
I'm the least technical.
Oh,
There's
God.
no way.
But the thing is, our moderator asked us a bunch of pretty technical questions. I'm literally waiting on my Telegram that my CTO can send an answer back to me. So to see me checking my phone is really like I'm too mid-curve for this panel.
I'm so sorry. I didn't mean to at all. I apologize.
So in talking to my CTO, I was actually curious about this myself. And because of these distinct user scenarios, it's definitely not possible on cost security and scalability. And so according to him, this is definitely not something that's going to happen.
Yeah, so I think at least thinking about the L2 as being able to house, the world's transactions as at least, an interesting thought experiment. And it takes you down the path of, the L2 needs to be as scalable as possible. So, we believe that's obviously with Stark's scale logarithmically with the more transaction data. So, I mean, you definitely need to build your stack. I mean, we think that you need to build your stack in that direction of one rollup while still opening the door for, different ways to enable app chains.
Yeah, I mean, I think plus one to what we said, right? I think we agree there isn't going to be a single roll-up. We've already seen right now with the market that there is a need for multiple roll-up and different types of roll-up. It's sort of how do you enable all these use cases to easily build and then interact with one another, both within the same stack and across different stacks, I would think.
All right, so I think we all agree, probably multiple roll-ups. I'm not exactly sure how many, but obviously each roll-up is going to have like a different flavor, some of which are general purpose, something like optimism, and others of which are more so focused on a specific sector, like consumer for Morph. Curious to see how you guys think about that, and like what might be the winning strategy as a roll-up. Why do you choose to go more so to the general purpose route, or more so specific to a particular ecosystem or a particular type of application? Feel free, anyone can get us started. Maybe Ben, you want to get us started with that question?
Sure. If you're an app and you're looking at the landscape of everything, you really need to understand if you need composability with other smart contracts on chain. If you do, and you also care about things like economic security guarantees of the base layer, you're probably going to deploy it to a big L2. If you don't need composability quite as much, then you're looking at an app chain. You can also get other different trade-offs like extremely high throughput, extremely low transaction price. You have a lot more control over the knobs of your app chain if you go the L3 route.
Maybe Shuyao, curious about your chain. Or I'm assuming you're creating an L2. Is that correct? Meg ETH is going to be an L2?
Yes. Well, we are using Ethereum security. Yes.
Okay, great. So I'm just curious, just curious. I know performance, right? And that you're talking about having really high performant environment. Are you thinking of focusing on a specific type of use case, or more so just enabling like any type of use case? And why would you do one or the other?
Yeah, so I think about how I got into crypto in 2017, and I think actually everyone wonders like the question of why blockchain, right? And I think the core tenet to my thesis is interoperability and having application to co-locate, to explore capital efficiency, and to create new marketplace. So with that interoperability thesis as in mind, I actually don't think you need application that just live on their own single chain and doesn't have to be interactive with other applications. I think that's Web2 applications. So if you want to be qualified for Web3 applications, you need to interop with others. So that's why we're building a general purpose rollup that is extremely powerful. We call ourselves the first real-time blockchain because we have extremely low latency, so some millisecond. In comparison, right, Solana has 400 milliseconds. And with our blockchain, you can actually have a lot of like compute intense consumer applications. Well, the consumer guy is sitting next to me, so I think you have to answer this question afterwards. And then, so that gives you the Web 2 experiences, right, without losing the Web 3 interoperability.
And, oh, did you want to? No, I was just going to disagree a tiny bit on a point that, what doesn't constitute Web 3 would be automatically Web 2. Things like, for example, autonomous worlds, I think, have like app chains that has a very direct thesis as to why it should be a Web 3 application and use case. And I think that's a very, interesting use case for Web 3 applications, right? That doesn't need to be a general purpose rollup, for example.
But the synergy you can explore, for example, with a fully on-chain game. So there's a team called Biome. They're building a fully on-chain Minecraft. And yes, it can exist in their own environment. But if you put it in a general purpose chain, that autonomous world can interact with a lot of primitives that is equally in the same general purpose rollup, right? So think about, like, there's a random meme coin that gets launched in the rollup. And that meme coin, perhaps some of them enter the autonomous world and someone start hoarding, I don't know, Red Hat, and then somehow this meme coin just became really popular, and you can start a, I don't know, Red Hat bank in autonomous world. So I think, and that's really where you create magic and imagination when you have applications co-locate.
Yeah, similarly, we went general purpose because it'd be easier for the smart contract protocols to interact with each other as opposed to different roll-ups on it. And gaming was one of the specific ones where we looked DeFi infra could be used for in-game tokens or NFTs using DEXs and NFT marketplaces as opposed to doing it a different way. And so we thought it would just make a more diverse ecosystem that way.
So I guess the benefits of obviously sharing a chain are like the real-time atomic composability, but at the same time you have more expressivity when you're creating an app chain. So I'm curious, like, I know that for Starkware and for Optimism, you're looking into L2 and L3 ecosystems, of which you can choose either being deployed directly to the L2 and taking advantage of the atomic composability, or going your own way and creating your own rollup. I'm curious, what do you think is an app then that would be best suited for an app chain environment or an L3 as opposed to deploying as a smart contract? Maureen, we can start with you.
Yeah, for sure. So I think, as you said, right, it's kind of like the expressivity, like what you're looking for. There's certain use cases that just want to be a smart contract on an existing like general purpose chain. There's others that want capabilities such as, for example, utilizing their token as the gas token, in which case that can be well suited for an L2 or even an L3 if they're more cost conscious and want to compose more with the L2 in question, with the L2 in question. So I think it's sort of like security and cost trade-offs and the level of like customization you're looking for.
So I would agree with what you said earlier. We think autonomous worlds are interesting as a L3. You can almost maybe even think of it like a state channel in which it kind of writes the final state to the chain at the end of the game. And there's obviously merit to it being on the actual L2 as well. But different games have different use cases. There's some use cases that have come out recently where people need different verification use cases. So you can think of like an L3 that writes its state diff to Celestia as well as the proof, and then the client can actually run the verifier and be convinced of the state transition himself. So there's a lot of actual different like software architectural use cases that you can do with app chains.
Shuya, I'm going to call upon you again. I know you mentioned, like, obviously the benefits of having that atomic composability. Like, an autonomous world someone could be in that environment and then go easily and get a meme coin and pull it back in. But what do you see as the potential limitations to this? Like, at a certain point, like, I understand that Mega ETH is really going for performance, but is there a world in which you just really have to have an app chain from your perspective, in which it's not possible to all fit it in one environment?
Sounds like skill issue to me. I think, with like DA solutions like Celestia, right? You're empowering general purpose rollup like Mega ETH to be fast and cheap. And I think in the future, the technology will get even more modular, even more granular. For example, we have node specialization, which my head of growth just talked to you guys about. So I think the blockchain performance will only get better and better, and that allows us to have application that utilize the block space, because I think fundamentally right now we have more block space than applications. I appreciate everybody discussing, worrying about a future where we run out of block space, but I do think right now we have to worry about not having use cases. I think to answer your question more directly, we actually just do not see a world of app chain. We think if the general purpose chain is powerful enough, then application must co-locate together.
Interesting. So I see we kind of have a divide here for different teams. We'll see what happens over time. But I guess realistically, you know, we're all building in different directions, and from the user's perspective, they have so many different chains, whether it be app chains or general purpose chains to choose from. There might be an application they want, you know, on Optimism, another one they want on Mega ETH, and they're going to have to all be connected, right? So I'm curious to get your take. Like, obviously now we have bridges, we're working on shared sequencers, and in the farther future, there's going to be the abstraction networks where the user doesn't necessarily know what route was taken, just that it was the best path. But this could introduce some, trust assumptions in using a bridge that, isn't a fully validating bridge or whatnot. I'm curious, do you guys think it's acceptable to enter into additional trust assumptions to be able to get users between all of these chains? And if not, why? If that makes sense. I can reword that because I think I kind of went a little convoluted direction, but you want to get started, Maureen?
Yeah, no, and I think there's like certain solutions that are coming up, like interop, right, and more like intent-based interop. I mean, we're at Optimism building native interop, but that's going to be able to be leveraged by like relayers using an intent-based system. And so there, the trust assumptions are, especially not within the native interop, minimized. So you do, I mean, in the future, there will be a world, right, where the trust assumptions of the users aren't the ones that they are today with certain like bridging mechanisms. So I think it will become quite interesting without the user's funds being at risk and more focusing like what is the ultimate intent of the user, and they'll never actually see the bridge or have to bridge. And it will be rather like the relayer that takes the risk, and so there will be just a pricing to that.
I think it's definitely a valid question. I mean, anytime you're injecting any type of trust into these systems, it seems like it should be a bad thing, right? We're supposed to be trustless in blockchain. So, so for StarkNet specifically, we prove the consumption and the writing to our messaging queue. So there's no trust assumptions in the system. It's a trustless bridge. So I think these solutions will pop up. I think they're inevitable, but I think it's a valid question as to, what are we really doing here?
And maybe just like one more thing there's like the users are already, there is trust assumptions, right? Like they're connecting with a wallet with an RPC provider, like everybody's not running their own node at home. So they're already willing to make these compromises. It's just how do you like reduce them and reduce the security risk vectors, I think.
I guess from my perspective, it's like, it's more so on the safety side of things. Like I think that we can, the way I see like what the mega rollup might be, it might not be like one singular chain that is the mega rollup, but it's that these ecosystems of chains, so whether they be in the Ethereum ecosystem or the Celestia ecosystem, if they're using a shared consensus and DA layer, they're able to have trust minimized composability using shared sequencers or using just proof aggregation networks or whatnot. So that, to me, I think that if you stay within a certain ecosystem in that way, you're able to have that feeling of truly one mega rollup that doesn't have the additional trust assumption. Obviously, that's a little bit farther in the future. But curious, how do you guys think about that? Like, do you think that a mega rollup would be just these kind of zones of sovereignty, or would they extend to potentially these order flow abstraction networks that go between DA layers? If that makes sense. Shuya, I guess I'll start with you.
I feel like I think if we're really successful as an industry, where there are so many people using crypto every day, so many interesting use cases. I do think what you're envisioning, how different parts of blockchain interact with each other. So I think answer is yes, I see that. The specific solution, I'm not sure, to be honest. I feel like the topic us as an industry have been discussing every single year actually is very different. And oftentimes, there's no correct answer. I think shared sequencing is extremely popular these days. At MegaETH, we actually take a very different approach to share sequencing, which means we actually don't believe in shared sequencing. What we're doing is rotating centralized sequencer. So at any one moment, we just have one centralized sequencer. That's how we ensure the performance is to the moon. But then there is a way to rotate the sequencer that's being used at the moment. So, I mean, you can criticize different approaches. I think right now it's really hard for me to think about which one is going to win. And I think different application or different blockchain ecosystem have different preference for security and decentralization. What we need to do, even for the blockchain ecosystem, is to enable them to express different approaches. For example, I personally don't think that layer 2 needs to be as decentralized as layer 1, right? Like, that's layer 1's job to be decentralized. Why are you replicating layer 1's job? You should just use what other blockchains have done really well, right? Use Celestia as your data availability layer. Shout out to Celestia. And don't reinvent the wheel. So I hope that answered your question.
Sure. Anyone else want to take that?
I guess one other thing I'll mention is, you know, in the not too distant future, we'll be committing to Bitcoin as well. So, you know, there's actually, you can maybe even think of it like different zones of sovereignty within the same general purpose L2 rollup. And then we'll also have volition as well. So kind of up to the developer, up to the user, where they feel they want to, you know, get sovereign.
Maureen,
Yeah, no, I think everything has been shared. In terms of shared sequencing, I think that's quite interesting. I think as we see many different L2s utilizing the same rollup as a service providers, we're obviously going to see some that are going to want to use shared sequencing, and that's going to enable atomic transaction around separate rollups, so that's going to be interesting. In terms of like what's going to win, I don't think there's going to be one winner in all of this. I think there's a world where you need a super beefy sequencer. There's a world where you need an app chain, and I think this is what the market is showing that they want. So I think everybody's going to win.
Very optimistic.
Yeah, right. Yeah, we're all going to win. Yeah, I like to think that as well. I think it is really interesting, right? Like, everybody has a totally different approach, and there's no one-size-fits-all solution for everybody. So my feeling is 1 million rollups more than 1 mega rollup.
1 mega rollup among 1,000 rollups.
Kind of, yeah. It'll hopefully at the end of the day will be totally abstracted to the point where you don't even know what you're doing, just that you're composing in a trust minimized way. I want to dive a little deeper, I guess, into what these independent networks will look like. So within that, okay, so we have like the whole larger thing, you know, some of which will have trust minimized composability, some of which will have some points of trust, but maybe these ecosystems, like for example, Morph, focusing on consumer, will have like a consumer experience like at the smart contract platform level. So yeah, I just wanted to dive in a little bit more into Morph, Azim. I know we haven't chatted a lot about like your approach to consumer within like a sovereign environment. So curious why you went in that direction.
So we went with trying to go for general purpose, having smart contracts deployed to the L2 for composability and interoperability. But we're going with, I'm actually reading this, Ethereum for DA, ZKPs with optimistic rollups right now. But one of the things that we thought about or looked at for like apps that might need better cost or performance is going to be being able to use a different DA for an L3 with them. And it's one of the things, like, have not chatted enough with Celestia, I see Nick in the crowd, but been chatting with Avail and Eigen about what that would look like in the future when we get to the point that we can do that.
Got you. So you're also, I guess, having the L2s as well as enabling an L3 ecosystem in the future.
Correct. Yeah.
Got you. So three for four going in that direction. Shuya, I'm going to pick on you again one more time. I know you're just going in a different direction, so I find it really fascinating. I'm curious, like from the technical perspective, like how are you going to enable this, true scale on one rollup?
Oh, great. Yeah. By the way, apology for my voice. But we're throwing another party tonight if you want to come to Mega Rave. We have a good DJ from Berkheim, so. Yeah, dude, that's hard to get them. And you might get a chance to win the hat too. So,
I want a hat.
So the question was what do we do? So, anyone read this paper from blog from Vitalik in 2021? It's called Endgame.
Yes.
Yeah. So in the Endgame, dude wrote this in 2021, right, many years ago. He said the likely endgame of scaling Ethereum, one of the two possible endgame is to have a blockchain, a mega rollup that has a relatively centralized block production and very decentralized block validation. And that's exactly what MegaETH does. So our block production, which is our sequencer, is extremely beefy. We've done a lot of optimization. We rewrote the entire state try to make sure that it's extremely performant. And we have extremely decentralized and lightweight validating node to ensure the security. And obviously, we're using Ethereum security guarantee. We have forced exit. And also, and then in terms of data availability, we're exploring all options. And so these, as a together, is called node specialization. So rather than having one set of nodes that does all the activities as most layer 1 blockchains and a lot of the layer 2s, we have different nodes that specialize in the things that they're really good at. So our secret sauce is actually not so inventive as what we would claim. Actually, Vitalik wrote about this many years ago. And I think the reason that not a lot of people have actually built it is actually a skill issue. So my co-founders are extremely cracked. They studied low latency data center compute at Stanford, PhD, and distributed system at MIT for many years. So I think we saw the vision and we actually are making it happen.
So interesting. So are you saying that these validating nodes are going to be lightweight, like in the same sense that like a Celestia light node is lightweight, so more people can validate and then just...
Yeah, so our layer 2 full nodes are extremely lightweight. So we decoupled the execution from the layer 2 full node.
Interesting. Yeah, I definitely need to dive into your docs more. Thank you for going into that detail. It is really curious to see, all teams going in different directions, and so I appreciate like the level of detail that you give. I'm going to zoom out a little bit now and be a little bit less technical. I've heard lately about this notion of enshrining certain core infrastructure into a protocol. Like for example, Berachain, right? They're having their like Berachain native DEX or their Berachain native like lending platform. And I think I've heard whispers throughout the ecosystem we're probably going to see more of this in the future, as opposed to just having like a fully permissionless general purpose execution environment. So kind of helping the ecosystem become a little bit more specific in what they're trying to offer. I'm curious if any of your teams have thought about doing something like this, like enshrining apps at the protocol layer, and if so, why, and if not, why not?
Since we're still in testnet, it was something we did consider. We ended up shying away from it though, because we thought while it might be better in the short term for having everyone know exactly where to go for things, we thought it would feel a little bit monopolistic, because other people who would want to then launch would be in a really bad position to be able to compete with the native things that we had enshrined. And so we didn't want to set a scenario where that would happen.
I guess also, Optimism and Starkware are not doing this approach. Do you see any benefits or perhaps drawbacks to potentially going in that direction in the future?
Yeah, no, I mean, OP mainnet, the network, obviously didn't make this decision. Optimism providing the OP stack also does not make this decision. We're even like very weary of including like certain pre-compile or pre-deploys, because we're even thinking about like not wanting to create state bloat that some networks might not want, right? So it's up to the chains that deploy to make those decisions if they want it or not. So at the tech stack level, we don't want to impose anything like that.
Yeah, same for us. We don't want to introduce any type of complication into the protocol layer that doesn't need to be there. The benefit of it being general purpose is that anyone can then go deploy these things. And it does sound like a good use case for an app chain at the end of the day. If that's something that they'd like to enshrine, that's a perfect reason to have an app chain.
Okay, I'm sorry, I'm just
Another
the one
contrarian take?
Yeah, we actually have co-located Oracle for MegaETH. And the reason is we're here to make Ethereum great again and beat all the other alts layer 1. So, and the reason is we have a rotating centralized sequencer. So when you co-locate the Oracle with a centralized sequencer, you can do magical things like arbitrages that no one else can do. And this is really a 10x experiences for a blockchain network, like similar to a Web 2 services. So that's what I think the different things that we're doing. Yeah, because the benefits is very obvious to any asset-to-asset transfer primitives on MegaETH.
So basic. Oh, you go ahead.
How does the co-location with the sequencer facilitate that?
What? Sorry?
How does the co-location of the Oracle with the sequencer facilitate that? I mean, you'll still have Oracle data on the...
Yeah, but it's co-located, right? It's extremely fast, so you can do arbitrages. Because everything we do is low latency, which is why we call ourselves the first real-time blockchain. Because you get first-time money market, first-time DEXs, and then like if you get liquidation, it's actually micro liquidation. You don't get like a sudden liquidation because the round trip for a transaction is extremely fast.
But I guess co-located means like it's not enshrined in the protocol, right? Like you're just running it out of the, okay.
Well, yeah, we struggle. We're like, is this enshrined? Because like in the Ethereum world, like enshrine
like
it can be
bare
quite
metal server.
Yeah. But yeah, Sarah, thanks for the correction. Yeah.
All right, I've actually run out of my questions. We've gone pretty quickly. Is there anything you guys want to talk about? I can go one by one. If there's kind of an overall overarching theme, what do we think? 1 roll-up, 1 million roll-ups? How do we feel after all these after all this talk, Maureen? I'll let you finish off.
Okay. Well, I think my position is a bit clearer. I mean, again, I will just say, also not just like for like public blockchains, right, but private blockchains. Ideally, there's a future also where private blockchains are needed, or already is and are. And so I think they're clearly not going to, like, governments are going to want blockchain, and ideally that leads to like efficiency. Hopefully not CBDC, but like other types of more efficient private blockchains, and they're not going to want like one, like a public blockchain where they don't control the sequencer. So even just from that aspect, right, I think you see that there's a need for like many different types of blockchains to meet the different types of applications there is. And I think the problem, even if like super beefy and fast with a general purpose chain, it doesn't have like the customizability to meet the need of certain use cases, right? I mean, I'm not sure what sort of like block time you're looking for, but maybe perhaps like games are looking for something even more, like even better, or certain use cases will always want more and are willing to make trade-offs on other things that like for general purpose you wouldn't want. So yeah, that's a bit my thoughts on that.
Yeah, so at the end of the day, app chains are cool, in my opinion. And you know, we believe that you need to have the general purpose L2 be as performant and have as performant as a stack as possible, so you can employ those things at the app chain layer at some point. I think it's also a switch to app chains, but in a similar vein, is proving snarks on starks. So you can do things that aren't even app chains, but that are still provable on the general purpose L2. So there's a lot of different use cases that we want to enable from the general purpose L2, to different layers.
I have 2 sort of spicy takes. One is that I know we're constantly talking about how only more infra gets funded, and I actually think more infra does need to get funded because we're not at the place where we have an understanding of how things actually will end up going with this. And the other thing is the infighting that I end up seeing within Ethereum actually is interesting, because it reminds me of AOL, because I'm old. And I think about how AOL commanded the majority of the market before, and how there are many people who still assume Ethereum has fully won already, when I do look at how Aptos and Sui, or when MegaETH came out, although you guys are EVM, that it seems like there's going to be different chains for different things, and that what my guess is that interoperability and composability end up working the right way between them over time, where things are abstracted away, and there will definitely be like app-specific chains, but they might be on completely different blockchains as well. I think like oftentimes we're in this echo chamber where everyone talks as if like ETH has already won forever, and I do my best to go out to other ecosystems, and like one of the people who was not fading Solana last year, and then like seeing what they've done, and ETH people will still say like, oh well, it's just meme coins, but like they've also done deals with Visa, and so when I look around, it's sort of looking at that.
Final spicy take.
I was gonna say Mega ETH is the real Solana. But, it's more performant and more secure and really exploiting the limit of hardware. Yeah, I think I respect, honestly, what optimism has done for our industry a lot. I think what Mega is doing, we cannot do what we do with optimism. We are using optimistic consensus, as consensus node, right? Like, so me here talking about Mega doesn't mean like other rollup is anything worse. I think everybody has done things really good, so that we can stand on the shoulder of giant. I really love what Starkware does as well. We also think ZK is the future. No offense, I feel like no optimism. You guys are also introducing ZK, but you got my point. I think all of this like very interesting innovation and different direction is just pushing everyone to think further about how to onboard applications. Like Marine, when you were talking about the fully on-chain game, I got really excited because I think this is truly a crypto-native use case that it would be great if it's an app chain. It would be great if it's on Mega ETH. Like honestly, it doesn't matter as long as like, you know, like Web2. Like we onboard more people to the fantastic world that we live in. We're obviously very opinionated on the mega chain, Mega ETH chain. But I think what we're doing as R&D in our ecosystem, we're hoping that we can give back to all of you, right? What we're doing on our sequencer, I hope we can empower everyone else as well. So like it's really not a black and white difference, as every single technology component can help each other. I think lastly, like I love what you guys are doing on the consumer focus. I think I'd love to hear more about what your lesson learned in maybe optimizing the wallet experience. How do you empower people to buy on and off-ramp crypto a lot more easily? How can I not use a spreadsheet to track my like seed phrase and etc. So and eventually, I think a lot of people here were just like make Ethereum great again, right? So we're all very much on the same mission.
Thank you so much, everyone. Would love to meet back in a year and see where we are and see if our opinions have changed or whatnot. But it was really great, and thank you for all of your spicy takes. And yeah, thank you the audience as well.
Thanks.
Thank you.
Should we take this? I think we take it back. Yeah, of course.
Yeah, I think we'll go out because next speakers will come. Yeah.
Yeah. Can I have the clicker? Here, I'll just.
I'm a little like event out.
Yeah, I hear
Is it not finished? No, it's like 2 more hours. But you could sleep. You could go to bed early. Oh my god, the light. It's a stage light. Okay. Hello, everyone. So right now, there is a time for the next speaker. It will be Patrick O'Grady from Ava Labs, and he'll tell us a bit more. About the decoupled state machine replication. Let's welcome Patrick O'Grady. Patrick O'Grady, are you here? Yeah. So let's give him a big round of applause. Woo! You can do better, I believe. Applause.
Alrighty. Let's see if this clicker works here. Yeah, I don't look like that, it turns out. It's, oh, there we go. I'll go way back. Yeah. Awesome. All right. Well, thanks for coming to my talk on VRIX, in parentheses, in practice. So today I'm going to be talking about fortifying decoupled state machine replication. I'm Patrick O'Grady. I'm the VP of Engineering at Avalabs. I've been there for about 3.5 years, focused on all things related to really the consensus stack. So that's networking, P2P stuff, consensus itself, and then really how to best make use of consensus to drive execution and scalability. So why am I here? And what am I talking about? So a few weeks ago, people saw this talk from Josh, great talk about we are building the same thing. And I also saw this talk. It was awesome. I think he did a great job of trying to draw similarities between different projects. Similarly, I'd been talking to Nick from Celestia for some time about some of the stuff we were doing. He's like, hey, you should come by, talk a little about what you're doing, which we're working on similar problems, but in a very different lens for Avalanche. And that maybe tell it from the perspective of a more modular setup, and maybe for this audience who might find it interesting. So at Avalanche, we've always been really interested in a bunch of different chains that are connected. And so this is my attempt at a meme related to that. But the idea is that a lot of the stuff we're doing is very similar to a new L1 where there's a bias towards, just a little bit bigger bias towards sovereignty and native interop. So instead of stacking everything on top, we believe more in the horizontal approach where there's just loose connectivity between the different components. And before I get started, forgive me, this was designed, I think integrated might be a dirty word here, but designed for an integrated blockchain. So where this all started, I don't expect you to read this, but a lot of people in the space to scale have been talking about agreeing on execution inputs instead of execution results. So if we just agree on like what's actually in the transactions and in the blocks, then if we just put those into consensus and execute later, then we can actually get the scalability and performance that we're actually looking for in building out these chains. Well, while that may sound straightforward and simple to say, in practice it can be a lot more difficult because you need to be very careful about what you actually allow to be in these blocks or what these inputs are, because they may not always be valid. So to understand a little bit more about what we're talking about, let's take a big step back. So anyone that read John Charp's post from a few weeks ago saw a bunch of these diagrams I made in basically kind of setting the table around what a lot of the state machine replication work that a lot of teams are doing looks like. So to first, it starts off with this traditional world of state machine replication, which if you use Bitcoin, Ethereum, or most other chains, you're probably very familiar with. Some validator or some block producer produces some block. They then replicate it to the rest of the network. Other people, when they get that block, verify it. And then let's say in this case there's 2 validators. The other validator will then build on that and only include transactions that are semantically valid. So if I include a transaction, sorry, Bob pays Alice, but Bob doesn't have enough funds, we would just consider that block invalid. This is what that typically looks like, and over some sort of time scale here, the issue is we have to actually verify this state and keep it up to date before we build. So people in recent years have started to optimize this a bit. So again, kind of hard to see, but with the same diagram is that people will build a little bit, then start replicating, build a little bit while they're replicating and keep going. And what we would call this is streaming state machine replication. So people that are familiar with Solana and how Solana works follow a very similar approach to this. Well, anyone that's been following the latest consensus research has seen this phrase, decoupled state machine replication. And folks that know the movie Zoolander should appreciate
that mean? But a lot of work has gone into trying to instead break this all apart. Now, why would you want to do that? Well, if you do that, you don't actually keep the state up to date while you begin to replicate its contents. Now, that may sound, a little pedantic, but what that really means is you may include blocks or transactions in blocks that don't actually have funds or can't even be processed correctly. Now, why you might do that is that you can reorder these processes of building, replicating, and verifying in a way that may allow you to achieve much higher throughput with the same hardware. But it's a little tricky. It's exciting because it allows you to achieve throughput you might not otherwise get, which is why we're seeing a lot of chains like Aptos and Sui, like what people call the latest generation of chain, really start to employ these techniques. But what it comes down to is this trade-off. We're not performing semantic verification prior to replication. So semantic verification here being, hey, does this transaction actually have enough funds to pay fees in this network? Now, on a standard chain, something like a Bitcoin or Ethereum model, this is easy to reason about. But the same thing happens actually quite a bit in the modular ecosystem, where you may have things on different layers. You may have some sort of synchrony delay between when you can actually check the balances or the validity of different parts of the stack and how things are actually included. And so ultimately, your consequence, if we break transactions per second into different components, is that you have fee-paying transactions per second, which are less than really what your replicated transactions per second could be. And then the negative externality of this is that you have some amount of invalid transactions per second included in different blocks. Now, if we're an adversarial user, can we cost-effectively increase invalid transactions per second? AKA, will the network allow us to just stuff it full of transactions that nobody can execute? So in the VRIX write-up, which you can check out at vrix.xyz, which is in the corner there, always, if there's a domain available, I'm always there to try and buy it. We model this with basically a naive implementation of decoupled state machine replication. So you can imagine a standard chain. Maybe there's, in this case, 100 validators. I think the specifics of this really aren't important. Really, what to focus on is that you as a user are going to send transactions to any validator. Your transactions have a nonce, and then validators of their own volition will try to include whatever transactions they think are valid. So just like a normal blockchain, you send it to some validator. They're like, great, I can collect some fees on this. I'll sequence it, replicate it, and then hopefully be able to execute it. Well, there's a number of attacks that can really undermine this approach. The first, we'll start very trivially. Let's say that I just send the same transaction to everybody at once. So I have TXID1, I send it to every validator in the network, all 100, and I have a bunch of different accounts that do this exact same thing. Well, all of a sudden, every validator, really, if I fill every validator's queue with the same exact transaction duplicates, many fewer transactions get in. Now, this is an attack that's been understood, and someone thinking about this is probably the first thing that they would think about. And so there's a paper, I always try to give credit to whoever the first person to point this out was, and I think this was the Mir BFT paper, and they suggest that you might want to partition the transactions by validator. So in this case, let's just say that that problem's solved. Well, unfortunately, there's a few more issues you might want to do, or a few more approaches you might want to take. So the next one is if we assume every transaction has some sort of nonce, what happens if you send different transaction IDs, maybe with different call data, to different validators? Well, if you do that, two validators may think that they have unique transactions because they're partitioned or like the TXID to that validator. However, nonce is the same. So anyone that's familiar with like the typical account model knows that only one of those will actually get executed. So we can perform the exact same attack we just tried to prevent using this approach. Another common approach, or simple approach an attacker might take, would be fund exhaustion. So what if I send 10 transactions from my account, and I only have the money to pay for one? Well, you're now going to sequence maybe all 10 of them, but only the first one's going to actually deduct fees. So this one can be pretty bad, and unfortunately, don't have the time to go through the math, but I have a longer video online that you can watch where I do. Sorry. This is what happens when you try to cram a hour-long presentation into 20 minutes, but bear with me. So things get really bad when you combine the attacks. So if you take conflicting transactions, one with nonces that conflict, and fund exhaustion, you can really take a naive DSMR implementation to almost no transactions per second. I think I computed it in this model to be like a 99.999% reduction in throughput. So what it really you have to think about is that this is not only the only problem. So anyone that knows, most people that use blockchains want to access historical data or sync the chain from scratch. Well, if you hash the data that's included and you want to now fetch everything to re-execute it, you unfortunately are indefinitely persisting all the invalid transactions over time. So if you want to sync it, not only at the tip are you only processing like 1% or using only 1% of your block space, but every time anyone syncs it, they're also wasting 99% of their bandwidth syncing transactions that never actually executed. Similarly, you might say, well, we really like the idea of having dynamic fees. When there's less activity, the fee should go down. Well, you might think, okay, well, I'm only going to charge fees for valid transactions. That makes sense. That's what everyone does. Well, you just incentivize an attack because if I'm an attacker and like, well, transaction prices are really high, I really want to get my transaction for less. Well, if I stuff the chain with a bunch of invalid transactions, the amount of actual execution that's happening is going to fall off a cliff, which means that the fee should go down, which now all of a sudden I've made my life cheaper. So you can even actually accidentally incentivize attack, which is a whole fun journey to go down. And so when you're thinking about DSMR, my only advice is to think a little bit more before you just deploy it, because there are quite a number of nuances to think about that someone could trivially exploit without having any stake. So what can we do about it? Well, not a lot. We don't have the state, so we can't really do anything that's state related. We could try to implement some sort of synchrony requirement or something like that. However, that can cause a lot of stability issues, especially if the network is degraded. So maybe we can rely on heuristics. And so what if we give validators the tools by changing some rules in execution to enable profit maximizing builders to at least minimize the number of invalid transactions per second that they actually include. Now, this may sound like a lot. I'll explain what I mean here. So VRIX is all about exploring what you could actually introduce to systemically prevent the attacks that I mentioned previously. So 4 ideas, and I'll talk about this as future work, is that we'd love to collaborate with the ecosystem on finding a more robust or formal description for what a minimal set of protections for DSMR might be. But 4 that we can explore here are account fraud proofs, temporal account partitioning, nonceless transactions, and post-execution transaction filtering. The fun part of this is it's actually consensus agnostic. So if you've heard of DSMR, you can just couple it with some existing DSMR. People usually like Narwhal and such. So first one we talked about as an attack. This was more or less a derivative of the mere BFT work. But if you point the transactions to some set of particular validators, you can avoid this transaction duplicate issue, and you can actually subpartition an account to multiple validators at once based on the TXID space, so that you can't be censored just by a single validator. So this is one approach that's interesting. I think my favorite, at least, is the account fraud proof approach, which allows you to have fully decoupled inclusion from execution without actually hurting the validator. So in this world, any account that wants to actually have transactions included in the chain would lock up some amount of funds greater than or equal to the fees that they may want to spend on some number of outstanding transactions at one time. So let's say that the fee rate on some chain is 0.1. I'm going to lock up 1 unit. That would allow me to have 10 transactions in flight at any particular time. Now, if I exceed that, obviously the builder can't know that I'm doing that, but because I'm uniquely partitioned to some number of builders, and this fraud proof is just divided between them, any builder knows that if I only include transactions divided by partitions at once, then I can claim my share of the fraud proof of whatever is actually outstanding. So you can give me absolute garbage, or you could have no money left, and I, as a validator, will be no worse off from a fee collection perspective, which is the most important part here. I can't ensure that what I sequence will be valid, but I can at least ensure that I'm paid for what I actually include in a block. Nonsense transactions are something that is not very popular in the EVM ecosystem yet, but I think that they will be. It's actually not that crazy, and the idea is you just keep some window of TXIDs and just make sure that there's no duplicate TXID included over that window. The nice benefit of this is you also get transaction expiry out of the box, which for many applications is super useful. And so this prevents the attack of having duplicate transactions that have different TXIDs. And then lastly, you can trivially filter the blocks and still keep things. So if you just require filtered chunks to be included in the chain after some diff, that will allow you to actually sync the chain at a later point in time without actually synchronizing the invalid transactions. And so if you include those in consensus, you can be very sure that they're safe to sync to. And so you might build a chain that has blocks. On each block links to some number of certificates, and then is eventually executed, and then the roots of that execution are eventually included in the chain. So how does it do? 2 minutes left to explain. So with a lot of this stuff, until you build it, you don't really know how good it is. And I think my primary goal after writing up a lot of the VRIX ideas was to actually try it. So my target was, everyone always talks about 100,000 TPS. Can you hit it, at least with micropayments, in a distributed cluster? So we did it. We set up 50 equal weight validators across 5 regions, 1 API node per region, 1 transaction issuer, transactions issued randomly to API nodes, and most importantly, a ton of accounts. 10 million active accounts, 2.5 million unique per 60 seconds. And then all transactions are just transfers. So we're talking micropayments here. We're not talking smart contract interactions. So you can see, big line at 100,000, nothing crazy. But you can keep it stable with minor variations in networking from our favorite cloud provider, AWS in this case. But generally speaking, what's important is that the network latency hovered around what we expected. So over like a sustained period of time, generally things stay pretty stable. And as a result, when you distribute transactions prior to execution, we're able to get attestations of their distribution within a couple hundred milliseconds. And so, and generally, things remain pretty stable. I'll skip this, just stability. But the important part was we saw no expiry or failure for any transactions, chunks, or blocks. It took on average about 230 milliseconds for a chunk, so this decoupled state machine replication, to be fully tested by stake in the network. It took 700 milliseconds for the full chain from a person to send a transaction to an API to then get it tested. So this is what you would show the user. And then the finality part is more a function of the consensus, so we won't talk about that. But we achieved pretty good throughput without really stressing the workload. Much of it was compressible because you see a power law typically of transaction inclusion. And then most importantly, VRIX focuses on symmetric bandwidth usage between the validators. So there's no like core node that is in charge of sequencing something or is like some bottleneck for bandwidth. And so like I mentioned, future work here, let's make DSMR safer for everybody because I think it's going to become a very popular topic over the next few years. And so it'd be great to work on formalizing the framework for minimizing what we would call invalid transactions per second. That's it. Thank you.
Thank you, Patrick. We have some time for questions. Anything from the audience? So maybe one question for me.
Sure.
What is like the biggest risk factor that you see to this architecture? Is it this ITPS, the minimizing, or?
Yeah, I mean, I think the toughest part about all this is I think a lot of people have great ideas for how to improve performance. And most of the time, those ideas work pretty well in the optimistic case. But unfortunately, when you consider ways to try and attack it or malign it. Even if you take one or two participants and make them malicious or take them offline, things tend to blow up quite a bit. And so I think the biggest risk is deploying solutions that sound great or look great without a lot of formal analysis around them when there's funds at risk. And so I think DSMR is great, but I think we just need to be careful as a community because it's a totally new approach than what we've been doing over the last decade. And so I think the risk is just that things are great and then all of a sudden they're not. And so by working together on what are safe frameworks to use, that hopefully we can make sure users stay safe, but hopefully without putting too much burden on them in the process.
Thank you. Any other questions? So thank you, Patrick, once again. Big round of applause. And right now we'll have Dino X from Fluent. He'll tell you a bit more about blended execution. Big round of applause.
Yeah. G-blend. Oh, yep, need that. G-blend, G-blend. Yep, I'm Dino, one of the co-founders of Fluent, and I'm going to be mostly talking about applications, actually, not necessarily blended execution, definitely not like the underlying tech and stuff. So I'll try to keep it high level, try to keep it interesting. And title, your favorite apps are blended. All right, so a few kind of main topics. We're going to be talking about learning from how the cloud scaled. There's some lessons in there. We're going to talk about, we're going to assess kind of like the current state of execution environments, and we are going to outline a better path forward for execution environments. So the first thing is we spend a ton of time in crypto talking about the next billion users and the next million developers, and the reality is we don't even have like 1 million users yet, so it's like we probably should be spending a little bit more time talking about some of like, the lessons we can learn from the, the spaces that actually have 1 million devs and 1 million users. Billions of users, actually. You could see here, like your typical social app, multiple billions of users and many millions of devs, actually. So maybe we can learn a thing from them. And so what they got right, in my opinion, is taking these individual functions of an application. So this is supposed to be like an Amazon type thing. So take like a search function, a payments function, a ratings function, and breaking that up into loosely coupled services. And they're like, hey, over 20 years, they realized like, hey, it scales way better this way. And we can update things, like different teams can iterate really quickly, work on different parts of the app, can update things, scale them better. And the reason we're all here is because we obviously learned a thing or two from that. We said, hey, the big fat piece of code doesn't really scale well, so let's chop things up and modularize. And so the main point here, which I think that they learned in the cloud, is that if you give developers like the best tool for each task or the best kind of tool for each function or module or whatever you want to call it, like in modular land, like this is kind of applicable to like the core architecture, you end up with better products. And so the question is like, what else can we learn from how other computing paradigms have been successful today? And we can just zoom in to kind of like the modular side of that last diagram and unpack the actual modules themselves. So like within a given like execution environment, most likely. But since it probably won't be that interesting to talk about like search, we're going to go to a hopefully much more relevant or familiar example, and we're going to talk about the front end of Figma. Most of you probably are aware of Figma, but in case you're not, it's a collaborative design tool that's built for the browser. And they basically managed to find a way in this very constrained computing environment of the browser that isn't very flexible. They found a way to actually, offer a unique application that wasn't possible before, and clearly a 10x application to disrupt the design industry. So it's like, what can we learn from like some of those design principles? And the way I break it down, like this is the Figma interface in case you're not familiar. But there's I'll break it down into like two core parts. There's like the middle area, which is like this main panel that's highlighted, and it's the meaty part of it. And this is where you'd have like all of your, all the files. There'd be hundreds or thousands of files, and basically that is kind of hard to do. Typically in like a browser environment. It has to be like really performant, and in their case, their design goal is like 60 frames per second, so there's not any lag. A very different design goal is on the layers and properties panel. And so this is like less performance sensitive, but the main design goal there is to make it like as easy to easy for developers to like quickly iterate on. So it's important to have like a ton of libraries that are sitting there waiting as like building blocks for developers to iterate on quickly. But it's not that like heavy compute. So these are very, very different goals. So what do, how built? And what they ended up concluding is that, you know, it's best to handle the different design goals with two very, very different languages. So in their case, C++ and TypeScript. So the layers and properties panels on the right and left side, they're basically, you know, they're written in TypeScript. For the most part, Figma's written in TypeScript. But then what they do is they use C++ for kind of the core rendering engine because it has to be very performant, right? And so what did they, I mean, what's kind of the net takeaway there? In my opinion, it's that the best tool for each job kind of can create the better products. In their case, a $20 billion product that disrupted a whole industry. Let's actually use another example that's, I mean, not everybody's a designer and maybe you're not super familiar with Figma. Let's actually use one that probably hits closer to home, which is Telegram. I'm sure everyone here spends way too much time on Telegram. But it's the same basic idea. So like most of Telegram, at least the web version of Telegram, is written in TypeScript. But there's a few core things that they actually use, whether it's C++ for or just some other, in their case, WASM-based language libraries for some, like different specific actions, whether it's because those parts of the app need to be like highly performant and to make more sense in C++, or maybe, you know, some other language has some interesting building blocks, these like pre-built libraries that they just want to like plug in. So one example here, and I don't know how this is going to come up because it's supposed to be like a GIF, but I think it has to be a video. Okay, yeah. So if you've ever used like the animations or stickers or anything in Telegram, you'll notice that this actually you're interacting with C++, which is you don't really think about because you're using a web app, but it's really the case behind the scenes. I guess it was a timed video. Okay. And so those are not the two only applications. I mean, so many of the applications, your favorite apps that you might use on a daily basis, whether you interact with them directly or whether they're sitting behind the scenes like a Cloudflare, like they still exist and they're built using these types of principles of like using the best tool for the job. Okay, let's contrast that with crypto execution environments today. So just like blockchain execution, what does that look like? And what we see is like a very different you know, level of kind of like expressivity for developers. It's like very siloed. Like if you're somebody, and by the way, this is not making a case like against like a bunch of roll-ups. Like we actually see that vision too. That's not gonna be the point of the rest of this talk, but like just a quick clarifier. But if you're somebody who is trying to build within a given sandbox, if you're trying to build like the best DEX or the best whatever possible, and that particular application, you're confined. Like you can't use the best tools for each part of that application at all. Even just the notion of being like an EVM developer, an SVM developer is like kind of silly. And so that's why, of course, you know, you got more ECC side events than actual Web3 apps. And so I'll actually go as far as making the statement that we will never get mass market applications with these like really constrained computing environments. So what do? Oh, what was that? So what we're proposing is a new type of VM called a blended VM. And the main idea here is you kind of have this one state machine that can support applications from all different types of environments that are atomically composable in real time. They're sitting there. It feels like one it really just feels like it's one VM under the at the end of the day, and it really feels like that for a developer. There are like a lot of from what we've found doing research, there's other types of implementations where it might seem like it's multiple different VMs together, and maybe that's how they implement it. But either way, like we haven't really found it done in like a very like elegant way, and this just like feels like one unified environment for a developer. And just to make that a little bit more concrete, what do you get? I'm not going to talk about the inner workings of it. We could save that for another talk. But what do you get? Dozens of programming languages, millions of software libraries, all in one place. And just to point out like a specific application, like get a little bit more concrete even, This is an example chess game. I guess you can't, I don't know how that actually renders, but there's one part of it that's in Solidity. We built it. There's one part of it that's in Solidity. For the most part, the thing is in Solidity, but it's using kind of Rust for like the core game engine. It's using a Rust library. And the cool thing about it is like to a user, the user doesn't feel that. Like the user doesn't interface with that. To them, just using their EVM wallet, the only way they experience that application is either being an application that's now possible all of a sudden, or just like a faster one or something like that, or just like with better features using libraries that somebody took. So that's like just a really simple example just to ground it, because I know sometimes you can get like abstract without that. But like we envision a lot more things. Here's just kind of a snippet from Twitter from someone in the gaming community. And we already start to see kind of like the juices flowing around what can be done in this type of blended VM. And we're really excited to see what people build. We're on DevNet right now. One thing I want to point out is like Fluent specifically is focused on, as you probably saw on the other slide, EVM, WASM, SVM apps. But like we think this is just like a better way to build execution environments, like this type of design. And like we would hope that other people maybe prioritize different types of VMs to blend together. And we envision not, if there's going to be like a million, like we'll call them single execution networks, we would love to see a million blended execution networks. So yeah, excited to see what people build with this. We're starting to hear some really awesome ideas. And just to like reemphasize, I mean, that's basically the end of my talk. Just want to reemphasize like the main point here that I think for us to actually build these 10x applications that anybody gives a shit about, we have to start like giving developers the flexibility to easily use the best tool for each job. And I think that's when you get the best products. And here's a spaceman meme. All right, thank you. Yeah, that's it.
Thank you. We have some time for questions. Is there anything from the audience? I'll wait for the microphone.
What is the communication layer between all of these, VM environments that you run within the blended VM? Like if I'm calling a Rust library within Solidity, is it like a network layer, or like are you having like a sort of like system call to like a Rust program? Like what does exactly happen behind the scenes?
I guess you could think of it like a system call we have. And by the way, like I'm actually someone in the audience here can explain this much better than me, our CTO. But like I'll give it a shot. I mean, there's kind of like two parts. There's like what we call compatibility contracts, but just like pre-compiles that like help with the mapping like between these things with different standards. And it works in tandem with like this reversible ZK tree, and like that's kind of like the magic under the covers. So that also makes it like much more like efficient to do, rather than just like running multiple like different VMs in the same place. Even just with like 2 or 3 VM targets or whatever you want to call it, because we're not running the actual VMs. But it also makes it like super easily extensible to other types of environments. So if we wanted to add, if there was interesting enough kind of VM environments to like add to like this VM, we can support that pretty easily without like a ton of ZK proving overhead. So just like a little bit of like a rounded like way of just packaging up the way it kind of works, just at a reasonably high level. But yeah, happy to like talk more offline.
Thank you. Any other question? So maybe now I have a question. Because you told about many products from, let's say, Web 2, you also talked a little bit about the future of the apps for the Web 3. But what is currently your favorite app in Web 3?
Got a friend shilling. My favorite app in Web 3.
Right now.
I mean, that's why there's more. Go back to the slide. That's why there's more ECC side events than apps. We need more blended environments and better ability for developers to easily build them. I don't really have too. I like some of the SocialFi experimentation that's going on. Some like consumer stuff. I also really like some of the autonomous world projects, but I don't necessarily have one specific one that comes to mind. Sorry, man. I know that's not too exciting.
So we are still waiting.
Yeah.
Any other questions?
Yeah. So thank you very much. Once again, big round of applause. So right now we'll have a quick break for 10 minutes, and the next one is DevBear from Berachain. So see you around in 10 minutes at 5:20. Hello everyone, welcome after the break. Right now there is a time for the next speaker. This is Dev Bear from BeraChain, and he will tell you a bit more about BeaconKit, a modular framework for building EVM consensus clients. Let's give him a warm applause.
I have a mic. I'm good. Oh, it's the clicker. Which button is it? I can't see anything. The green button is forward. The red button is backwards. All right, I'm gonna test it.
The green one is for the next.
Oh, okay. I think we're good. We're good. Okay. All right. Thank you. Sorry? We're good? Beautiful. I can't see anything, but we're good. Thanks. Beauty. Make sure I don't fall off of here. Okay, perfect. How's everyone doing today? So today, gonna give a little talk about BeaconKit, and super excited to share that with you guys. Quickly to just introduce myself, I'm Dev Bear, one of the co-founders of BeraChain, CTO. Been focusing a lot of my time over the past little while on kind of execution clients and building out kind of core protocol stuff, and super excited to share the next part of the journey with you today. So to kind of give a little bit of an update from last year I spoke about Polaris, which was our kind of previous version of this EVM framework. And we've been through a long adventure figuring out how to build a modular EVM. So kind of to give a recap of how we got here. Way long ago, kind of when we were first IDing on BeraChain, kind of the first thing that we thought was like, hey, like what if we just, do what everyone else does, kind of start a Geth fork and go from there? We realized that that's actually quite difficult. When you want to like start playing with things and changing the logic, it can become quite cumbersome. So we looked at, okay, like is there a framework that we can use? Looked into Substrate, funny enough. I don't know if that's still alive today. And then as we kind of dove into Cosmos, we saw Ethermint, and we saw that, hey, like maybe there's something here, the intersection of the interchain with EVM, and maybe this is where we want to go. Ultimately, where it took us was we were like, okay, there's pieces of this that we like, pieces of it we don't, but overall we were bullish on this ideology of having this interoperability. So we were like, okay, let's go build our own framework, and that's kind of how Polaris came to be. So the idea behind Polaris is that we saw this like opportunity to build this modular EVM framework, and the way that I kind of break things down for this, and still very true today, and you'll see this in BeaconKit, is we can break down kind of any blockchain into like 3 basic pieces. You have to build a block, you have to process a block, and then you need to like save the block somewhere. And the whole idea behind Polaris was like creating this modular separation of these concerns. Now, what happened was, we also discovered that ABCI and Comet BFT and all this jazz and the EVM kind of lifecycle and semantics of that didn't really mesh well together. The EVM mempool, the EVM block building process has been something that's been iterated on for almost a decade at this point, and we discovered that it's really critical that you actually use these semantics in the way that they're supposed to, and kind of just some of the ways that ABCI was designed made it kind of some performance issues there. On the converse, though, we saw that there was definitely something there when it came to like having this interoperability. We had this concept of like precompiles, which allowed EVM transactions to touch into like Cosmos namespaces. And we think for application-specific chains, this could be really cool. If you have a really complex application that you need to run on a blockchain, but you want your users and developers to be able to interact with that application in a programming language that they know, having that, synchronous composability is really powerful. So the one downside to this, though, is you're going to end up with a Geth fork. There's no way to get around it. Like, we tried and tried, but ultimately you're going to end up having to maintain your own EVM. And that's kind of the problem, is that you think it's going to be great. You're like, okay, we'll use all this stuff that Ethereum has. We'll add our modifications, and we'll like make this super crazy thing that's like Geth++. In theory, this happens. Oh, one of the slides got messed up. Oh, no. There was a SpongeBob like on fire meme, but what ends up happening is you end up just like having to maintain a nest of dependencies. You're forking your own logic, and it just gets like really messy. And we see this on a lot of other chains where Geth falls behind, they're running an EVM that's older, people want the latest features, but it requires engineering effort to keep it there. And it just ends up being like this nasty cobweb of things that just like sink time and money into it. You end up having to do exactly that, right? You're building these cursed connectors, you're having to like figure out ways to patch pieces together. It just gets really gross, and you end up just spinning and burning engineering time trying to like build something that you shouldn't have to. Like you're trying to like figure out how do we make this layer like just work. Like you know have 1,000 meetings, 1,000 design sessions, and ultimately you kind of end up at the same place where you're like, we just need an EVM that works. And that's what developers want at the end of the day. Like a lot of our experiments and testing and things really showed that users just want, or developers just want an EVM that just works. And if you have this embodiment where like JSON RPC is slightly off, or like an opcode is slightly changed, the whole suite of EVM tooling that has been developed over the past 10 years at this point starts to run into issues, and it really adds a lot of friction for developers. At the end of the day, there were basically like 3 biggest things that we wanted to be able to achieve as part of this EVM framework. The biggest of which was we wanted to be able to still leverage these like cool concepts around like comma BFT, single slot finality, IBC. But at the same time, we wanted to avoid having the situation where you're like running this kind of hodgepodge EVM that like has issues. Lastly, one of the things is that we didn't want to have to like maintain all of this work. Like a non-trivial amount of engineering time was going into just simply keeping our EVM up to date. And it seemed like really silly, and like there was a better way to get around this. And teams that are building, if you just want to build an app chain, having to devote millions of dollars a year in engineering time to just keep your EVM up to date seems really, really silly. So, I don't know at this point, 6 months ago, 7 months ago, whatever it was, I had this crazy idea. And the crazy idea was, what if we were able to just run any execution client, anything we wanted? We just wanted like an EVM that works. We don't want to have to deal with it. And where we got to is we came up with this idea, which is now called BeaconKit. And the tagline is a modular framework for building EVM consensus clients. And basically, the idea behind that is we have 2 different binaries. So we have one on the left, which we call the consensus client. The consensus client is basically, in EVM terms, and this is taken straight from kind of Ethereum 2.0, it's responsible for consensus. It doesn't do anything. You can't submit transactions to it. It's just simply, what is the state of my blockchain? Are we coming to consensus on it? And the thing that it's coming to consensus on is basically, what is the, and I just realized I'm standing in front of the screen, what is the state of my execution chain? And it's basically saying, okay, like the consensus chain, there's an execution chain, I want to come to consensus on what the head of that chain is. And that's pretty much all it does. Lastly, how it does that, and it powers the EVM, is over what's known as the engine API, which if you're into the ETH2 world is a very well thought out, very kind of, it's been around for a while at this point. But what's nice about it is now we're interacting to the EVM in a way that's very natural, right? We're using the common channels, the common API that it was designed to do, and that allows us to have this like standard unmodified EVM, but still being able to leverage comma BFT, IBC, et cetera. So what this looks like to the developer that's running it, and you can, if you go into our repo today, you can just run this simple example. On the left here, we have BeaconD running, which is the consensus client. Then over either IPC or JSON RPC, it communicates with an execution client. And if you were to read into these logs, you'll see that they're basically talking back and forth, one building a block, saying, hey, are we good with this? And then basically moving the execution chain forward. And what this looks like when you actually run a full network is it looks very much like Ethereum, where you have all these different consensus nodes. They're all communicating with their execution client over that engine API, and then that's the whole blockchain system itself. On the execution layer, we have the ability for gossiping like ETH blocks and ETH transactions, and that allows the network to leverage that like P2P optimizations that have been done on Ethereum over the past 10 years. And on the consensus layer, we're able to come to consensus on the state of this chain really quickly, thanks to Comet BFT and all the work that has been done there. So at the end of the day, the coolest part, in my opinion, is that out of the box, if you're using BeaconKit and you're building on BeaconKit, you can use any Ethereum client you want. So obviously, you can use Geth. You can use Aragon, which is at this point a very, very far fork of Geth, or Turbo Geth for those who've been around a while. But you can also use some of the high-performance clients too, like Nethermind and Reth, who are really pushing forward, like how many gigagas per second can we go? If you're an enterprise user, you can use Besu and get all the benefits of Java and being able to plug into that ecosystem. And if you're like some members of our team and you really, really like sniffing glue, you can run ETH.js or Nimbus if you're really, really, really bold. So to kind of sum it up, at the end of the day, if you're running BeaconKit, you get a fully 100% EVM identical. If you run that smart contract on Ethereum mainnet, you run that smart contract on a BeaconKit chain, it's going to behave exactly the same. Absolutely zero forking. It is something that I will die on the hill of when it comes to BeaconKit. BeaconKit should forever be able to run any Ethereum execution client without any modifications made. Docker pull go Ethereum/client, Docker pull Nethermind, and it should just run. And exactly that, right? We want to be able to support as many clients as possible and leverage all the work that these execution client teams put in, day in, day out to keep those clients running well. And lastly, not only can BeaconKit be used for L1s, but by leveraging things like RollKit, we can also be able to run L2s. And that's really, really powerful because BeaconKit really is this first framework that can run, any layer you want. You want to run a layer 1, you want to run a layer 2, you want to run a layer 7, whatever you want. It's the first framework that allows you to run any standard unmodified execution client in any kind of format you like. And the way that we're able to achieve this, and some might say it's very much too good to be true, is through, this is Modular Summit, modularity. Am I missing a slide? No, we're good. And how this basically looks is what we've done architecturally is not only have we decoupled the execution client from the consensus client, but within the consensus client itself, we've actually decoupled our specific runtime that powers the EVM from the consensus engine completely. So in a traditional kind of Cosmos chain, the ABCI, or Comet chain, I should say, the ABCI lifecycle is actually what's powering the chain. But what we do is over on the BeaconKit in our code, we have modules that actually are powering themselves, and we run a service-based architecture to achieve this. And then all that's actually happening is when something about ABCI happens, so I use prepare proposal as an example, right? Prepare proposal doesn't actually trigger BeaconKit to build a block. All prepare proposal does is basically emit an event that tells our code to move forward and tells our code that something happened. So for instance, when a block is built, right, ABCI will come along and it'll be like, hey, this happened. And then our code basically just uses that as a point in time. So these events are essentially taking ABCI calls and things like that and basically allowing our runtime to create a canonical set of points in time. And if you look into our code base, we use this as an example as in Ethereum, we have the concept of slots, which are based on these 12-second intervals. But how we compute slots today is we actually define the length of a slot based on when ABCI is emitting certain events. And what's really powerful about that, though, and this is the coolest part in my opinion, is it, in theory, allows us to run any arbitrary consensus mechanism we want. So you could use Avalanche consensus, you could use hot stuff, you could use anything you want. All you have to do is write this little middleware piece that glues basically what Avalanche uses as its cadence, its ABCI thing. I don't know the details of, maybe it's Snowman, however you want to think about it. We can translate things that Avalanche know to things that BeaconKit can understand. And then all of the logic that's happening in the runtime over here is completely agnostic. It just sees hey, I received a block, hey, height increased, things like that. And it makes it ABCI makes it really easy to go and build new applications without having to worry about consensus. But we've also gone the other way where we can build these applications in a way that they don't care about what consensus is happening. And I think that's a really powerful thing in the future. One of the other things that I really, really thought was important was encoding. And in Cosmos and in a lot of people in general, they don't really think about how important this might be. But one of the things on Ethereum, and specifically ETH2, is this concept of SSL encoding. And what that is basically, it's called simple serialization. And what it is it's basically a way to serialize data that is natively Merkleizable. What's really powerful about this is after the latest Deneb upgrade on Ethereum, we have EIP 4788. And what this actually means is that the block root of the block is actually pushed into the EVM. And this is used by a lot of protocols. Eigenlayer, Lido is looking into this. We actually use it for our PLL prover, which we won't get into this in this talk, but effectively allows us to relay consensus information about who proposed a block, what the, how many transactions were in that block, et cetera. And proof of liquidity can actually leverage that data in a way that's completely decentralized because it's natively provable and Merkleizable, et cetera. Lastly, one of the things that we really spent a lot of time on was making the code modular itself and really ensuring that from a software architecture perspective, there was as minimal coupling as possible and making things really extensible. So for instance, we've broken down all of our kind of core pieces of the chain into their own modules. This has taken, a lot of the inspiration was actually taken from Reth in terms of their crates and having everything broken down. And we've kind of done the same thing. Additionally, I think this is something that's not really used in Go that wildly, at least at like this high of a level. But everything in our typing system is completely generic. So we've gone and spent the time to like fully genericize everything. And what's really powerful about that is it allows people to like get creative with how they're, building their own BeaconKit chain. I want this to have a different type, or I want to, inject a tracer into some block or something like that. As long as you're able to like create that hard type that implements the interface, you can add your own custom logic that way, which is super, super cool. Now, you may think that like all of these things are, adding a lot of overhead. But one of the things that I've personally spent a lot of time on is making sure that not only is BeaconKit modular, but it's super fast. And I will live and die by this statement. Some may disagree, but running a BeaconKit chain today is like the fastest, lowest resource way to run an EVM. It's stupid fast. So this data is actually real from our validator nodes on Bardio testnet, which is running the latest version of BeaconKit. These nodes like consume, like it's literally nothing. It's like half a gig of RAM, not even half a real CPU, like half a virtual CPU. And we're still able to achieve like super low block times. And one of the things that I think is really cool about this and what it enables is it enables running BeaconKit on like super low power devices. Which is really nice for eventually getting to this thing where instead of having to trust an RPC node, I can just run not even a light node, like literally a full node on my phone, or a Fire Stick is one of the jokes that we've made. You can just run it and verify things yourself, and I think that's like a super powerful thing to be able to do. But not only on the other side of the spectrum, you can think about it like what we've seen is if we throw hardware at it, we can actually achieve some like sane transaction throughput numbers. So this was an example that we cooked, I guess, last week. And it was running basically a combination of BeaconKit using an L2 on RollKit with a local version of Celestia running, and then Reth. And we were able to achieve, obviously this is the execution client pulling its weight, 3 gigagas per second. But mainly what was really cool about this is we could actually support around 30K transactions per block. This may be able to go even higher. We just kind of stopped the testing because we were like, that's a number that looks good on a slide. But what's really cool is that's actually testing the actual level of how hard the actual consensus client can go. And we can see that we can support these really, really large blocks, which may be useful for certain applications, right? Like if you need to support a lot of ETH transfers, or you have, your chain has some piece that really needs to go in and send a lot of transactions. It's cool to see that we can handle that level. Additionally, right, because we support the engine API, if we get into some cool things that are kind of in the works, not by us, but by people at Broad, if your parallel EVM supports the engine API, you can just plug it in, and that's kind of again showing that performance is always on the table, and being able to plug in the work of another execution team that's really striving for that shows kind of the modular extensiveness of BeaconKit, and it's super cool. So kind of tying it all together. BeaconKit, unmodified execution client, that's something that I will hold up forever, because I think that's one of the biggest value adds is that you don't have to change anything. Supports building L1s. Right now that's done via BFT. Supports building L2s. Right now that's done via RollKit. But again, right, based on this architecture, we're really thinking down the road about like what if somebody wants to write their own consensus thing, or plug in Avalanche as it is written in Go, something like that. One of the things I actually forgot to mention earlier is since we're using standard unmodified clients and we strive to maintain full EVM or EIP compliance, we actually have, BeaconKit has a built-in DA layer as well. So you can submit blobs, blob TXs on the EVM, and they will get stored and you can access them, et cetera. And then also because the client is modular, this is a great segue into, if we wanted to use another DA layer, you could totally do that, right? So we could, you could have it, so instead of just saving the blobs to the file system on your chain, you could use EIP 4844 endpoints on the execution client to like forward those blobs to Celestia, for instance. What else? Yeah, we got full Cancun support, so kind of tying into before, right? We're always going to be able to have all the latest features because the EIPs just come with the execution clients. And lastly, the thing that I personally find is like one of the most important things that I think is really people it kind of falls behind, not falls behind, but people don't like think about it, is that we support like the standard ETH2 SSL encoding, which will be really powerful for people building things that require cross-chain interoperability and proof-ability and those type of things. So yeah, to kind of sum it up, BeaconKit allows you to build your L1, L2, whatever you want to build. You can use BFT and RollKit today, but there's no reason why you can't start plugging in your own engine. And if there's anyone who's interested in doing that, I would love to chat with you, especially as we think about these APIs, et cetera. And some of the other things that we're also in the works right now. So, and if you're interested in working on these things, please reach out to me. An SSD native database. So we're actually looking at how we can store SSD data really efficiently on disk. We're building that basically for the purpose of reducing hashing over and over again. And that's where we're exploring building that on top of MDBX, which is a really, really powerful database there. Tying into SSZ and 4788, one of the things that we want to figure out how to build is this generalized execution client, consensus client, middleware piece that allows you to communicate data back and forth. The consensus client would read logs from the EVM, and then conversely, the consensus client could pass data in a provable way back to the EVM. And lastly, this modular architecture is really powerful because it allows us to test and verify and audit all these pieces individually. So one of the things that we're working on now, we're working with Informal on basically creating a formal spec and then eventually verifying that spec for kind of our core state transition module, but that could apply to any module in general, which is super cool. So thank you guys for coming so much. Again, if you're interested in working on any of these things, please reach out to me on Telegram, Twitter. It's all under the same header here. And check out the GitHub at Berachain/BeaconKit. Yeah, that's everything. Thank you guys for listening to my talk.
Thank you. Thank you very much, Devber. Wait. We have some time for the questions.
Yes, I do.
Some questions. Yeah. Can you wait for the microphone? Here is a question.
Hello. Yeah, very cool presentation. Thank you. So one question is that, so you mentioned at the start that scroll and all these ZK rollups or optimistic rollups, they don't have 100% compatible EVM. Mm-hmm. I'm not sure how this solves for that, because the reason they don't have a complete compatible EVM is because they have different implementations. They need to write the EVM in ZK circuits and all of that, or in case of Optimism, they have to support for a fraud the interactive fraud proof game for every opcode. So I can see how this is useful for L1s, which don't need that kind of construction Optimistic or ZK, but I'm not sure how this helps with L2s.
Sorry, could you repeat that last bit? Just one.
So yeah, I understand how this can be useful for all EVM L1s, but not for EVM L2s, because you need to have ZK or Optimistic there.
When you say you have ZK Optimistic, what do you mean by that exactly?
So why ZK Sync, Scroll, or all of these ZK rollups have a different EVM, which is not 100% compatible with the L1 EVM. The reason for that is because they have to implement every opcode in the ZK circuits, and that is super complicated for some opcodes, and that's why you can't have that 100% compatibility. So if I'm using this the Beacon Kit, I have an EVM which is out of the box EVM, but that's not a ZK EVM, or it's not a EVM which supports fraud proofs in case of optimistic rollup. So how can this really be used to build an L2 which supports either ZK or fraud proofs? I'm not sure of that.
So there's kind of multiple answers to that depending on how you want to look at it. The way that I always think about it is, if we can create on the beacon chain, if you think about it, just go back to it being an L1 just for a second, right? If we can create a beacon chain state transition function that is provable, right? And we know that that state transition function is bound by the rules of the EVM, kind of by proxy, you get that. Now, I fully acknowledge that that's not the same as a true ZK EVM, but in terms of the security properties there, you do end up with something that still checks all the boxes. Completely different way of doing it, and there's obviously other use cases that we want to have an EVM that's fully snarkable. But in terms of actually getting something that could be working, it would solve for that. But I do agree with your points that at the end of the day, there are fundamental limitations around hashing with the EVM that make it very difficult.
Thank you very much. We don't have more time for questions, so sorry. Maybe in the venue. Thank you once again, Devber, and big round of applause.
Thank you. Go this way, or can't see anything.
Okay, and right now on the stage there will be Larry Yu from Left Curve Software, and he'll tell you a bit more about GRAG. Big round of applause.
Hello. Hey, my name is Larry.
I founded a company called Left Curve Software, and we are building an execution layer for blockchains called Grok. So before we jump into Grok, I want to just give a bit of general thoughts on what it's like to building an execution layer in today's market. So, there are three aspects you can look at when evaluating an execution environment. There is speed, meaning just how many TPS you can do. There is security, meaning how many security pitfalls your developers can potentially fall into. And there is features, meaning how big of a toolkit you're providing to your developers for them to build their apps. Now, you can choose to spread your efforts evenly across these three aspects, and in the end, you might get a new execution that is, let's say, 1.2x better than the EVM, right? But, that's a good thing, that's cool, but I think that's just not going to have a very good of appeal in today's market. So the approach that we take for Grok is we want to pick only one of these aspects and really focus on that. And the objective is we're going to be 10x in that one aspect than any other alternative. And that, now you see, if there's some apps that really, really need that one aspect to be good, well, that is our natural customer. So that's how we carve up a niche in the market and grow from there. So that one aspect we picked is the features side. So our objective is that by providing a rich set of features, some applications that are difficult or just straight out impossible to build in other VMs are going to be easy to build in Grok. So for the rest of this talk, I will just walk you through some of my top favorite features that Grok uniquely offers. Feature number one is our smart account system. Now, Ethereum has EIP 3074, which I think is the right direction. However, our smart account system, I think, is more elegant and more powerful. And is just really simple. Let me talk you through about it. So on the right-hand side, it's the flowchart on how a transaction is handled in Grok. So when a blockchain receives a transaction, usually the first thing it does is to authenticate the transaction, meaning to make sure the transaction comes from the rightful owner of its sender account. Typically, this is done by including a cryptographic signature in the transaction, and the blockchain will verify that signature. The drawback of doing that is the blockchain needs to kind of enshrine a signature scheme in the chain's logic, and that is not flexible, meaning the account cannot choose which scheme it uses. So if at one point there's a new scheme emerges that's better in UX, better in security, well, it's not very flexible. So we take a very different approach. Instead of a cryptographic signature, you see in bottom left, our transaction includes a field called credential, which is just a generic JSON value. The blockchain does not attempt to interpret this value, nor does it attempt to do anything with it. Instead, each account in Grok is a smart contract, and that smart contract must expose a special function called before transaction. So on the top right, the first step of handling a transaction is to call the before transaction method. In this method, the contract is provided with the details of transaction, including what are the messages, function calls are in there, and what is the credential. And it is up to the contract to interpret that credential and do anything about it. So this is the most flexible authentication scheme ever because the contract can literally do anything it is programmed to do. So it can be a cryptographic signature, it can be a one-time password, it can be a hardware key, it can be a combination of the above. So anything you can imagine is totally up to the contract programmer. So after that step, we move on to execute that transaction. And after that, it is our second major innovation in this account system is we call back into the account contract again, another special method called after transaction, and the account can do whatever it's programmed to do. So this opens a lot of possibilities. I'll just tell you two of them. One is that you can set a daily outflow limit in your account. In the before transaction function, you calculate the total value of your account. And in the after transaction function, you calculate that again, And if that decreases too fast, well, you can reject the transaction. Now, if you implement this correctly, that can pretty much prevent majority of the hacks. If it just, your account literally doesn't allow its own value to drop too fast. That just prevents hacks, right? And the second use case is a financial use case called credit account. So this is a new DeFi primitive where your account is allowed to take uncollateralized loans. And this is only possible because of two things. One, in the after transaction hook, we can compute the account's health factor. And if that transaction causes your health factor to drop too much, we reject that transaction. And the second fact is because our account, each account is a contract, we can build in liquidation mechanism into that account. So these two things combined make it possible to allow the account to take uncollateralized loans. So this is a DeFi primitive uniquely enabled by Grok. Now, it would be dishonest for me to not mention Mars protocol, which I worked for prior to working on Grok. Mars implemented credit account in CosmWasm. So it's not saying it is impossible to do that in other execution environments other than Grok, but it's just really, really, really difficult. In fact, we estimate that if the credit account had used Grok, the size of the code base can be reduced by 70% easily. So that is just how easy Grok makes to write this kind of complex financial applications. Okay, second feature is flexible fees. You might notice that there's one last step in the transaction flowchart I didn't mention, and that is where we handle the transaction's gas fee. So different from every other blockchain in existence, gas fee in Grok is handled by a smart contract that is appointed by the chain's governance. So inside that contract needs to expose a special function called handle gas, which is called after each transaction. In that function, the contract, which we call taxman is provided with the details of the transaction's gas consumption, and it can be programmed to do whatever the developer wants it to do. So I'll just give you a few examples of what you can do about this. Maybe you don't like the floating gas fee in EIP 1559, so you can implement a flat gas fee, or maybe you don't like burning your fee, you want to distribute that to stakers, you can just program that in your taxman contract. Or maybe you can allow the account users to pay gas fee in any asset. If that is not an asset you want, you can just swap that in your DEX. Maybe you can say, oh, we want to give holders of a certain NFT a discount in gas fee, you can do that. Maybe you want to give some new users some free transactions, you can do that. Maybe you're running an order book, you say, oh, if you put a limit order that doesn't eventually get filled, maybe we can give them a refund, you can do that. So this may or may not be a good idea, I'm just showing all the possibilities, right? And if at any time you don't like your current gas fee mechanism, you want to change one, you don't have to fork your chain, you just upgrade that one contract. That's all you need to do. So makes it super simple. Feature 3 is cron jobs. Cron jobs means tasks that need to be executed at regular time intervals. For example, an order book exchange needs to find matching orders and execute them like every block. A perpetual futures exchange will need to update the funding rates of their markets based on the open interests, long and shorts, every once in a while. So these are cron jobs. Now, in traditional blockchains, these actions needs to be triggered by transactions. So if you're using OP Stack or EVM or Solana VM, you have to run bots to send transactions to the chain to have these things done at regular time intervals. But in Grok, this is baked into the blockchain. So how do we do that? Well, we borrowed this concept from Cosmos that, well, this is our flowchart for handling the entire block, right? When we receive the block, there's a list of contracts called begin blockers that is appointed by the chain's governance. It will just be called a special function called before block one by one. So if you are running an order book or a perps exchange, you can do that things in your begin before block, And then it go on to process the transactions one by one. And after that, there's another queue of contracts called after block. Will also be called one by one. So that is where you can do some of other tasks. So apparently, before and after blockers needs to be appointed by governance because these function calls are unlimited in gas. So we don't want somebody to put in like an infinite loop in them. But you can imagine programming a contract that has some sort of limited gas ceiling and use some sort of auction methods to select, permissionlessly select these contracts. So that's something we can do, right? The fourth feature is our token standard. Everybody hates ERC20, I'm pretty sure. But exactly why are ERC20 bad? I can think of 6 reasons. One, every ERC20 is a separate contract that has its own state. And it just happens also that Ethereum transaction, each transaction can only call one contract natively. So that means each transaction you can only send one token, right? Now imagine you have 30 tokens in your account. You want to migrate them to another, well, that's 30 transactions for you. So that's the first drawback. Second drawback, you cannot send a token to another contract and then immediately call a method on that contract. So that is why when you swap on Uniswap, it asks you to approve a spending limit and then withdraws that. In a second transaction, it withdraws that spending limit from your account. Now, there are some newer standards like ERC 677 that adds a new method called transfer and call, but still, you can only transfer and call with one token per transaction. So if you're providing liquidity to Uniswap that requires 2 assets, well, you still can't do that. The third thing, the recipients cannot reject a transaction. So that we've seen a lot of instances where people sending assets to a contract and that results in permanent loss that cannot be prevented. And the next 2 things are related to queries. Given an account, I want you to list all the assets held by this account. Impossible, because each token is a separate contract that needs to be queried separately. If there are 1,000 tokens out there, I need to make 1,000 queries. That's just ridiculous. Given a token, I want you to list all its holders. Impossible, and that is for a different reason. That's due to the Merkle-Patrizia tree that Ethereum uses. It hashes all the keys and values. So because those values are hashed, you cannot iterate them. So this is a fundamental flaw in the Ethereum design that is just too late to fix. Finally, not a drawback in of itself, but fungible and non-fungible tokens are 2 standards. Wouldn't it be better if we can manage them under one roof, right? So Grok solves all of these problems. So let's start with the queries. On the right is an example of what happens if you query an account's token balances. You just say, hey, this is the account address, tell me all the token balances, and the query just gives you a list of results, as simple as that. And also, NFT. Each NFT is just a one supply fungible token, right? So we can manage NFTs and fungible tokens under one single standard. So in the example here, you see I have Bad Kids. If Bad Kids was using Grok, this is what you can do. Recipients can reject token transfer. Each account must implement a special method called receive. So each account can examine, oh, which assets were sent to me, who sent it to me. If I don't like it, I can reject it. And finally, you can, when you call a contract, you can attach any number of fungible or non-fungible tokens as a payload, and the contract can just then do whatever it is programmed to do. So I hope it convinces you it's a much better token standard. Cosmos IBC is natively enshrined as a native bridging solution, so that allows you to onboard users seamlessly from every ecosystem. I'm listing some possibilities here, not endorsing any of these protocols, just give you an example of what can be done. And this is for the nerds. We have a lot of quality of life improvements for you. Our transactions are natively multi-call. If you have a mapping data type, you can iterate them. We have null types in Solidity. If you have a number, that number is 0. it's not possible for you to tell whether that number is simply uninitialized or it's actually a 0, right? We have null type. Contrast can be upgradable, no need for proxy patterns, no need to worry about you mess up the state. Call data are human readable, and reentrancy attacks are simply impossible in Grok. So that's some of the top features. Our roadmap, we are thinking about tagging a release candidate in Q1 of next year. As that, we are not really focusing on performance, we are focusing on features. However, I think even without any serious efforts into optimization, we can still do 1000 TPS, which is, I think, enough for a lot of the applications. We are going to launch a chain, we're going to have a token, and we're going to ship the first few consumer apps ourselves. So post-launch, we're going to do a few more things. There will be a solution to state bloating, which is believed to be the biggest hurdle in Ethereum scaling. We're going to have a solution to that. We're going to think about parallel processing with block STM. And finally, we want to also ZK-proof our execution. So that's all. Oh, right. One last thing is we built Grok by standing on the shoulders of giants. And specifically, this giant is CosmWasm. We are inspired by CosmWasm. It would be literally not possible. It would literally not exist if CosmWasm didn't exist. So thank you to CosmWasm creators and developers. And finally, this is our Discord channel. If you would like to chat, please scan the QR code, take a picture, post on Twitter, and thank you.
Thank you, Larry. Unfortunately, we don't have time for many questions, so thank you. Our next speaker will be Rushi Mancha from Movement Labs, and he'll tell you a bit more about embracing modularity. So let's give him a big round of applause.
Hello, hello. I thought I made the title a little bit more fun. Think the original title was a little bit boring, but the future of Gmove. I think I've spanned this thing over like 3 times a day, 4 times a day, and now time to be like going a little tech a little bit. I'll walk through a quick agenda, just glossary, context, problem, solution, architecture, and kind of where we're headed. Starting with glossary, I think we'll start off with a sequencer. I know we've been chatting with Astria, Espresso, a few of these other sequencers. No, we're not a shared sequencer business, but I think we're entering this era where a lot of these layer 2s are coming out with their own shared sequencers. You have Optimism Superchain, you have ZK Sync working on a superchain. Aglair itself is working with a few shared sequencers. So for Movement's network, we envision a network of high throughput rollups that all want to share state and sync across. The biggest issue with this, when you have thousands of rollups, especially those that are different VMs, is how do you sync state across rollups? Specifically state finality guarantees, which I'll get more into later. But we have M1, which is our decentralized sequencer network. We have the Movement L2 itself, which is kind of the main bread and butter. A VM as a virtual machine, I don't think I need to explain this, but it is the execution layer where folks deploy apps. If you're using Uniswap, Curve, Aave, any of these things, you're probably on the EVM. And then with this modularity thesis, we've seen a Cambrian explosion of different VMs. We have the Solana VM, we have the Move VM, we have Wasm-based VMs and future VMs coming to market. And we're all here for the experimentation. The Movement SDK is a software kit to execute smart contracts on the layer 2 itself. The Move VM itself is, I'll get more into the kind of history and where it comes from. Fractal is the EVM interpreter. So I think the one thing that we specialize in, I'll go into architecture as well, is we recognize that new tech is pretty cool, but it has to have backwards compatibility. Majority of developers today are Solidity, so the question is, how do you onboard new developers and new apps? I think 2 of the layer 1s, Aptos and Sui, try bringing Move to market, but it's a slow process teaching people languages. Solana took 4 years to kind of kick off and took some time. The first Solana wallet, if you guys remember, it was pretty poor, and then it took like 2 or 3 years until the infrastructure got there. And Move is still in that early nascent stage where infrastructure is still developing, teams are still developing, so it's important to also have even compatibility, which is where Fractal will get into. DA layer, I don't think I need to explain this to you guys. I think Nick White can explain it better than I can. So context, Solidity is the most commonly used smart contract language. Most people have written it, probably hate it. There's over $7.6 billion lost so far. Increases the barriers to entry, but more importantly, this chart. This chart is a loom groom and why none of your parents, family, or anyone can trust crypto. There's over 4.5 this year in billions lost in hacker attacks this year. Some of the notable exploits are private key compromises, registry attacks, flash loans, math mistakes. Like 2% of all attacks in crypto are just because you added the wrong number. So it's like if you did 256, if it's a 256-bit limit and you did 257, congratulations, you lost $50 million. In traditional tech, if you get hacked, like when Facebook and Mark Zuckerberg started Facebook, you just lose a few files and it's not the end of the world. You get hacked in crypto, you lose your entire user base, and most importantly, trust overnight. Because crypto is so reputation-based, it's extremely important to have security, especially at runtime. So the part of the work we're doing at Movement is to really bring the security landscape to the forefront where users, developers can trust the system that we're building, and modularity itself can bring security to the forefront of discussions. So context, for those that aren't familiar, there was a DM program around 6 years ago. Facebook essentially put $1 billion in the blockchain. It was like, we're going to have a Facebook blockchain, essentially USDC or their equivalent, floating from New York to Thailand at the speed of light. So you didn't need to send WhatsApp, you didn't need to send PayPal or Venmo. You could do it within Facebook itself. They had all these partnerships and all this work laid out. SEC is like, nah, you can't do that. Thanks, Gensler. But the language was still really powerful, right? It was a new paradigm of resource-oriented programming. You have formal verification built into runtime. And most importantly, you also have block STM. A lot of the parallelization engines that you know and love today, like Monad, Aptos, Sui, et cetera, are all variants of this original research done at Facebook, which was this optimistic parallelization engine known as block STM. So what Move does is brings the security and speed in one VM, and our mission is to bring it to Ethereum. So can we enable safer smart contracts within Ethereum? Can we bring Move to Ethereum? I think so. And our solution is a Move-based rollup on Ethereum. I won't get too into rollups because I think we've kind of nagged on that a lot. But there's two main categories of rollups. You have optimistic rollups, which have fraud proofs and challenge periods. And you have ZK rollups, which are validity proofs, fast but computationally expensive. I think most of the rollups coming to market in the early stages, like Arbitrum Optimism, with optimistic proofs, optimistic rollups, and then you had ZK Sync Scroll bringing ZK rollups to market. And we're kind of in this weird stance because now we have these next-gen rollups coming to market. So you have optimistic, ZK, and next-gen rollups. The question is, what's the right architecture? Is it optimistic and ZK? I would still say we're pretty early on where it's still very computationally expensive to do a ZK Move VM or a ZK SVM. If you have to write custom circuits, it's probably a 3-year project. And it's a whole different company, honestly. We barely even solved it for the EVM, so doing it for next-gen VM is rather difficult. I think a good middle ground that we reach is ZK fraud proofs, which kind of blends the kind of mix here, where it's still an optimistic rollup technically, but you can use validity proofs in ZK when you're doing challenge periods. So you only use ZK when you need it. And that's kind of where we're getting into and kind of blending it. So for starting, we're going to have an optimistic rollup, but the 6, 7, 10-year end game is a fully end-to-end ZK rollup. And I think a lot of the ZK researchers agree that the end game is ZK. We believe in validity proofs. It's a little difficult to get there, but I think we're getting there. And that's also end game for movement. So the final architecture is a Move-based ZK rollup. We say ZK fraud proofs to start off with, and then migrating to a validity proof network eventually. M2 makes most sense because A, you have all the benefits of safe execution environments like Move with the high throughput parallelized environment with Ethereum. It's kind of the best of both worlds where if you built on Aptos and Sui, you might have been pushed off by the lack of liquidity, maybe the vibes. But the two main issues for building apps in these new layer ones is A, acquiring liquidity, and B, acquiring mindshare and user base. For context, I built the first DEX on Aptos. This was August 2022, and it was pretty awful. There's like APT and testnet like DEX token, which meant the DEX was kind of useless, right? No one wants to trade 1.5 assets and doesn't really get anywhere. So it's that same DEX can deploy on top of Movement. You still get all the benefits of Move, but you have native ETH directly from Ethereum. You have low fees because of Celestia and alternative DAs. So you're able to bring essentially these different parts of the stacks in one combined environment. So you have all the benefits of Aptos and Sui while living on Ethereum with liquidity and security while still having low fees. So this end game is when we can finally have these layer 2s challenge the throughput and security and speed of layer 1s. And we have a few folks do for the SVM, MoveVM, parallelized EVM, and the next gen is the future for sure. A little bit in the architecture. I'll kind of walk through everything. I know I have 10 minutes, but the movement SDK is where the main block building happens. Proof of marketplace is kind of on how we generate fraud proofs and validity proofs eventually on, and how we settle on L1. So the EVM compatibility is kind of the bread and butter, because a lot of you guys are like, okay, Move is dead. There's like 5 Move developers, and I argue that's true. It's very difficult to build a new language. Solana was barely able to do it, and they pulled it off. Most other alt programming languages kind of die off. I think there's a cause of 2 issues. A, there's no backwards compatibility. If you're a Solidity developer right now, for most L1s, even if you want to try the ecosystem, it's pretty difficult to do so, because you need to learn new language, you need to learn new kind of SDKs, and there's so many programming languages, so why would you do that? And secondly, the kind of go-to-market strategy is relatively difficult, because you can't give people the taste of the ecosystem. You're pretty much isolating yourself, so you yourself and your 5 devs, so that's why some of the L1s have issues. With Movement, we have full end-to-end EVM compatibility at the bytecode level. We support Solidity smart contracts, as well as Move smart contracts, compile them to one bytecode, and settle them on the Move VM. Here's a little bit how that translation process happens. I won't get too into it. You can ask questions if you're interested. But essentially, you take the Solidity script, parse it down to AST, which is an abstract syntax tree. You go to intermediary language called UL, which is more similar to assembly. You map those UL opcodes, so you have like 142 Solidity opcodes. You map those to the 54 Move opcodes, and you deploy them on top of the VM itself. It's similar to like Soling on Solana, but actually useful. And then I think similar to Neon. I don't really know what's up there, but it's completely end-to-end compile SDK level. So it's not a bridge at all. I think Neon's more of a bridge from Solana to the EVM. I'm not too sure. This works at runtime. There's no latency issues. So I would say like 60% of the ecosystem right now is EVM, which is fine. We acknowledge that there's very few Move developers right now. We're going to work our asses off to get more Move mindshare. The goal is 10% by the end of the year. But even if you don't like Move, you can still be in Movement. Let's see, go through this. So decentralized sequencers, pretty hot topic. Some people say centralization sequencers are the end game, and we want to prioritize UX. And some people say decentralized sequencers and shared sequencers are the future, because you want interop. I would say the correct answer is both. If you're a gaming role prioritizing high throughput rollups or high throughput capacities, you should choose a centralized sequencer today. If you use a decentralized sequencer, there'll be latencies and trade-offs, and you don't necessarily need a shared sequencer. If you're building a fully on-chain MMO, you don't need to have composability with a yield aggregator. It doesn't make sense. You're focused on user experience. You don't need to take the latency. I think secondly, what's really interesting is there are use cases that need shared sequencing. For example, if you're a yield aggregator rollup, imagine if Yearn launched a rollup. They want people to compose with other assets. Maybe it's the GameFi assets they want to roll in. Maybe it's Orbook assets they want to roll in. And for that, shared sequencers are really important. Commonly, the issue is if you have a bridge, you have to read light clients from each different rollup, which is kind of low, slow, clunky, and bad UX. For the first time, if you have shared sequencers, you can read state directly from the shared sequencer itself. So for us, we have a stack which is execution layer stack. You can use whatever role framework, use whatever DA, and then use the Move VM and connect to the shared sequencer. That way you have one unified execution layer and one sequencer to connect. If you don't want to use the shared sequencer, that's fine. We'll still love and embrace you, and you can still be part of the community. But we believe that there's a lot of use cases that demand shared sequencers. So the end game is kind of this both economy, where you can choose whatever you want, build whatever. But there's some use cases, and I would say most use cases actually would prefer shared sequencers. And most importantly, we're getting into token economics here. Most L2 tokens are meme coins. They're just governance tokens that have no actual value accrual. What's really interesting is when you decentralize a sequencer, now you have MEV, you have robustness, you have censorship resistance. You have all these principles that we work so hard for. That's not just one AWS node that's running billions and billions of dollars. So I think Starknet just announced today that they're enabling staking. All the rollups will eventually decentralize. Yes, Arbitrum is making billions off this sequencer, but the end game is decentralized sequencers and finally giving value accrual back to tokens. So M1, as it stands right now, is a common BFT Tendermint consensus. No, it's just not another consensus, Cosmos chain we slapped on. What's really interesting is a lot of this shared sequencers are working transaction finality, but that's not the main bottleneck for shared sequencers. It's state finality guarantees. If you're Arbitrum trying to bridge to optimism, how do you ensure that the state is synchronous across different rollups? Right now, there's no real solution to that. There's two main proposer solutions. It was either ZK state proofs, which what Lagrange is working on, or you need economic guarantees to back up the state between rollups. So what gets really interesting here is you can actually make the shared sequencer fundamentally like a staking hub, where if you have 4 different rollups all joining one shared sequencer, they can all delegate X amount of stake. So if I'm Arbitrum, I can delegate $1 million worth of Arbitrum to this shared sequencing pool. Optimism can delegate OP $1 million worth, and then you have to be honest about your state finality, otherwise you will get slashed. So that state finality guarantees introduces a new paradigm. It's very, very R&D, I will preface this. It hasn't really been implemented, but it's something that our research team, our head of research worked to Mantle and designed their shared sequencer kind of implementation, but it's something that we're thinking into, because if we're ever going to get to this end game where people actually care about shared sequencers, transaction finality is not the main issue, it's state finality guarantees. So how do we get there is the main question for us. So yeah, proof of stake, again, native staking token is what gets me up and going. Like, how do we make L2 tokens actually great again? And staking is the way you enable this. You have, if I'm a validator, I stake the move token or alternative tokens to receive emissions, and then I get transaction fees for multiple rollups. And then I can use that tokens to run more and more nodes. So you actually have L1 principles that can be applied to layer 2 solutions, which solves a lot of the paradigms we're seeing where layer 2 tokens don't really scale and don't really compete with layer 1 tokens. But now I think we're entering this mechanism where we can have creativity, we can have MEV, we can have deep, deep MEV research. Imagine Jito for Arbitrum. That'd be pretty cool, right? So yeah, multi-taking stoking, native DA tokens, etc. I know I have 3 minutes, so let me go into the ZK side. Again, another research article or research part that we're looking into. ZK next-gen is pretty difficult to do. I think we benchmarked that it still costs around 4 to 5 cents per transaction using Rister's latest benchmarks, which for us is pretty expensive considering our transaction fees are 1 cent to 2 cents. We're trying to get there. So right now, I don't think ZK is there for like ZK Move or ZK SVM, even though teams have kind of implemented it. There's a team that did it for Halo 2, and it was pretty expensive. But I think Succinct is working on making it more accessible, so we're looking to presenting research with them, where provers can generate the proof. Right now, we can use Plonky 3 for Movium. Right now, Plonky 2 is a past example, but with Succinct, you should be able to do Plonky 3 with field encoding, custom gates, and optimizations. The main thing is having recursive proof generation. But until we get there, ZK fraud proofs are pretty good. Again, most users don't care about validity proofs or how decentralized the proof generation is. They just want great user experience. So ZK fraud proofs and optimistic rollups are good enough for the time period. And then once we get the point where ZK proof generation is cheap, and most importantly, proof verification is cheap, we can get to a point where we can have ZK Move and ZK Next-Gen VMs. And yeah, other components, obviously settling on Ethereum. You have a validating bridge smart contract and full nodes. Let's see what else. So yeah, where we are today and what we're launching testnet in 2 weeks. Public testnet, we had private testnet go live a week ago. Have our core teams building on. Intermediate goal is movement as optimistic rollup, ZK fraud proofs, executions movement SDK, sequencing with our M1 network, data availability with Celestia, and then ZK proof generation with Rister right now. And we're next having our SDK go live, having the ZK rollup go live. Hopefully we can get to the point where proof generation and verification is down, so we can have fast, high throughput rollups with ZK, and then shared sequencer. And finally, use cases for infra. I think yesterday we announced the first, or the movement phone. I don't know if it's the first movement native phone, but I think mobile is really where we're getting at, where it's finally use cases for apps. We have high throughput chains, high throughput environments. We have a team based in Kyoto that sold 10,000 phones already. It's called Network HQ, you should check it out. But they can have a fully on-chain, decentralized DeepIn product that's going to pick up a lot of steam in Japan. But yeah, use cases for infra, enabled by high throughput infra, and yeah, getting right there. Thank you.
Thank you very much. We have time for questions. Are there any? Yep. Wait for the microphone.
So do you still get all the benefits of Move when you are writing your contract in Solidity and just having it like transpiled into MoveVM?
So you have the parallelization. You have the parallelization benefits, but you don't get the security benefits. And that's marked because to get the benefits of security of Move, you need the Move prover to verify correctness of Move code. But if you want our EVM, it'll be high throughput, but you won't get security benefits. So it's up to your use case. If you care about security, it's fine. If you don't, you don't.
Got it. Thank you.
So how do you exactly get the parallelization benefit for EVM? So I mean, I was attending like the talk by, you know, Monad yesterday, like about how they are doing like the parallel EVM, and basically like you have to make sure, right, like the accounts are not being shared, like the Solidity programming paradigm, basically how it's ensured and stuff like that. So how do you exactly make it happen? I mean, because I guess if just the transpilation layer, then you can like yeah, exactly. Like, I'm just want to know how
The best thing is that we don't need to worry about that. We use the move EVM. With Mana and other EVMs, we have to rewrite the EVM from scratch, and that's the execution layer. We're still using the move VM. So if you write Solidity code, you essentially interpret down to move bytecode. So it's still move bytecode being executed. The Solidity accounts get mapped to move accounts and move account modules, and those are executed. So we still retain the parallelization of move, but you have essentially a layer on top that enables Solidity smart contracts. It's probably not going to be as performant as the most parallelized EVMs, but the thesis is we'll support backwards compatibility. The best performance will be on move, and we'll market that and advertise that and encourage move developers. But it'll still be pretty darn good if you write EVM.
So it's kind of like it's Solidity compatible, but not EVM compatible per se, like the smart contracts.
I mean, that's been thrown around, EVM compatible, EVM equivalent. It's Solidity code you can deploy Uniswap in 10 minutes, whatever that takes or means to you.
All right.
Thank you. Thank you very much for the questions. We don't have time for more, sorry.
I'll come talk.
Yeah, thank you once again for the presentation. Big round of applause. And right now we have the last item on our agenda for today. This is the fire chat with Mustafa. It will be between Mustafa and Laura Shin. So let's welcome them on the stage in a second. We need to set it up. It's ready? Okay, so let's welcome Mustafa and Laura on the stage. Let's give them a big round of applause.
Hi, everyone. Thanks for coming to this fireside chat with me and Mustafa. So some of you might know that he has a very interesting personal story. So we're actually going to start with that. As a teenager, you were what's called a hacktivist. You were involved in LulzSec, or I think that was your group, and Anonymous. But before we get to that story, I just want to even hear about your childhood, because that, I feel like, sort of sets the stage for what happened next.
Yeah, sure. Sorry. So, I was born in Iraq, in Baghdad, and I moved to the UK as a refugee when I was 5, moved to London. And I, this was southeast, London on a housing estate. And I had my first experience with a computer when I was 6 or 5. And this was a Windows 95 computer. And that was my first introduction to computers. And from there, I I was just very curious, and I think this is it's actually a very common story with a lot of people who learn programming from an early age. And I came across software like Microsoft Front Page, which was this software in the Microsoft Office suite that lets you create your own website. And I experimented with that, and that's how I first got into technology and coding.
And so from there, how did you end up, I guess, engaging with these different hackers and becoming a hacker yourself?
Yeah, so I started to figure out how to create my own websites using programming languages like PHP. And as I was doing that, I realized the ways that people could make mistakes, or programmers could make mistakes when they're creating or programming their websites to create security flaws. And as I was thinking about that, I every time I would visit a website, I would see if it's vulnerable to what I think it's vulnerable to. So for example, one day I was doing my maths homework, I didn't have a calculator with me, so I Googled for online calculator, and it turned out there was this flaw in the calculator that you can, instead of typing 1 + 1 in the calculator, you could type in computer code into the calculator and execute that computer code. And this was a calculator that was run on this like American university server. So that was it was really interesting to me that you could hack a university through a broken calculator on their website. And that's kind of like how I first realized that you could actually hack into things, or things could have security flaws. But then I was also very interested in accessing software or media that I couldn't afford to access at the time. And back then, the BitTorrent and the Pirate Bay was a very popular way of accessing that kind of information for free. This was like before Netflix existed or other streaming services existed. And to me, BitTorrent was really interesting because it was like a peer-to-peer file sharing system that did not rely on centralized entities. And to me, it was evidence that we didn't need a centralized internet. But I first got into activism when there was a group called Anonymous that was conducting a denial of service attack against the Motion Picture Association of America and the RIAA, which was trying to take down the Pirate Bay. And then these people kind of organized a denial of service attack against those companies. And then so I kind of got involved into these hacker chat rooms, and that's how I kind of got into the hacker scene. And then it kind of ended up with me creating my own hacker group called LulzSec that kind of, in the summer of 2011, went into a kind of like a massive hacking spree that hacked into all kinds of organizations like Sony, FBI affiliates, Fox News, and like a bunch of other corporations, including military contractors.
And so there's just so many stories there, but do you have any favorites?
Yeah, I mean, so like I guess like part of the point of it was political, but a big part of it was back then, no one was taking security seriously. So the only way to show people that they weren't taking security seriously was to kind of show that the emperor had no clothes. So for example, there was a company called HB Gary Federal, which was a military contractor or defense contractor to the US Department of Defense. And the CEO used the same password for his World of Warcraft account as he did for his PayPal account and his emails and his company emails. And it wasn't because we were great hackers that we were able to do this. It's because people were doing dumb things like using the same password everywhere, for example. Or their websites were vulnerable to very basic vulnerabilities that everyone knows exists. But no one had the balls at the time to kind of like actually hack those companies and show that the emperor had no clothes. So it's kind of like a issue that everyone knew existed, but couldn't do anything about it.
And since that was like a government contractor, did they end up just getting no more work from that seems like a really bad breach.
Yeah, I mean, the CEO had to end up resigning. And I think there was like an investigation into them in Congress about how that happened.
And you were how old when you did that?
This was when I was 15 to 16.
I love it. And I mean, there are so many others. Like I listed a bunch, and you could really pick any other story that you want to tell. Like the Westboro Baptist Church was also kind of a funny one. Sony, there's another thing involving the Arab Spring that, yeah, I don't know if you want to tell another story.
Yeah, so I mean, Sony was a fun one because this was in the summer of 2011. There was kind of like big hack. Like the PlayStation Network was down for like a month, and like a lot of kids everywhere were really angry that the PlayStation Network was down. But Sony is a perfect hacker target, or was a perfect hacker target at the time, because they just had prosecuted George Hotz for breaking the DRM of the Sony, and because he managed to install Linux on the PS3. And because it was such a great hacker target, like Sony was hacked around 30 times, or like in the summer of 2011, and they were hacked so many times by all these different people that it kind of like became a game to see who can hack them the most. So someone was keeping track, and it was like we hacked them 7 times, and this other hacker hacked them 6 times. So it was kind of like we won the race against this other hacker to see who can hack them the most in different ways. Like, you know, you had like Sony Pictures, Sony Music. They have so many different areas of their business and so many, like, such a big attack surface to attack. Westboro Baptist Church was also a fun one. So Westboro Baptist Church is this really controversial kind of hate group in the US that pickets, for example, the funerals of dead soldiers to say that they deserve to die because they were gay, and that kind of thing. And they kind of put out a press release challenging us to hack them. I think it makes sense for them because they need attention, but we managed to kind of hack them and hack their website on a live radio show. And it was kind of like they were being interviewed, and in the middle of the radio show, we kind of like put up, defaced their webpage, and then that video online, you can watch that video on YouTube. It's got like 3 million views on YouTube.
I love it. I love it. This is just so interesting because you were a teenager, as we mentioned, and so then at the age of 16, you got arrested. How did that happen, and what was that like?
Yeah, so I was arrested, and it turned out that there was an FBI informant in the group. He wasn't originally an FBI informant, but because he had 2 children that he was looking after, when he was caught by the FBI, he kind of turned into an informant that was logging everyone's chats in the chat rooms. And yeah, so I was arrested when I was 16, 1 month after I finished my exams. So that's pretty convenient, because if it was before, then it would have been more annoying. But and then I was arrested, and I was taken to like a police station, and they did like a separate charge for each pack. So they had like 80 charges, and they have to arrest you for each charge. So every time they arrest you, they have to caution you by saying something along the lines of, "You're not under arrest for this. You don't have to say anything, but if you do not say something that you later rely on in court, then this might harm your defense." They had to say that. They were supposed to say that 80 times for each arrest. But I gave a no-comment interview, so my answer to each question they were asking was like no comment, because that's what I was advised by my lawyer to do. But they only managed to finish arresting me 40 times instead of 80 times, because there was a time limit to how long you can keep someone under 18 in custody without charging them. And unless it was for terrorism, or I had some excuse like I was a terrorist or something, which I wasn't. And so they didn't manage to finish arresting me.
I can't even imagine what your parents must have thought. They probably were just like, what is going on?
Yeah, they had no idea.
All right, so clearly he's got a colorful history, and then he gets into crypto. So you got into Bitcoin. How did you go from that to getting into Bitcoin?
Yeah, I mean, I was kind of like very naturally interested in Bitcoin because of my interest in BitTorrent and the Pirate Bay. Like when I was using BitTorrent, which was just a peer-to-peer file sharing system, I was interested to see, okay, like we can have decentralized file sharing. What else can be decentralized? So like, even before Bitcoin, people were trying to decentralize all kinds of things. Like so people were trying to create like a decentralized domain name system because they were worried that the Pirate Bay domain name would get shut down by ICANN, for example. They were trying to create like decentralized social media because they thought like Facebook would censor stuff during the Arab Spring, for example, or governments would try to censor that kind of thing. So when Bitcoin was came around, that was kind of like naturally piqued my interest. And our hacker group accepted Bitcoin donations at the time, so that was kind of my first experience with Bitcoin. And it was also the case that, for example, WikiLeaks accepted donations in Bitcoin because they were blocked by Visa and MasterCard, so they had to use Bitcoin to accept donations. So that kind of like, that's when I first learned around Bitcoin in 2009, 2010, and that's when I kind of started following it. But then I was arrested in 2011, and I was not allowed to use internet according to my bail conditions for 2 years. So then I kind of like came back online in 2013, and I started following the space more closely in terms of the scalability debates, because at the time, like there was this 1 megabyte block size limit, and I was kind of like worried. I was like very into Bitcoin, so I was like, okay, at the time the main narrative was let's make Bitcoin accepted everywhere for payments, and retailers, even Microsoft, started accepting Bitcoin for payments, and different companies were experimenting with it. But then I was worried, okay, there's this 1 megabyte block size limit. What happens if it gets hit? So I started discussing this in these core developer chat rooms, and people weren't really worried about it. But then in 2013, the block size limit did actually get hit, and there was this huge internal war within the Bitcoin community about whether we should increase the block size or keep the block size small but scale with payment channels. And I was kind of very much on the side of increasing the block size. But the reason why they didn't want to increase the block size is because they thought it would make it more expensive to verify the chain, or for end users to run a full node to verify the chain, which kind of defeats the whole decentralized nature of Bitcoin. But in the Bitcoin white paper, Satoshi mentions this idea of fraud proofs, or what he calls alerts, which is the idea that a end user running a wallet on their phone, if even though they're not verifying every transaction in the chain, they could be alerted to an invalid block by a full node that has detected that there's an invalid block. But this was like a very nascent idea that wasn't fully fleshed out, and there was problems to it, including the data availability problem. So then I kind of decided to focus a lot on layer 1 scaling and how do we square this dilemma between decentralization and scalability.
And so what year was that?
So this was like 2013, 2014 when we started hitting the block size limit, and then in 2016 I started doing a PhD at UCL focusing on layer 1 scaling.
Okay, yeah, because in my head at least the block size wars didn't get settled until 2017 with Bitcoin Cash. And even now, sometimes they still flare up again in case of, I don't know, some of you might notice that. But I guess at that point, that brings us to Celestia. So how did you go from that point to founding Celestia?
Yeah, so the current approach or the current thinking around how we should scale layer 1s, especially within the Ethereum community around 2016, 2017, was mainly centered around this idea of sharding the chain. So the idea of sharding is like you have a layer 1 chain, but can we split up that chain into multiple chains that each have their own validators that can process transactions in parallel? And this was like what the original Ethereum 2.0 vision was. It was going to have like 1,024 shards. And I co-authored the first smart contract sharding paper called Chainspace during my time at UCL. And that was later kind of spun out into a company that was acquired by Facebook. But when I was working on this, to me there was a massive missing piece of the puzzle to making sharding work, and this is also known in the Ethereum community. And that piece of the puzzle was how do you how do you protect yourself, or how can a network protect itself from malicious shards? Because when you're sharding the chain, you're also sharding the security of the chain to all these shards. So like if you split up the chain into 10 chains, you're also kind of splitting up the security of the chain into 10 chains in some way. So you can't assume that every shard. So what happens if one of those shards is dishonest and starts kind of infecting invalid state to all those shards? So the essential kind of missing piece of the puzzle was a way to detect that shards were misbehaving, and that would basically you would use fraud proofs to do that, which is the idea that Satoshi mentioned in his white paper when he released it in 2008. This idea of alerts. But the problem with fraud proofs or alerts is that you can't, if the malicious shard does not publish the data in that shard, then you can't prove that anything bad happened. You can't generate a fraud proof. So the missing piece to the puzzle was this data availability problem to make the whole system secure. So then I kind of started researching it, and I saw that Vitalik had done some thinking around that, and he had a note on GitHub to how that can be solved, and I started kind of chatting with him, and I kind of realized that this was actually a fundamental. I was surprised that people weren't talking about it more, because it was such a fundamental element to blockchain scaling. And then I kind of realized, and I co-authored the paper with Vitalik on how to implement this and proving the security. And basic idea is that you can have data availability proofs to prove to other shards or to users that data is available. But then I kind of realized that data availability is actually the core primitive for blockchain. So at the time, people were thinking about blockchain scalability from a top-down perspective. Like, okay, we have shards, and how do we make them secure? But then, at the bottom of the entire stack is data availability. So then I started thinking about it from the bottom. If you start from that, what do you get? Because it turns out that the core thing that a blockchain does is just a proof of publication. It's a proof of publication system, and that's what's mentioned in the Bitcoin white paper. Satoshi doesn't even mention the word blockchain in the white paper. He mentions a timestamping server. He refers to the Bitcoin system as a timestamping server where you publish data into it. So the core primitive of all of these things is this proof of publication system. And it turns out that if you scale that, that's all you need, and that's indeed the primitive to all rollups. And so that's when I kind of started Lazy Ledger. I wrote a paper about Lazy Ledger, which is what Celestia now is, which is basically a blockchain that is lazy in the sense that it only does the core things that layer 1 does, which is just publish data and have consensus over that data. And that's what Celestia is. And it turns out if you just have that as a core primitive and scale it, then anyone can build anything on top of it.
Yeah, I love how the two core pieces, one comes from Satoshi and the other from Vitalik, which is sort of a metaphor for crypto today generally. So we're going to talk more about Celestia, but before we go on a little bit further, can you just define, I'm sure a lot of people know, but just to level set that, what data availability sampling is?
Sure. I mean, why don't I start with data availability? So as I mentioned, it's the core primitive of what a blockchain does. All a blockchain does is it's just basically a system that proves that some data has been published. And it tells you when that data has been published. So if you know that some data has been published, and you know when that data has been published, then you can you basically have a ledger in which you can build any decentralized application on top, including applications like cryptocurrency or payments. But what data availability sampling does is it allows users to verify that the data has actually been published without requiring users to actually download all the data themselves. Because going back to this Bitcoin block size war, remember that the whole reason why the Bitcoin community did not want to increase the block size over 1 megabyte is because they were worried that if you make the blocks too big, then the only people that would be able to verify the chain are big players who have access to data centers and big hardware. And if that's the case, then that kind of defeats the whole point of blockchains, because then you have to trust the miners, you have to trust the validators. If no one can verify the chain, then the miners basically have the freedom to change the rules of the chain, to print money, to change people's balances, for example. And the whole point of a blockchain is that you're not supposed to rely on any committee to enforce the protocol rules. It's like the end user who's verifying the chain directly should be able to enforce the protocol rules. So what data availability sampling allows you to do is it allows you to basically very efficiently, an end user can very efficiently check that the data has been published without them having to download the whole data, which basically circumvents this original problem that Bitcoin community had with increasing the block size, because now you can increase the block size without damaging the ability for end users to actually verify that the chain is correct. Because now they can check the data is published, and if they know that the data is published, they know that someone can generate a fraud proof or prove that something bad happened on chain if the validators were dishonest.
And so Celestia finally launched last fall. What do you feel has been going well, and what have you been surprised by?
Yeah, so we launched October 31st on Halloween, and I think there's definitely been a massive expansion. I think I've definitely been surprised by the amount of product market fit we've had, because when we launched, there were no chains at all that had the ability to support data blobs. This was before EIP 444. So when Celestia launched, there was this extremely pressing need in the industry that we just needed a place for these roll-ups to post data blobs cheaply. And so now we've seen kind of an influx of of rollups post their data to Celestia. There's something like 20 OP stack chains posting the data to Celestia right now, and many more in the pipeline. So there's this kind of like extreme kind of like product market fit. So I think that's going well, especially with like I always kind of envisioned 2 years ago that like 3 years or even 3 years ago, my vision when I created Celestia was that one day you'll be able to go on some website and you'll be able to click a button and immediately launch a rollup, your own rollup, which is basically a virtual blockchain. And that's now possible today. And I didn't imagine that would happen that quickly. But now we have many different rollup as a service providers like Caldera, Contribute, and Gelato that all make that possible. And now we're seeing that the default way for developers to deploy decentralized applications is not to use smart contracts on a shared smart contract environment, but to deploy their own rollup using these providers that let you do it in one single click. And like, if you asked me 3 years ago if that would happen that quickly, I wouldn't have kind of believed it, but it has.
Wow, that is super interesting to me because, it goes very much against kind of like the idea of the FAT protocols thesis in the sense that kind of almost assumes that there will just be very few. But I love this idea that there could be many different blockchains. So what is on the Celestia roadmap now that you're looking forward to?
Yeah, I think there was a few things that was presented by Ismail earlier today, but the roadmap kind of revolves around three main things. The first thing is this idea of abundant block space. So we want to have 1 gigabyte blocks, and this is very important because what we've seen in blockchain in history is that use cases have always been limited by supply of block space. Like even in Bitcoin, I mentioned that Bitcoin was used for payments before 2013, and retailers like Microsoft actually stopped accepting Bitcoin for payments. So there's actually a period of history where there was more retailers accepting Bitcoin, and then they stopped accepting Bitcoin. And the reason for that is because there wasn't enough block space, and so transaction fees were too high, so it didn't make sense. No one was using Bitcoin for payments. So you have this idea where, kind of like the early internet, more bandwidth made different use cases possible. Like YouTube would not be possible today with the bandwidth, the average internet bandwidth or speed that people had in the early 2000s. I believe that if you increase block sizes and have more abundant data throughput, it will enable applications and use cases that simply weren't possible before, or no one had imagined before. Especially like more payments on that lower value payments. Like imagine you could stream 1 microcent payments, and that was actually possible because we had the block space for it, for example. And so like so the idea is like we brought block space from the dial-up era to the early broadband era, and now as part of the roadmap, we want to bring it to the fiber optic era with 1 gigabyte blocks. The other part of the roadmap is to have a widespread adoption of trust minimized light nodes. So like instead of wallets connecting to centralized RPC endpoints like Infura and Alchemy, and this was a massive criticism of Web3 as it stands today by Moxie Marlinspike, who's the creator of Signal, that you're basically, like, what's the point of Web3 if you're just connecting to decentralized RPC endpoints that tell you what the state of the chain is and you have to trust them? That's how most people interact with Web3 today. They just interact with Infura or Alchemy. But we want to see a world where you can actually, these wallets are connecting directly to the network, to the peer-to-peer network, and verifying the state directly with these light nodes. And we're one step closer to there because now we have a Celestia data availability sampling light node that you can actually run in your browser. And that's a very important first step to making sure that those light nodes can be embedded within wallets. And finally, the final kind of piece of the puzzle, or part of the roadmap, is this idea where, okay, we're going to have abundant block space, but we also want the block space to be frictionless and useful. So like developers want access to liquidity. We don't want to have an ecosystem where you have 1,000 rollups and they're all fragmented and it's hard to bridge across them. So as part of that, we have this, we've been working on this concept called ZK accounts, where you basically can have a Celestia account controlled by a ZK program, and that will basically allow rollups to bridge directly to Celestia and with each other. So you can kind of think about it as like a more generalized version of Polygon's AG layer, in the sense like the ZK account itself is not an AG layer, but you can build an AG layer on top of it. So it's this kind of like very generalized primitive that you could that could be a powerful primitive to use to connect all these rollups together in a verified way, instead of having so many fragmented rollups.
And so just explain that a little bit further. So you have the ZK account, and so it sounds like more like a control center, and there's more execution in the rollups, or can you?
Yeah, so it's like the idea is you basically assume that, so you have an account that where the account, the funds in the account can be controlled by a ZK program. So you can imagine that you can express any rollup as a ZK program, even if it's an optimistic rollup. You can have ZK fraud proofs, for example. So now basically it means that any rollups can directly have a trust minimized bridge with Celestia. Now that's already possible today with Ethereum, for example. So that's basically making something that's possible with Ethereum now possible with Celestia. But the main difference is because I think Celestia is more suited towards this use case of defragmenting liquidity. Because the reason for that is because, one of the reasons for that is because Celestia supports IBC, which means that now, unlike Ethereum rollups, which only have access to assets within the Ethereum ecosystem, Celestia has a native way to bridge assets outside of the trust zone of Celestia in its rollups using IBC. So for example, you have projects like Noble, and you have Circle issuing USDC on Noble, and you can have IBC bridge from Noble to Celestia to that rollup. And so that kind of like gives you access to a much wider network of assets, because whereas Ethereum, your liquidity, your trust zone, your native bridging zone is kind of limited to Ethereum and the rollups. With Celestia, you have Celestia, the rollups, and also any chain that supports IBC, basically.
Okay, and then there's also this concept lazy bridging. Is that different?
Yeah, so lazy bridging is kind of like a lifestyle that encompasses ZK accounts, and the idea is that users are kind of fed up with this fragmentation. So they just want to be lazy. So it's called lazy for two reasons. That the users want to be lazy, and also Celestia L1 is minimal, and so like it's a lazy protocol. And the idea of ZK accounts is that the idea of lazy bridging is that it's ZK accounts combined with technologies like chain abstraction and things like intents. And if you combine all these technologies together, like ZK accounts and chain abstraction and intents and cross-chain contract calls, then you can basically, and things like AG layers as well, then you can basically have a seamless user experience where the user basically feels they're only interacting with one chain, and they don't even know they're interacting with different chains, and they don't have to worry about the security assumptions of all these different chains, because everything is kind of unified in a lazy way. And so that's why it's called lazy bridging.
And so when Celestia achieves its vision, then kind of like what will that overall user experience be like? Part of it will be lazy.
Yeah, I mean the user experience should be like you're interacting with one chain. You open your wallet, you see all the assets you have, even if those assets are across many different chains. Let's say you have assets on 10 different chains. You want to use those assets to mint an NFT on some other chain. You shouldn't have to care what assets those chains are on. Like you just care about the end user actions. Like the chains should be completely abstracted to the user, similar to how like if you use the web today and you're using different websites on the web, the user has no idea what infrastructure those websites are using. Like they don't know if they're using Amazon AWS or Google Cloud. The idea is to achieve a similar experience with Web3, such that the only thing that the user sees is a wallet, right? And they see assets in that wallet, but they don't need to care about which chain those assets are hosted, or they don't have to care about bridging those assets through some canonical bridge and